right, welcome back, and we are on the next lecture. We are going to be talking about RC circuits. We're going to talk about charging and discharging. And then, if we get time, we'll go into low pass and high pass filters, but I think we'll save that for another lecture just to break this up a little bit. All right, so looking on your screen, you're looking at the notes for this lecture, which is still out of this is out of chapter 3 of my book. And right away you can see there's a bit of math down here, a little bit of calculus. Again, this is not a math class, and I don't want to go into this stuff too deeply, but I just want to show it to you just one time, kind of in general, just so you kind of know what's going on and know what you need to do to solve these things if you ever wanted to, and kind of where the formulas come from. So, just as a little, side note here, when you're learning electronics or just anything really, electronics or physics, chemistry, you memorize so many equations and formulas. And if you've never derived them or never understand them, it's just like you've just memorized so many things and they're really easy to, unmemorize, right, and forget. So it's nice to kind of derive things a little bit or at least understand where they come from so that you could, if given the time and the proper resources, you could derive it or you kind of know where things come from. So I kind of like to know where things come from and their fundamentals, even if I forget about it. And there was a time I'm sure that you learned something that you've completely forgotten. I'm the same way, but at least you learned it once and it's someplace in there in your brain. If you ever need it, you can kind of go back to it. Electronics is the same way. There's so many formulas, especially when you get into more complicated things like RF theory and that kind of stuff. You just cannot you memorize all these things, and if you don't understand them, it's just like a mishmash. Anyway, so we're going to talk about two really kind of interesting and kind of fun. Once you kind of get the hang of these things, it's actually kind of fun playing with it because they do exactly what the math says they should do, which is kind of what things do. But in electronics, it's kind of hard to get things to work that way when you're on the bench because there's so many variables. Anyway, so what we're going to talk about and what the global plan here is, we're going to talk about charging and discharging of capacitors, and then we're going to talk about low pass, high pass filters, maybe in another lecture, and then we're going to talk about inductors. Again, we're going to talk about energizing and de-energizing. I don't like the word charging because they don't really charge, they energize. And then we're probably going to start talking about phasors and complex impedance. And then we'll go into some more semiconductor stuff. So the whole idea is we got to learn this stuff at least once so we kind of understand what's going on. All right, so we learned that capacitors store charge, and we learned that once they're charged up, there's charge on their plates, and it'll stay there until they're discharged through some kind of load. And so as capacitors are charging and discharging, this is kind of a transient response. They're changing over time, rapidly, transiently, and we want to understand, how that happens and kind of the math behind it. And the reason why that'll let us understand what's happening when we start kind of moving things to a digital domain, and we have clock signals that are square waves, and we'll see these square waves are not square waves. They start bending and deforming. But the reason why is because of capacitance and inductance. And then we'll know why based on our knowledge of transient analysis. So again, you're never, ever probably going to use these formulas when you're designing something. You'll use the final formula sometimes, but you'll never have to derive anything. But it's just nice to know how. And all of these things we've kind of talked about before. All right, so let's get started. So again, you've got these notes and you can go through them slowly and look at other resources, but I just want to go through these things and kind of see what we see here. So, all right, so let's see. All right, Control Shift 6, that erases this little highlighter. All right, so looking at the screen right now, we're going to talk about the circuit that you see right here. All right, and so this is a kind of a representation of something we would use to be able to kind of charge up a capacitor and then discharge a capacitor, and then kind of look at what's going on. So what you see here is we've got a voltage source, an input VI, and this could actually be a function of time, but right now we're just going to say it's a steady voltage of some value, 5, 6, 9, 12 volts, whatever. All right, and at at time right before 0, this switch is in neither position you could think of. Maybe it's just straight up, so it's not connected to either thing. So the capacitor has no charge on it, just sitting there, just waiting for something to happen. All right, so like maybe at time 0, what we do is now we switch the switch here to position 1, and then what's going to happen is we're going to get a current, like that, right? And so what's happening then is we've kind of got this circuit down here in B. The battery or voltage source, the current source, is going to start charging the capacitor through the resistor, and at some time in the future it's going to stop charging. So remember, what's going to happen is there's going to be an initial rush of current, and then this current's going to decrease as the charge accumulates on the plates, and then at some point it's going to stop. We want to know what that looks like, right? We want to know what is the math behind that exactly, so that we can write things down and do computations. Okay, so that's one case. Now the other case is over here in figure C. And in that case, now, so the capacitor is charged now. And so now imagine that instantaneously we, flip the switch and we move it over to this position. So now the capacitor, which is charged plus to minus, is going to discharge through the resistor. All right. Now our question is, what does that look like? All right. So that's discharging, and that's C. So B is charging, C is discharging. All right. So those are the cases that we're kind of interested in here, and we want to kind of mathematically model what's going on here. All right. So what I want to do here is we're gonna kind of we are gonna skip this case for right now, and so this is the charging case. We're going to skip this for right now, and we're going to jump to the discharging case, and we're going to kind of work through this because it's a little bit simpler. And then we'll come back to the charging case and then kind of look at what's going on right here. All right. So let's actually go through and look at this this discharging case. All right, and kind of see if we can kind of figure out what this looks like. All right. So let's go ahead and do that. So let's go to our drawing program here. Okay. All right. So let's get a good color here. So get a good color. How about, we always like green, or I do at least. It's nice and bright. Okay, so, and again, this is not a math class, and but we just can't avoid some of these things. We got to do them. Okay, so so what we had was, we had a voltage source, right, which is could be a battery or something. It's just a static source in this case. It's not changing. And then we had a resistor, and then we had a capacitor, like this. All right, and then we assume that for a very long time this has been on, very long seconds, minutes, hours, whatever is necessary to completely charge the capacitor. So when this thing turned on, there was an initial current, I that went around like this and charged this thing up, and then the capacitor charged up with plus on this side and minus on this side, completely charged, and then there was a voltage developed here, right? So there was a voltage plus to minus developed here, and then there was also a voltage drop, we'll call it VR over here, and then this voltage source, we're kind of calling it VI. So sometimes you'll see VI for V input, or you'll just see it V, or you'll see it VS. All these things are just ways to label these things. All right, so for a very long time, so this is all charged up, and now our capacitor is charged. Now let's imagine that we get rid of this power source here. We short it, and then we let the circuit discharge. Okay, so now that's what we're going to do. We're going to discharge the circuit. So now we've got this scenario here where we've got our circuit, and we've got our resistor, and we've got our capacitor again. And I hope I have enough room to do the math. We'll see. All right, we've got R, we've got C, and so now we've still got all the positive charge here. We've got negative charge here. All right, and let's use a couple different colors here. And we'll say that this is, oops, we'll say that we've got a current here. So now it's going to discharge. So the current was going in this direction, in this clockwise direction. Now the current is going to go counterclockwise, right? Because the capacitor is going to discharge. All right, so the capacitor is going to discharge. There's no more battery or source in here. This is what's happening. So we've got this right here. Okay, now the voltage on the capacitor, right? So we could call this, let's just call this, we can call this V, right? And uh, let's put a little node right there. Okay, and then now as this current flows, and we can call this current I, let's call this current I, there's going to be a voltage drop over the resistor, right, because there's a current, and it's going to drop plus to minus, right, because the current is going, you know, in this direction, right, plus to minus, all right, and we could call that if we want, we could call that VR, all right. Okay, so now we kind of have everything. Now, what do we know here? And of course, this is, you know, plus and minus. And remember, the current is going to, you know, go this way. It's going to go counterclockwise now. So it charges up clockwise and then it discharges counterclockwise. And we're assuming it already charged. That has its modeling equation, but now we're going to do the discharge because it's a little bit easier. All right, so at this point, we've got everything, we're ready to go. And now, so let's start writing some things down. So let's write down some stuff so that we have it again, so we don't have to wiggle around and try and remember things. All right, so how about, you know, one thing is V equals I times R, right? So that's Ohm's law. All right, and then the other thing is we know that I in a capacitor equals C dV dt. So this is the general equation. This is just one of them. And what's I? That's really dq dt, right? So we could do this in terms of charge if we wanted to, but I like to do things in terms of current. I mean, no one ever works in charge, ever, ever, ever in a million billion years, unless you're doing a physics class or an electrical engineering class, then you'll do things with charge. But electrical engineers and embedded engineers, the only two quantities are I and V, and then, you know, resistance, capacitance, inductance, and all that. But I and V, we don't use charge. So that's kind of silly. All right, so I equals C dV dt. So let's see, can we write some kind of equation to constrain what's going on here and then start solving for it, all right? Okay, so so the current coming out of the capacitor is C dV dt, all right? So C dV dt, okay, that's the current going out of the capacitor. But there's one little detail, I'll get to it in a second. Now, what is the current going through the resistor? Well, I already know what the voltage is. The voltage is this V, the capacitor's voltage, and that's going to be divided by R. So it's simply just V over R. That's it. There's nothing more. V over R. Okay, now there's one little detail here. One little detail that we need to add. So this modeling equation, I equals C dV dt, notice that the current is flowing in this direction and it's flowing down. When that's happening, I equals C dV dt. So if the current is going from plus to minus, I equals C dV dt. But in this case, wait a minute, the current is going up. Even though the charge is in the same place, now current's going to flow back out of this thing. So the currents can't be C dV dt anymore, right? In this particular case, it's got to be minus. There's got to be a minus sign here. All right, we got to flip that. Got to be very careful with that. All right, so we have to take this general equation and consider it in both of these cases. So now this is what we have. So we have this right here. All right, so we've got that right there, and this is what we need to solve for here. Okay. All right, so let me just bring this over here. Let's get a brighter color. All right, so let's bring this over here. So we have minus C dV dt equals V over R. Okay, so this is a differential equation. And so all that means is we've got some function. Now V really means V of t, right? So this is really V of t. It's a function of time, right? V of t. But we're just calling it V right now, so we don't have to write a bunch of sub t's. But it's a function of time. So this is a differential equation. What a differential equation means is that we've got the variable v, which is a function of time, and then we have its derivative. And what the derivative as a function of time means, its slope. So what this says in English is v over r equals, so the function over r divided by r equals the derivative of the function with respect to time times minus c. That's it. It just says they're equal. But what's the derivative? That just means the slope. So it just means the slope. So here's an interesting thing. The function with some constant divider equals itself, right? But the slope of itself with respect to time times some other constant. Okay, so let's simplify this a little bit so that we can kind of see things a little bit better. So let's see here. How about dv dt equals 1 over minus RC times V. All right. So okay, so that's it right there. Okay, so we've got this function V, and whatever that is, its derivative with respect to time equals 1 over minus RC times V. So this is a differential equation, and if you've done this in school, you get this. If you haven't, this looks kind of circular. It's kind of like the derivative of the function with respect to time equals some constant times the function. That seems kind of impossible, whatever this derivative is, but it really just means the slope of the function equals some constant times the function. There are functions that'll do this, all right? And so now when you learn differential equations, you learn different kinds of solutions to these things. You can derive them, but basically you learn that certain classes of functions have certain kinds of general solutions, and the solution for this, I'll tell you, looks like this. So V equals some constant e to the minus t over, and I'm going to use this thing called tau right here, all right? So V equals AE minus e to the minus t over tau. And so this is E, which is just the constant, the mathematical constant E, 2.7 and some change. And that's it. So now if I take the derivative of this right here, so the interesting thing of this function right here, so again, you don't even need to know calculus. So let me show you something real quick, just real quick. Let's say if we have a function of x, and the function equals ax to the n, all right? So if we want the derivative of this, say if we wanted df of x with respect to x, so the derivative of this, if you have just a simple polynomial like this, a constant, a variable to the power, is simply the power, you bring it down here, you bring the power down here, n, and then times the a, and then x, and then now n minus 1. So that's it. So if someone were to say, hey, what's the derivative of 3x to the fourth? Right? What's the derivative of that? If someone said, what's, ddx of 3x to the fourth? You would say, okay, it's 4 times 3, that's 12, x to the 4 minus 1, 3. That's it. That's it. It's not magic. It's just a mathematical function which computes the slope. All right. So this function right here, though, has an interesting property. The exponential function has an interesting property that when you take the derivative, you get the function back just simply with this out in front of it. All right. So in other words, exactly what we want is we want the derivative of something equals the something just with something out in front of it. And that's exactly what this exponential function, when you take the derivative, does. Google it, look up derivative exponential function, you'll see what I mean. All right. So the result is in this form right here. And what we want is we know this. Okay, so now what we want to do is we need to solve for these constants because we're looking for V. We're not looking for dv dt, we're looking for V. So we know that it's of this form. Okay, so what are some things that we do know? Well, we do know at time t equals 0, V equals like its initial condition. And that was the initial charge on it from whenever it was charged up, all right? So that's the same as, so we could say at time equals 0, right? Right when this thing starts off, the charge on it, V, is simply V sub 0, right? That's whatever the initial charge is on the capacitor, all right? So V sub 0. So if it's okay, I'm just going to call that V sub 0, like the initial charge. Okay. And that initial charge, what's that really? That's really going to be this V sub I. Because remember, when this thing gets done charging up, we don't know how exactly it charges up. It does some function. When it's done, it's going to charge to whatever that voltage is. So it's kind of like that V sub I. But we'll just leave it as V sub 0 right now. Okay, so V sub 0 equals A, which is some constant, and then E to the minus at time t equals 0, 0 over tau, right? Which is, this is just e to the 0. Anything to the 0, right, is 1. So this is V sub 0 equals A. All right, so a equals v sub 0. Okay, so this thing here, this guy is v sub 0. All right, so now we're getting there. So now we know that v equals v sub 0 e to the minus t over tau. Okay, so we're getting someplace. Now this tau, how are we going to get this? Okay, so we need to solve for this right now. All right, so let's look back at what we have. So we have that the derivative of our function with respect to time equals 1 over minus RC times V. All right, so can we use this to try and find this tau somehow? All right, so that's what we're going to do right now. So let's do that. Okay, so let's see here. All right, so our function, we can go back with this right here. All right, so this says that the derivative of v with respect to time. So here's our v. So we want the derivative of v with respect to time. So I'm going to differentiate this. So here we go. So let's put v down here equals, and we could put the a there, or we could put the v0. Want to put the v0 since we already figured it out? Why not? Okay. Okay, so now what I need to do is I need to differentiate this thing. All right, so I'm going to differentiate both sides of it. All right, so I'm going to differentiate dv dt equals, all right, and when I'm done, this equation says it's going to be 1 over minus RC times v. All right, so here we go. And so let's differentiate this right here. And when we differentiate this, we're going to get simply this term right here looks kind of messy, but it's just minus 1 over tau. All right, so we're going to get equals v0, and we'll just parenthesize that, minus 1 over tau. Oops. All right, and then we just get this back again, which is just e to the minus t over tau. All right. And so the derivative of this function equals 1 over minus RC times V. This is the derivative of the function. It equals this thing right here. So this has to equal this. So it has to equal 1 over minus RC times V. Now, where is V? V is just this thing right here. So we're looking for V naught e to the minus t over tau. There it is, V naught e to the minus t over tau, right? So so now what we can say is V is right back here, right? So it's V naught, V naught. We can leave it like this if we want. We can leave it like this if we want, but let's just go ahead and fill it in. So V naught, and then e to the minus t over tau. Okay, so now if we look at both sides of this, right? So here's the v naught, here's the v naught, here's this e to the minus t over tau. So we can cancel this out with this. We can cancel out v naught with v naught, and then we're left with this right here. And I hope you can see this. I hope the little screen over here is not covering it. Anyway, so now we have that 1 over tau equals minus 1 over tau equals 1 over minus RC. So we can get rid of that, we can get rid of that, we can invert it. Tau must equal RC, okay? So tau must equal RC, thank goodness. So that's it. So now finally, if we can find a place to write this, our final equation is V as a function of time equals whatever the initial voltage on the capacitor was when it was charged. We can call that V0, or we can call it V sub 0, e to the minus t over RC. So that's it. So that is the equation that describes what the discharging will look like mathematically. And I know it's just, what a mess, huh? Brutal. And this is the easy way to do it. There's a harder way to do it, which is even more messy. So, but again, once you remember this, it's pretty easy. So this RC is called the time constant. All right, and so I want to talk about some more stuff about that. Let's go back to the notes now, and I want to show you some stuff inside of the notes. So let's go back to the notes. All right. So, and again, we're gonna go back to the other case in a second. So let me scroll through this. All right, and okay. So I want you to look at this right here. Let me zoom into this here a little bit. Okay. All right, so this is kind of what we just figured out, right? We just kind of solved this situation here. And this is what the discharge curve looks like. So it's exponential, and basically V equals the initial charge on the capacitor times e to the minus t over RC. So RC is this time constant, all right? And so this is what it looks like. Now, uh, the time constant RC is going to be in both charging and discharging, and this is going to come up in many, many places. In any kind of RC circuit, you're going to see this RC in a lot of places, and this is why it's called tau, all right? And it's going to come up all over the place when we do filters and all that, all right? So now, this is the easy case. So this is when the capacitor discharges. All right, let's look at now when the capacitor charges. So let's go back up and into the notes here, and I want you to see this figure in a second. We're going to talk about that in a minute. All right, but I want to talk about I want to talk about this right here, this figure right up here. Okay. All right, so again, in the charging, we make this connection and we've got an RC circuit and the capacitor is going to charge. Now, this is the math. If you run through this and you solve this, and this is a little bit more complex because it's not just a constant times the exponential, there's a constant plus a constant times the exponential. But when you do all the solutions, then you find this. So here is the charging. So V equals VI times 1 minus e to the minus t over RC. All right. So I don't expect you to memorize that right now, but keep that in your mind for a second. And what I want to do is I want to go to our drawing program, and let's take a look at what's going on here a little bit. All right. So, oops. All right, so let's first let's pick a color here. Okay, so let's do our RC discharging here, right? So we've got RC discharging. All right, and we know that that looks something like this. All right, we've got some initial voltage. We're going to call it VI, right? And it's going to discharge like this. Okay. And so this right here, this axis is voltage, and this axis, of course, here is time t. All right, and the thing that models this is, and then this curve right here is v as a function of time equals, what does it equal? It equals vi times e to the minus t over tau, or which is RC. Okay, so that is discharging. All right, now charging. So now RC charging, and the only reason we did these backwards is because it's a lot easier to do the discharging math. RC charging looks like this. Looks like this. So it looks like down here again, this is time t, and this is voltage here, voltage V. All right, and again, this is 0 in both axes. Okay, so RC charging looks like this. And we have this exponential curve that gets asymptotic, and that is, okay, that's horrible. Let me do that again. Okay. All right. And so this curve is asymptotic, is the term. And what that means is it never, ever, 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 ever reaches this in reality, except at infinity, right? But it gets closer and closer and closer and closer. And what is that point that it gets up to? Well, that's just VI, right? That's that initial voltage that it's going to charge up to, and then it's going to discharge. So what do we have here? And actually, the charging curve, we can just put the discharging curve right on it. So If we charge the thing up and then we discharge it, right, it's going to look like this, and then discharge, right? So it's going to charge and then discharge. Okay, so that's the charging, and then what does that look like mathematically? So that looks like V sub t equals, and this one's a little bit, it's really not that hard if you think about it. It's V sub I times 1 minus e to the minus t over RC. All right, so they're very, very similar. They're very, very similar. They're just kind of analogs of each other. In one case, you're discharging, and then this, when you memorize these, sometimes it's hard. You kind of think this one kind of feels like a discharging because there's a minus in here. Well, let's see what happens. So at t equals 0, what does this one look like? At t equals 0, this term, the exponential, is e to the 0, so it's 1. So at t equals 0, we have vi, all right? So is that right? So here's t equals 0 here, right? And sure enough, we have vi. That's the initial voltage. That's the battery or the whatever's charging it up. Okay. At t equals 0 here, let's see if this is right. So this term right here, when t equals 0, this goes to 0. So e to the 0 is 1. 1 minus 1 is 0. 0 times vi is 0. So at t equals 0, which is right here, right? Again, we have a voltage of 0 volts. So that makes sense. Now let's imagine that t goes to infinity. All right, so let's do that for a second, if that's okay. So let's do t goes to infinity. So as t goes to infinity, what does this really look like right here? So what it really looks like is this. So this is equals vi, and then 1 minus e. All right, so this is e to the minus t over RC, right? So let's just for a second, let's pretend that RC equals 1, all right? And the product equals 1. It's not going to matter at infinity, right? Because infinity is going to be bigger or small, 1 over infinity will be smaller than anything. So let's just pretend RC is 1. So if RC equals 1, so when RC equals 1, just to make this easier, we have 1 minus e to the minus t, okay? All right, but what is that really, right? So that's really 1 minus 1 over e to the t, okay? Right? Anything to a negative power is just 1 over that to the positive power. Okay, so as t keeps getting larger and larger, right? E to that gets larger and larger and larger, and as it gets larger and larger and larger, 100, a million, a billion, a trillion, a quadrillion, a septillion, and on and on and on, this term goes to 0, right? So this is going to 0. As this term goes to 0, what do we get? Well, we just get this 1 here times vi. We get 1 minus 0, so we just get 1 times vi. So at infinity, and here's time moving towards infinity, and so see this over here, this is kind of, moving towards infinity here. As we go towards infinity, then the voltage, V of t, goes to V sub I, and sure enough it does. Asymptotically though, because it can never reach it until it reaches infinity. So that's it. But now here's the other thing that I wanted to bring your attention to. So I want to find over here a figure that kind of shows this for you. And let's see if I can find it, then I'll move it over here. I want to show you. So we talked about that RC time constant, right? And that's going to show up everywhere. All right, take a look at this right here. So in this figure right here, you see this is a charging. And as we're charging, if you do the math, if you let t equal RC, in other words, if the time that you allow this thing to charge equals R times C, so you would get minus R times C over R times C. That would just be minus 1. So you would get 1 over e to the 1, right? And so if you got 1 over e to the 1, let's do the math. So 1 over e to the 1, so let's just do e to the 1. So we'll do shift e to the 1, which will just be 2.7 and some change, right? Okay, and now if we invert that, right? If we invert that, we get 0.36. 1 minus 0.36, right? Minus 1 is, 1 minus 0.36, right? 1 minus 0.36 is approximately 0.64. So it's about 63% actually. So the whole point is that when the time equals 1 RC time, when the time t equals 1 tau or 1 RC, you're already going to be charged to 63% of the total value because this term here turns into 0.63. All right. So because there's an exponential here, this term very, very quickly diminishes, and because it's a 1 over term, right? Because it's to a negative power, it diminishes very quickly. And as it diminishes very quickly, this whole thing goes to 0, and then this goes to 1. So in about 1, 2, 3, 4, 5 RC times, in about 5 RC times, you're practically 99.999% charged up. And that's kind of what this is showing. So here's T equals RC, or T equals tau. At 5 RC times, and this is this little tip right here, at 5 RC times, for all practical purposes, the capacitor is charged or it's discharged. All right, so 5 RC times. And then if you were to plug in and do the math here, which we can do, so let's actually go to the let's go back to the board, and let's take a look at that. So let's see if we let something charge up for 5 RC times, what will it be charged? All right, and then let's actually do this with a circuit. All right, just to make this more interesting. Okay. Okay, so let's do a charging circuit. All right, so here we go. Let's do a charging circuit. So let's say that we have a battery. All right, and we have a resistor. And let's make this 1K. And let's make this capacitor. And this is R, and this is C. And let's make this capacitor, let's make it 2.2 microfarads. All right, we don't want to make it too simple. All right. This battery, it's a 9-volt battery, let's say, 9-volt battery. So when we turn this circuit on, the second that we connect this, right, we connect it, boom, what's going to happen? This thing is current is going to start rushing out. All right, and we're going to get this current I. We're going to start charging up this capacitor, right, plus to minus. And if we look at this curve, the curve is going to look like this over here. Here's time, T, and then up here is voltage, V, all right, and then here's the origin here. All right, and then as this thing charges up, it's going to, do this kind of thing, right? And it's going to asymptotically go to, what's it going to go to? It's going to go to here, right? And this is the 9 volts. All right, and so the question is, what's it kind of doing in the middle? Well, we know exactly what it's doing in the middle, right? Because we know what the modeling equation is. So what's the modeling equation? The modeling equation for this is for charging, right? Is what? And so let's put something here. So we'll call this plus to a minus. We're going to call this V sub t. Okay. So V sub t equals the initial voltage here, right? Which is 9 volts. So 9 volts, 1 minus e to the minus t over tau, which is RC, right? So that's 1K times 2.2 microfarad, right? That is the equation that will describe what's going on here. So let's clean this up a little bit. So we've got V sub t, and I'm just going to take away the voltage here, the V, and just leave it as a 9, okay? 1 minus e to the minus t over, now let's figure this out. Let's get our calculator, right? So we've got 1K times 2.2 micro equals 2.2 times 10 to the minus 3. All right, but that's in the bottom, so I'll leave it there for now. So down in the bottom here, we've got 2.2 times 10 to the minus 3. All right, that is our tau. So tau equals 2.2 times 10 to the minus 3 seconds. All right, so what this says is that, and so this is our RC time, this is tau. At 1 tau, so if we go here and say that this is like that's 1, and that's 2, and then that's 3, and that's 4, and that's 5. So if we say that each one of these is 1, this is a millisecond, right? 10 to the minus third. So if this was 1 millisecond, and this was 2 millisecond, and this was 3 millisecond, 4 millisecond, and so forth, right? Then right here at like 2.2, right here, so at 2.2, that's 1 RC time. If we come up here, right, to here, then this should be at roughly 63%. And I haven't drawn this correctly, but this will roughly be 63% times the 9 volts, right? So 0.63 times 9 volts equals 5.67. So again, I have horribly drawn this to scale, but this would be 5.67 volts at 1 RC time. That's what's going on. Now, so the question is, we want to know at 5 RC times, what is the voltage? So let's do that. So we want to say at 5 RC times what's going on. All right, so let's do this. So we have V sub t equals, all right, and then we've got 9, and then we've got 1 minus e to the minus t, but t now is going to be 5 RC, 5 times RC, over, and now we're just going to leave this as RC, right, like that. Well, the RC's cancel out, so it's just e to the minus 5. So this is equals 9 times 1 minus e to the minus fifth. Okay, so let's do that with our calculator. Okay, all right, so what we have here is 9, 1 minus, and then this is really 1 over e to the 5, right, e to the fifth. All right, so when we do that, we get 9 times 1 minus, and then we'll do e to the fifth here, e to the fifth, and then we'll invert that. And then just to show you how small this number is, we will say, let's do this. So this number here is 0.0067 ... and something else. So this is 9 times this, and this is practically 0, so it's just 9 times 1, so it equals 9 volts. In other words, at 5 RC, this is so small, right? This is, really what, 6.7 times 10 to the minus 3, right? This is so small, it's infinitesimal. At 5 RC times, we are like 99.9999% fully charged, all right? So that's it. So at 5 RC times, you're fully charged, all right? So that's the rule. And then the same thing happens with discharging. So now if we were then to get rid of this battery and short the battery, so if we came here and we shorted the battery, then it would start discharging, and then basically as this thing charges, wherever we are here in time, it would then start its discharging, right? And then this discharging in 5 RC times would be all the way to 0. So that's it. So anyway, so that's RC charging and discharging. And this is why. And then one last little thing. So I think yeah, we have time. Let's go ahead and let's go on the bench, and we're going to do a simple little experiment. And what we're going to do is this. We're going to synthesize what happens with cables. All right, so now, so one thing is that you may have, learned about or seen, or in some context, is, so here's time here, and here is voltage here. And say you have a square wave, and you put a square wave down a cable, and you have this nice, beautiful, whoa, all right, unless Andre draws it, you have this nice, beautiful square wave, which represents a signal or some bits or data, whatever, and the signal gets really, really distorted. The reason why it's getting distorted is because there's R and C in the cable, resistance and capacitance through the cable. And it distorts the signal because it's charging up capacitance, right, and then discharging. So what does this signal turn into? It turns into this. What it turns into is we charge like this, and then we, discharge like this. And then we charge like this, and then we discharge like this. So the square wave turns into this bizarre sawtooth shark jaws looking thing. And the reason why is because there's RC charging and discharging, and this comes from the impedance or resistance of the cable and other electronics that are connected to it. This is why when you run things down cables, you want to have low capacitance and no capacitance and no resistance, because you want these signals to end up down the cable the way that they started. Otherwise, you get this distortion. What does that cause? All right, so let's zoom into this real quick. So what that causes is this effect. It causes this to happen. So if we look at the square wave here, so here was the nice square wave to begin with, right? Okay, and now it kind of looks like this. All right, and then it kind of looks like this. So normally the electronics, whatever circuit was getting, so it used to see this nice sharp, rising edge, so it would transition really quick. But now, because this thing is struggling to get up here, there's time is occurring in here. So what happens is the circuitry, maybe before at this time here, call it time 1, it transitioned to a 1, but now this thing's struggling, and finally here at maybe position 2, it toggles to a 1. So things start getting skewed, right? And time starts getting delayed. And the same thing here. Now it just instantaneously used to drop, but now it's still a 1, a 1, a 1, a 1, a 1, a 1. Okay, now it's a 0. Right? So it becomes a 0 here at this time here, this time 3, and we really wanted it to become a 0 right there. So anyway, this is why capacitance and resistance inside of your cables is a bad thing. All right, so you got to watch out for that. Okay, so let's go ahead. We're going to go over to the bench, and we're going to do a little experiment to show how we can deform a square wave signal inside of a circuit by putting some resistance and capacitance. So this will be kind of a quick little fun way to end this lecture with an experiment, which we always like to do. So meet me over at the bench and let's do that. All right, so normally I like to put things together while you're watching, but getting this analog stuff to work sometimes is kind of finicky and it just kind of wastes a lot of time. So it's not really important in this case. So what we have set up is if you take a look at the equipment screen here. So over here we've got the oscilloscope. The top line is going to be the input. The bottom line is going to be the output. So we're going to see the original wave and then the distorted wave on the bottom. Over here we've got the signal generator, and we're going to be putting out a square wave. Right now we've got it set for 5 volts and it's at 1 kilohertz, but we're going to change that. Okay, now back to our circuit. So let's take a look at our circuit. So the whole idea here is the signal's coming in on the red line, and then this is ground all down here. So the oscilloscope grounds for the probes, and then the signal generator ground. So this probe right here, the top probe, is the signal coming in that we're watching. That'll be the yellow one. And then the signal's going to come in. Forget this top resistor right here. Just ignore that. And then it's going to come in, and we're going to have some resistance. And right now I think I have that as 1K. Brown, black, red, 1K. And then we're going to have some capacitance going to ground, and that'll be kind of our RC charging circuit. So we're taking the output from the capacitor node itself. All right, then that's going to travel along this, and then we're going to get the output right here. So this simulates a circuit trace that would be on a circuit board. Now, there's inductance in this circuit, but we're not going to worry about the inductance because the frequencies are low enough where it's not going to come into play, and we don't know yet about how to model the inductance. But there's distributed capacitance, resistance, and inductance. So everything distorts everything depending on the frequency, all right? So right now we'll just pretend the inductance isn't there. The whole point of the experiment is we're going to show that if we take a nice square wave and we send it into a a black box or some components, and those components have distributed resistance and capacitance, we're going to distort that waveform. All right, so that's what our goal is to see that effect. Now, right now, there is no capacitor going to ground, so we do not have the capacitive component of the circuit. So we're just going to do a couple different runs, and then we're going to add capacitors, and we're going to see how the different capacitance affects things, okay? All right, so what I'm going to do is, since we don't need to look at the circuit's not changing, we're going to change the view and we're going to look at the equipment so we can see what's going on. All right, so now we're looking at the equipment. All right, so the first thing that I'm going to do is I'm going to turn on the signal generator. All right, and as you can see, the top wave is the input and the bottom wave is the output through the distributed system with resistance and capacitance, except we have no capacitance right now, so just resistance. So the only capacitance we have is basically in the oscilloscope lines and the wires and that kind of thing, so it should be very, very little. All right, so we should be able to run this frequency up and have no problem. So right now we're at 1 kilohertz. So keep an eye on things, the 1 kilohertz signal right here, and keep an eye on the oscilloscope. So what we're looking for is distortion of the bottom wave. All right, so I'm going to start turning this up, and we're at 10 kilohertz, and then I'll crank up the frequency here so you can see. So everything still looks good. All right, so now we'll go on to the 10s and 30, and we're going to keep going. All right, and there's 200 kilohertz. Everything still looks good. All right, and let's keep going. And now we're to a megahertz, and now I'm going to get on the megahertz adjustment. Now I don't know if you can see this, but we're starting to see some distortion here, and sometimes getting the oscilloscope to lock into things is a challenge here. So let's see if we can get the oscilloscope to cooperate with us a little bit better here. We'll do an auto set. Give that a second. Okay, and we'll put this up, do this, and okay, turn that down. Okay, good enough. Okay, okay. All right, so you can see we're starting to get a little bit of distortion. So this is, from capacitance and inductance that are just in the lines, and also this resistance that we've added in here. But it still looks not bad, and we're at 1 megahertz. All right, so let's keep going. 2 megahertz, 3 megahertz, and so forth. And you see at 6 megahertz here, we've got a triangular wave on the bottom. The top wave is still okay. We're seeing some little bits of ringing and whatnot in the top, but the bottom wave is definitely distorting. And there's 5 megahertz, and then you go up to 10 megahertz, and now I've got this triangle. So what's happening? There's a lot of things going on here, inductance and whatnot, that's causing this to occur, and that's why we're having what are called transmission line effects and different things. And so now let's back off of it now. All right, so let's back off of it to where it wasn't happening. So let's back off of it back into kilohertz. So at 100 kilohertz, we're pretty safe. And you can see if we open this up, and you can see right here on the oscilloscope, we can see that little edge there. That's an RC charging edge. There's some capacitance there, right? But if we zoom out, we can't really tell. Okay, now let's add some capacitance into it and let's see what happens. So we're going to start off with 47 picofarads, a teeny tiny capacitor. So let's go back to look at the circuit here, and we're going to add this in. All right, so now imagine we have a little bit of capacitive load. And all right, now back to the oscilloscope. Let's turn the frequency up here. All right, so 100, 200, 400, 500 kilohertz. Let's open this up. And again, we're seeing this effect, and at a megahertz, we're seeing the effect. It's pretty much similar to what it was. Let's pull the capacitor out in real time and let's see what happens. All right, so did you see that? So the capacitor is definitely causing more distortion. So there's with the capacitor, with no capacitor. And this is a tiny, this is picofarads. This is 10 to the minus 12th farads. There is nothing here, but you can see it's, really affecting that quite a bit. And if we go up to even a higher frequency, let's go up to 5 megahertz. So there's 5 megahertz. All right, with the capacitor, that waveform is just, it's brutalized, right? It is brutalized. And let's take the capacitor out. All right, there's with the capacitor out. And with the capacitor out, it got some semblance of a square wave, right? We can see the charging and the discharging, right? You can see the charging and the discharging, beautiful, right? And now let's put that capacitor back in. This little picofarad, you can look at it, it's totally triangular and it's attenuated as well. Because what's happening here is there's filtering going on. We've created a filter, and we've created an RC filter as well. And we're going to learn about that, but I wanted you to see this in action. Now, let's get back to where we should be okay. So at about 500, at about 100 kilohertz, if we back off this, our square wave more or less looks like a square wave. So we're at 100 kilohertz right now, and we're back to normal even with the capacitor. So we're going to take it out, but let's add some more capacitance. Instead of picofarads, let's put microfarads. And now watch how bad this gets. So now we've got, this is a 0.1 microfarad capacitor I'm going to add in here, all right, 0.1 microfarad. And right now we're at 100 kilohertz. Now watch this. So down on the board, I put it in. So now I've got 0.1, oops, put it in the wrong place. There we go. All right, so I've got 0.1 microfarad, and now look what happened to our signal. There is no signal. So two things have happened. We've not only have we RC charged, we're doing RC charging, but we've attenuated the signal enormously. So what I'm going to do here is I'm going to put this on AC coupling, which is going to cause more distortion because then there's a filter inside. But I'm going to amplify this so you can see this a little bit. All right, and forget about those noise, those spikes going up. We're at 100 kilohertz, and we now have this complete triangular wave. And now the amplitude, look at the second channel, it's 100 millivolts. So we had a 2 volt on the yellow, so 2 volts per division. So we've got a nice 5 volt signal, and now we're only getting 100 millivolts out. It has just been completely attenuated and distorted. Now, but we're at 100 kilohertz. What happens if we go to a higher frequency? Will it get better? It doesn't look like it, right? It's getting worse and lower and all that. Okay, let's go to a lower frequency now. So let's go to a lower frequency. Now we're at 100 kilohertz. Now 90, 80, 70, 60, 50, 40. Now look, the signal's getting bigger. Okay, now it's getting happy, right? It's getting really big. So now we can turn our amplification down. We can do this. Okay, now we've got 500 millivolts per division on the bottom, so it's getting better. We're at 10 kilohertz. And now, look, I'm going lower frequency. I'm 5 kilohertz, 4 kilohertz. I'm at 1 kilohertz. Now we're getting in business. All right, and let me do that. So now look what's happened here. So we've got a 1 kilohertz signal, and if we zoom out a little bit, it's not too bad. We're seeing definite RC charging. The scale is almost the same, so the attenuation is going away. So we're seeing the charge and the discharge, but we're not seeing, but because we're not doing it too fast, it has time to charge and time to discharge. But as we increase the frequency, that charging and discharging, it doesn't have time. So it starts and it stops, starts and it stops. And that's why it's attenuating and deforming so much as you see it there. We're at 10 kilohertz and the signal is completely gone, right? Okay, now let's go down to less than 1,000. And there's 900 hertz, 800, 700, 500, and 400, and 100. We're at 100 hertz. So at 100 hertz, and let's get rid of the AC filter, and let's put it back to DC. On channel 2. All right, so now 100 hertz, we have our signal and it can survive. So 100, at 200, at 300, it's okay. And then it starts, getting obliterated at 1 kilohertz. So the reason why is because we've got this capacitance and resistance on here, and we're creating a filter, which we're going to learn about. But we can see this RC charging. And so what's the point? The point is, in the first case, we had a capacitance of 47 picofarads, which is, when you start looking at chips, you'll see that they have input capacitance of picofarad range. In other words, they're going to have very little effect, picofarads. But if you start putting microfarads, right, even microfarads or nanofarads, you are going to put a lot of capacitance on these lines, and you're going to start to see these deformations in your signals, all right? So that was just 0.1 microfarads. Now, can we help it by decreasing the resistance in the signal line? Yeah, sure. So the RC time, it's R times C. So we've got this horrible signal right now at 1 kilohertz. Can we fix that by changing this the 1K? So can we increase the drive, and would that help us a little bit? Yeah, sure. So let's increase the drive. So let's go back to the circuit, and let's put a 100 ohm. So I've got a 100 ohm, brown, black, red. And I'm going to pull out the 1K, so signal's gone. Remember what that looked like. And I'm going to put the 100 ohm here. All right, and now look at that. So now that's not bad. That looks pretty good, right? And so now let's go up in frequency. So 1 kilohertz, 2 kilohertz, and now at about 5 kilohertz, we're at the same place we just were with the 1K, we're at the amount of distortion, but now we're at 5 kilohertz instead of 1 kilohertz. So now we've increased our frequency that we can send signals out without, them being too deformed, right? And then of course, if we keep going up to 10, now we've got our triangle wave, and maybe our electronics can tolerate this, but what they're not going to like is continued attenuation. And then notice what's happening. There's a DC offset here, so we're staying way up high. We're never going down low because we just don't have time to. We don't have time to because the frequency is too high. So for all intent purposes, we've just got a constant 1 signal here, right? Even though we've got an up and down going from 0 to 5 volts, the capacitance just can't discharge and charge fast enough, so it's hanging up there. All right. This is the basis of also certain kinds of D to A converters, right, called PWM, pulse width modulation, which we'll talk about at some point. Okay, so let's back down. All right, and so this is the reality. This is what's going on when signals get distorted. All right, so this is good. All right, so what did we do? We increased the drive. So we increased the drive to this 100 ohm resistor back on the circuit board here. So that helps. So what do we know? We know if we want to send signals in circuit boards, we want to make sure they have a lot of drive. We want to make sure their impedance, their resistance is very, very low. So that's 100 ohms. What would happen if we made it 10 ohms? All right, obviously we know what's going to happen. It's going to get better. So this is why we want outputs to have very low impedance, okay, or low resistance. And I haven't really told you what the word impedance means. It's kind of resistance to AC. It's a complex though, meaning a complex number. It's complex impedance. It has both a real and imaginary part, and we will get to that very, very quickly in the next lecture or two. Now look, our signal is all back to normal. Let's go up to 5 kilohertz and let's look at it. And again, it's not too bad. And now one thing that's starting to happen, notice how the top is starting to deform. The reason why is we're putting a load on the signal generator itself, and we're getting reflections, and we're distorting that. All right, but we've got this 10 ohms here, so that's pretty good. Now, let's, and again, if we go back to low frequencies, our signal will straighten back up. All right, but let's put the resistor back to 100 ohms, because that's just more realistic. 100 ohms, brown, black, red. All right, so we're going back to 100 ohms here. All right, and there it is. Okay, we've still got a 0.1 microfarad capacitor going to ground as our distributed capacitance. All right, and so that's what our signals look like. There's 2 kilohertz, 3 kilohertz, 4 kilohertz, 5 kilohertz, and and that's about it. So it survives up to like 5 kilohertz, and then it's just kind of starting to get useless. That's with the 0.1 microfarad. Now I want to show you an extreme case. What if we put a 1 microfarad? What if you try to drive something that has an enormous amount of capacitance? 1 microfarad. What's this going to look like? So here's a 1 microfarad capacitor. I'm going to put it in here, and watch how ugly this gets. So we're at 5 kilohertz. Look, we've got, nothing. We've just basically got, this DC with ripple on it, right? That's part of how you make a power supply. When a power supply has an AC signal, so we're putting in an AC signal, aren't we? But what are we getting out? We're getting out a DC signal that has some average, right? And we could scale this a little bit, and we could look at it. So right now we've got 1 volt per division, so 1, 2, 3. So we've got a kind of a DC average of 2.5 volts. So we just basically made a power supply. This is kind of how buck boost power supplies generate voltages. They oscillate and create an output. But that's not what our intention was here. All right, so let's go ahead and let's lower the frequency because we've got this huge capacitance. So let's go over to the signal generator. We're going to lower it, lower it. And we're at 1 kilohertz, and it's still bad. And now let's change the frequency here. Let's change the gain a little bit. All right, and we're going to lower. And 200 hertz, 100 hertz. At about 100 hertz, this is starting to look good again. There's still some curvature and still some charging. All right, and let's go down 90, 80, 50. At about 50 hertz, looks pretty good. So in other words, anything more than 50 hertz, you just can't send down this signal path, right, with these components. So if you have a 1 microfarad of capacitance, you can't send any signals down here. Now, if we had picofarads, we could go all the way up to a megahertz or so, and it was kind of okay, right? So the moral of the story is capacitance, resistance, and inductance matters, and it changes signals, and it turns square waves into a mess because of the charging and discharging. And then we'll also see inductive energizing and de-energizing. Probably in 2 more lectures. Next lecture we're going to do filters, and then I think we'll do inductors. So anyway, there's kind of what really is going on when you're sending signals, and that's why you want to have very little capacitance, very little resistance. You want to have low output impedance. When your outputs want to be able to have a lot of drive, and you want to drive them into very low capacitance. Otherwise, you're going to get these effects going on. So anyway, so that's it, and I will see you in the next lecture. Bye. All right, welcome back. We are on the next lecture, and last time we talked about RC charging and charging and discharging circuits. So if you take a look here at the screen, kind of just to refresh your memory, we had a capacitor, resistor, a voltage source. We switched it in to charge it, and then we switched it out to discharge it. So here would be the charging figure, here would be the discharging figure. Then we went through some of the math and we solved for this, and we kind of came up with a couple different equations. So we had one for charging, which is V equals VI times the quantity 1 minus E to the minus T over RC. RC is called the time constant of the circuit, or tau. And then we learned that at 1 RC, the circuit would be charged to 63%, and at 5 RC, the capacitor would be charged to like 99.999%. So whatever RC is 5 of those is how long it takes to charge. And then we learned, what else did we learn? We learned the curve looks like this, right? So it's this exponential curve. It's asymptotic, and it's asymptotic to whatever the input voltage is. It will never ever reach it until you get to infinity, right? But it will try and get very, very close, and at about 5 RC times. So here's 1 RC time, that's 63%. At 5 RC times, you're, for all intent purposes, you are fully charged. All right. Then we did the discharge, and the discharge was very, very simple. It's almost identical, except voltage equals the voltage in times e to the minus t over RC. So that one minus term goes away because we're just discharging. All right. So that was it, and that's what it kind of looked like, right? So the discharging. And then we talked about some transmission line stuff, and we actually kind of did the experiment that you see here in figure 325 here from the notes. You see that we put a square wave through, and we actually put it through something just like this, an R and a C. But we talked about it more in terms of, what if you have a signal line, it's got some capacitance on it, some resistance on it, and then it's going to deform these waveforms like this. All right. So we kind of saw that happening, but we didn't really have the language yet to talk about it because we really don't know about filters yet. And of course, there's all kinds of filters. There's RC filters, there's RL filters, there's RLC filters, there's active filters, there's passive filters. And the bottom line is filters filter signals of certain frequencies. So we're going to start talking about what's called the frequency domain instead of the time domain. So we've been talking about the time domain when we talk about a transient response. In other words, our functions are functions of t, of time. But that's only interesting at the very start and the very end of when a signal is processing through a bunch of blocks of circuitry. What we want to know is the continuous operation. So if we put a signal in that's some kind of AC signal, we're talking about AC signals here, not necessarily alternating current, but we're talking about small AC signals like audio or other information. When we're putting them through a system, say like it's voice, we know that voice goes from kind of like DC up to maybe 3 kilohertz is where the majority of a human's voice is, right? So maybe we know that, so we filter everything from say 6 kilohertz up. We want to filter out because we know that that's probably noise, right? So filters help us do those things. Now, I was going to jump into filters in this lecture, but I've decided instead of doing that, what I'd like to do is talk about inductors, and then I think instead of going into filters yet then, we need some language that we just don't have, and so I think we're going to start talking about phasors and complex impedance. So I think the plan is, and I might change my mind again, you can just fast forward to the next video and find out what I did. But I think what we're going to do is we're going to talk about, we're going to derive the energizing and de-energizing, which is similar to the charging and discharging of an LR or RL circuit in this lecture. Very similar to what we did with the RC stuff. Once we have that, then we're going to kind of segue into kind of AC systems where we're talking about signals in the frequency domain. All right, and to do that, we're going to learn a bit about phasor, what's called phasor math and phasor diagrams, and we're going to learn about reactance and complex impedance or impedance. And then I think then we'll be really ready to really understand what's going on with these filters a lot better. Because you can look right here on the screen and you see this little circuit right here, R and C. It creates a low pass filter. And the final math that describes that is just right here. Okay, and oops, and it's not rocket science. You can see it's fairly simple, and it says that V out equals V in, right? And these are the functions of time. V out is a function of time, is 1 plus quantity 2 pi f squared, so that f is frequency, r squared c squared, all to the 1/2, which means square root. And that's it. So that will tell you what the magnitude of the output signal is relative to the input signal. We could just use this math and go on our merry way for all of eternity, and in fact that's what you will do. Ultimately you'll never derive this again, but I don't like that we don't know where this is coming from exactly, so we are going to learn some stuff so that we can kind of know this a little bit better and understand where it's coming from a little bit better. Like I said, I like to do things at least one time so that you've seen it, you can say, I understand it, I've seen it, and then you can forget about it. And then you can come back to it if you ever need to. But if you just don't know things, then you just end up not knowing, everything, and you don't know how anything works. So, all right. So we're going to skip this right now, and we're going to go and talk about inductors. So I believe in the notes here, if we were to skip forward here, and we're going to talk about decibels. That's going to come in a moment here. Here's more of the RC stuff, and all this is in chapter 3 of my book here, high pass filters. We're going to skip this. We're going to come back to this, and let's see here if we even have, let's do a search on inductor and see if we can find that. There we go. So inductor circuits 3.3, and so this is what we're going to kind of skip to right now, and then we're going to go back. All right, so we've talked about inductors before, and so inductors, like capacitors, they store energy, except a capacitor stores energy via charge. So, well, not technically the charge, it's the electric field. So as a capacitor charges, charge accumulates on the 2 plates. We have a positive plate and a negative plate. And as that charge accumulates, an electric field is set up, and the actual energy is stored in the electric field. All right. Now, with an inductor, instead of charge accumulating, what happens is a current is set up, and once this current is set up inside of the inductor, a magnetic field is generated. The magnetic field is where the energy is stored. All right, so it's in the magnetic field in one case, and it's in the electric field in the other case. And so capacitors and inductors are analogs of each other, and they're super interesting because, each one of them kind of exposes magnetism, electromagnetism, and kind of shows it for its symmetry. And so what's interesting is when you have charge, right, separated by space, you have this electric field. Then when you have a moving charge, you generate a magnetic field. And so and then you take advantage of that in the inductor. So both of these are very similar, and all of their formulas that describe them are also very similar. So we're gonna get to that in a second. So here's the kind of model here. So we've got a coil. So here's an inductor coil, and we apply a voltage, and then a current is going to run through here. And then this current is going to generate a magnetic field. Flux is going to be generated. And the equation that models this is V equals L di dt. Okay, plus or minus a minus signal, all right? So, and we'll talk about that in just a second. So, inductance is measured in henries. We've talked about that before, named after Joseph Henry. And this law right here is called Faraday's law of induction. And I believe so I have it here. So if you go on Wikipedia, Faraday's law of induction, and we've talked about this before, and you can kind of read through this. It's very interesting. And at the end of the day, we get to something like this. And this is Faraday's law of induction. It says that an electromotive force equals minus d phi dt. And so this d phi here, or d phi sub b, this is magnetic flux. All right, this is magnetic flux. And we're going to see kind of how this relates to that other equation, which is V equals L di dt, all right, in just a second. But anyway, you can look at Faraday's law, and then Faraday's law is also, there's another law which kind of goes with it, which kind of describes where this minus sign comes from. And that's this right here, Lenz's law is shown by the negative sign. So Lenz's law, the direction of current induced in a conductor by a changing magnetic field due to Faraday's law of induction will be such that it creates a field that opposes the change that produced it. Say that 10 times really fast. All right, so all this means is Lenz's law, which is really just Faraday's law, or just a restatement of it, saying, you know, what's happening, where this minus sign is coming from. When you have an inductor, and we're going to draw this in a second, when you have an inductor and a magnetic field is generated and there's changing flux, there's going to be an EMF or a voltage generated in the other direction to oppose that. All right, and that's what capacitors and inductors do. They have what's called reactance. And reactance is like a resistance to current flow or voltage. All right, so both capacitor and inductor, the capacitor doesn't want voltage on it, the inductor doesn't want current through it, and in both cases, what happens is both of these devices push back. The capacitor pushes back charge, so it pushes back current, and the inductor pushes back voltage. All right, so anyway, we're going to hopefully look at some of these things here and kind of go through this stuff. So anyway, but you can take a look at Lenz's law, Faraday law, if you want to kind of read through this. All right, so what I want to do is, and let's see here what we have in the notes, and let's talk about series and parallel inductors, which we're not going to care about right now. All right, so what I'd like to do is let's just start, drawing some stuff here so we can kind of start to understand a little bit what is going on with inductors. All right, so first thing is, let's talk about what the symbol is for the inductor, right? So inductor. All right, so the symbol for the inductor is just a coil of wire typically, so you'll just see it drawn like that, you see it drawn like that. Real inductors can just literally be that. They can just literally be a coil of wire. Of course, it's got to be insulated. It just can be a coil of wire wrapped around itself. Or there can be a core in it, so for just like a transformer, and we've already talked about this stuff. So say if we had, let's use this gray here. Let's use the gray, and this can represent an iron core or a ferromagnetic material. All right, and so then if we have a wire, and this wire goes like this, and then comes, it's behind it, and then, okay, that's horrible. So this would go like this. I think this is right. Yeah. All right, so anyway, so this is wrapped around this piece of iron here, ferromagnetic material, and so you'll see inductors like that. That would be an iron core. If we get rid of that, then this is an air core inductor. All right, and again, inductors are measured in henries, and after Joseph Henry, and it's that Henry. And you're never going to see a 1 Henry inductor. That would be massive. So typically we're talking about millihenries or microhenries, milli or microhenries. Just like capacitors, we're usually talking about microfarads. All right. So, all right. Now let's let's make a circuit here. Actually, let's look at something else. Let's talk a little bit about flux and whatnot and what's kind of going on here. All right. So, a matter of fact, here, let me get move this over here for you guys. All right, and so let's talk about flux. All right, so let's see here. So when we have, let's say that we have a current, and we're going to have a current, and the current is going to go through just a wire. Let's just say we have a current going through a wire here. And matter of fact, let's draw this kind of like this. All right. So we have this current I going like this. And then what's going to happen is as this current I is flowing in this direction, uh, a, uh, a magnetic field, magnetic flux is going to be generated. All right, and it's going to be generated based on what's called the right-hand rule. And so if you were to take your right hand and you were to wrap it around this arrow in the direction that the current is flowing with your thumb, then your hand is curling around the direction the magnetic field gets set up in. So the magnetic field is kind of this circular field. It's kind of a curling field. So in this case, it would look like this. It would look like this. All right, so it would just get set up like that. Now, all right, so again, and again, you know, when you when you do this, it's like really easy to confuse yourself optically here. So let's make sure that we have this right here. All right, so we're gonna wrap our hand around this, and the current's gonna the field is going to go in the direction that we're curling our hand here. So let's be careful. So let's go like this. There we go. That's better. And like this, and like this. All right. So now if I curl my hand, I'm trying to get my hand in the camera here, curl my hand this way, that's right. All right, so point is that the right-hand rule tells you which way this magnetic field, these flux lines kind of rotate around. And also we can actually look at this, and again, if you go to Wikipedia, it's got a nice little page on this right-hand rule. You can read through this, and the right-hand rule has to do with a lot of different things. And one of the things is in magnetic fields, or the B field, that's the magnetic field, and you can see it right here. So again, where's my hand? I'm going like this, and in this figure here, you can see the current is flowing up, and the field is going like that, and that is what we're trying to depict here. Okay, so that's the direction that the flux goes. All right, and okay, so now let's try and draw an inductor here, and let's do something. So let's imagine that we have an inductor, all right, and then imagine that we're drawing the inductor, you know, in such a way that it's curling like this, and there's that, and then our current I is going like this, and our current I is coming out here like that. Now, if we were to look at this, and this was drawn really, really nicely and not horrible like this, what this would really look like if we were to cut a cross section across it, right? What would it look like? It would look something like this. We would, you know, start off here, and then there's our first wire, and then we would basically see the coils. And here's each cross section of coil, right? And they could be touching each other as long as they're insulated. All right, and then we're coming out of here, right? And I'm not even going to try and think about where the wire would end up being and all that. All right, and then here would be the other side of the cross section, right? So this is a cross section. So, all right, so this is a cross section. So we have all these coils of wire, kind of a coil in space, and it's a cross section, or we could have wrapped it around something. So for example, if this was wrapped around a rod, all right, this would be, you know, you would call this a solenoid, right? So if it was wrapped around a rod, so that would be here, like this, and it would be wrapped around like that. Okay, and then now the convention is if the wire is going into the paper, so in 3D, if we're looking at this page here or this screencast, if it's going in, you draw it with an X like that. So there's an X in each one of these. So that means it's going into the paper. So so current, the wire is going into the paper, so current is flowing in the direction in 3D going in, and then it's going to have to come out, and then the coming out symbol is a little dot. All right, and I hope I have that the right way. It's one way or the other, but I think X goes in. And I used to have a mnemonic to remember, like X marks the spot where you dig. I think that's what I used to make up. So you would have to dig in, so that means it should go in. Who knows? Look it up, see if I'm right. Okay, so now let's now let's figure out. So and these two things, the green things, these are just the wires, right? And maybe we can let's draw those a little bit, kind of draw them a little bit different here. And again, I don't want to, I'll probably make a mistake if I do this. I don't really want to do this, but this one's kind of going in. So yeah, I mean, I think we could say on the very first, we could say this one's coming in like this one's coming out like this. Yeah, I think I'm comfortable with that, I think. If I made a mistake, I'm sure someone will tell me. All right, so here is our current I. Here's our current I, and it's going this way, and then it's coming in, and then here it is coming out. Here's our current I, and it's going that way. And then this is a cross section of our coil. All right, so is that cool? Everybody is following. All right, so so now all I want to kind of show you is what does the magnetic field look like here? So if we're running this current, and let's just say that the current is stable and it's not been doing anything for this, what I'm going to talk about right now. So, so there's going to be a magnetic field generated here, right? Because there's a magnetic field right here you can see, and let's use the same color. So it's going to be, so the magnetic field, let's again, you know, it's really easy to get confused here with clockwise and counterclockwise when you're drawing things in 3D that are 2D. All right, so if we use our right hand, the field curls, you know, always curls like this. And as long as our thumb is pointing in the direction of the current, it's curling towards us with our right hand. Okay, right? So if we go over here, so this the currents are going in, right? So if I take my right hand and I kind of put it up like this, and my thumb is pointing into the screen, right, into the screen, and I twist, right? So then the field is going clockwise. All right, field is going clockwise. All right, so here's the field, and it's going clockwise like that. Okay, that's good. That, and of course, this one's the same way. This one's going clockwise. All right, this one's going clockwise. Thank goodness we figured this out. This one's going clockwise, and this one's going clockwise. And of course, they're circles, right? Circles. This one's going clockwise, and this one's going clockwise. And in 3D, this thing is all wrapped around, so it's creating this three-dimensional toroid, right? Each one of these is a three-dimensional toroidal field, right? Now, these currents are coming out. So these guys are all coming out of us, right? Coming out towards us, right? Since they're coming out towards us, clearly the field is going to be in the other direction, but let's just use our right hand rule. So let's take our hand. So my thumb here is pointing towards me, and again, I'm going to wrap it around, and now it's going counterclockwise. Okay, so the field is going counterclockwise. All right, so let me draw this counterclockwise. There it is. There's the field direction. Counterclockwise. There's the field direction. Notice what's happening with these arrows. They're all going in the same direction, right? So this is kind of all working out, and as it should. So that's, you know, thank goodness. And then here's the next one and the last one. Okay. So we have all these arrows going in one direction. So, and let's just use, let's use this color. So now what's happening is all these fields kind of add up, and the whole thing kind of makes this beautiful 3D field where you're going to see field lines going like this, these magnetic field lines, and then like this, and then kind of there's another one in here going like this, and then and so forth. And then these things, you know, all wrap around this, right? They all wrap around this, each one of them. So the field is going from this side to this side. That's what we call north and south over here. This would be south. So that's the north, and that would be the south pole, okay, of the magnetic field. And this is how you make an electromagnet, right? You take a piece of metal or iron or something, you wrap a coil around it, you run a current through it, and boom, you've got a magnetic field. Now, so let's look at one thing. So now let's add one thing. So this flux, all this flux here, right? So what does it equal? So flux equals the inductance L, right? So the inductance of the wire here, right? Times the current. And and then you can kind of, if you want to start coming up with formulas for inductors, you can actually figure out, you know, what's the inductance per winding, and then you could say, you know, it's Li times N for N windings and all that. But just in general, we're just going to stick with flux equals inductance times current. So however much in current you're going to run in there, that's going to definitely be proportional to the flux, and how much flux is the constant of proportionality is L. All right, so that right there is what's going on here. Now, let's see if we can finagle this a little bit. So this is kind of our first modeling equation, right? So this one is analogous. Okay, so let's come over here, and we're going to put inductor here, and then we're going to put capacitor. Inductor here, and then let's put capacitor over here, just so you can see some differences. Now, the capacitor, when we have our capacitor, we have an equation very, very similar to this. And let's see, I want to put it in this form right here. So we have flux, which is magnetic field flux. So this is magnetic field flux equals the inductance times the current. But in a capacitor, we have a very similar equation, which is charge, right? Q equals capacitance divided by voltage. And so now we're just going to start to see all this symmetry start happening here, right? Okay, so all right, so we've got this right here. And so one thing we could say is if we start wanting to kind of figure out different formulas for things, we could do something. We could take the derivative of both sides. Let's take the derivative of both sides. So, and again, all the derivative means is the slope of both sides. So we're going to take the rate change of phi, or the flux with respect to time, which will then force us to take the rate change of current with respect to time. We have to do the same thing to both sides. Okay, so let's do that. And so now something interesting is going to happen here. Oops, that's a slightly different color, eh? All right, so we're going to take d phi with respect to time, and that's going to equal L di dt. Okay, so L di dt. So this is interesting right here. All right, now let's go over to the capacitor, and now remember we learned this. Let's do this. Let's do the same thing. Let's take the derivative of both of these sides right here. We can do that, right? So and then before we do, let's see here. If I want to do this like this. Oops. I made a mistake when I wrote this. This should be just C times V. Sorry about that. Okay, so this should be C times V. Okay, and now if we do the same kind of derivative operation of both sides, then we're going to get dq dt, right? equals C, which is a constant, dv dt. Okay, and hopefully we can see what's going on over here. All right, and now, all right, so now we've got, okay, and this is bad. Let's make sure we can read what this is. Okay, that is dq. Okay. All right, so on the left here we have d phi dt equals L di dt, and then we have dq dt equals C dv dt. Well, we already learned that this, we already know that dq dt, what's that? That's just current, the rate change of charge per unit time, right? That's coulombs per second, so that's just current, right? So that just equals I, right? So I equals C dv dt, right? And we know that one for the capacitor. All right, now over here, we're not quite sure what's going on over here, but I can tell you, so we have this L di dt, d phi dt, so the rate change of flux per unit time, this is actually voltage. All right, so now if we go look here, and if we go look here and we go back to Faraday's law, and we can kind of take a look here and sneak down here. So see this right here? So this is just electromotive force equals minus d phi dt, all right? So, and there might even be, maybe not, no. And then if we look at Lenz's law, there might even be a final, no. Okay, so, but there's a minus sign, right? So we need a minus sign here. And all the minus sign really does is it just reminds us that this voltage acts in the opposite way to impede the current that's flowing in the inductor. So that's all that means. So you got to be careful, DIDT. You got to be careful when you're using this and this minus sign. All right, you got to be careful, or you'll mess it up. I do it all the time. All right, so there we go. So there is our modeling equation. So V equals minus L di dt. And then, of course, we already knew this one. I equals C dv dt. Let's write that down one more time over here. So I equals C dv dt for the capacitor, right? And so there are two equations that describe everything. We already knew this one, but I wanted you to see the symmetry here. So it's voltage and current, and now it's current and voltage. It's inductance and capacitance. You know, very, very cool. All right, so that's kind of an inductor. That's kind of you know, what's happening with the flux and how that's computed. And then of course flux equals Li. Remember that one. Flux equals Li. All right. And then let's talk about one more thing. And then I think what we're going to do is we're going to stop this lecture and we're going to start up another one because we're going to need the full hour to go through the derivation of the energizing and de-energizing of the inductor. So let's just talk about one more thing here on this figure. So what I want to talk about is this, and just so that you kind of have a feel for it. So let's find a color. All right. So what I want to do is, you know what? Let's just erase all this. This is too messy. So let's get our inductor again. And what I want to show you is this. So here's our inductor. Huh, that one wasn't too bad, huh? So this has got an inductance cell, and then I'm going to run a current through it. So we're going to run this current through it. We're going to call that I. Same current's going to come out here. We're going to call that I. And as the current goes through the inductor, right? All right, let's erase that. As it does that, it's going to create the magnetic field, right? It's going to create the magnetic field. And I'm going to draw that magnetic field, however. And all these field lines are going to kind of, you know, do this kind of thing. And in fact, they're going to kind of go like this in this direction, right? We just looked at that like this and like this and like this. So this field is going to get set up inside of here. All right. So now let's look at what's happening. So what's our equation? Our equation says, what does our equation say? It says voltage equals minus L di dt. All right. So just kind of keep that in mind for a second. And so what happens is this. So as the current flows through here, a magnetic field starts to get generated. All right, so flux is changing. So we've got changing flux. All right, so as there's this current that flows through here, we've got a changing flux. As we've got a changing flux, then this Faraday law says, okay, well, we've got a changing flux. Then what's going to happen is we're going to generate a current in the opposite direction because there's changing flux, and a current will be generated in this direction. And we can just call this, I star or something. Or actually, we can call that I phi because it's the current that's being generated due to the changing flux. So as you push a current through the inductor, the self-inductance itself, right, the inductor, there's flux being generated. Because there's flux being generated, then there's a current being generated in the opposite direction to oppose it. This is where this impedance or reactance comes from in an inductor, just like with a capacitor. And that's why so now there's an EMF or a voltage, and that's where this negative sign is coming from. This voltage is generated in the opposite direction, which is going to push a current back in this direction. All right. So as you keep pushing current in this way, it keeps fighting back in this way. How much does it fight back? Well, it fights back at the rate of the derivative or the rate of change of the current you're pushing into it with respect to time. But at infinity, as time goes forward and forward and forward, so as time goes this way towards infinity, then di dt, there's no more change here, right? And since there's no more change, then this goes to zero and there's no more current in the opposite direction. So we don't have that reverse electromotive force, it's called. All right, so that's kind of what goes on. So that's where the impedance, or that's where what's called reactance, that's the reactance of the inductor. Now, the exact same thing happens with the capacitor, and we didn't exactly talk about this, but let's talk about this a little bit right now. So again, say we have a circuit here, and we've got a capacitor here, okay, and then let's say that we apply a voltage to this. Let's talk about voltage in this case, right? So we'll talk about voltage with capacitors. We apply some voltage, plus to minus like this, and plus to minus like this. Okay, so what happens here is, the second that we apply this voltage, what starts to happen is we start to get current here, and then a charge starts accumulating plus on this side, and negative charge starts accumulating on this side. Okay. However, as more positive charge accumulates on this side, well, here's positive charge, here's positive current coming this way, right? This positive current coming this way is impeded by the positive charge here, because remember, like charges repel. So the more charge that you accumulate on here, we get a little bit more, and then we get a little bit more here, right? Now it impedes it even more. So now this current here keeps getting less and less and less. So if we were to draw this and represent it as a length, we could say that the length of this little arrow, so the length of this gets smaller. Now over time, right, more time happens, we get a little bit more charge on here, right, and then we get a little bit more charge on here. And then what happens? Now it's being impeded even more. Look at all this positive charge, and we're trying to put more positive charge. Well, we're just not going to be able to put much. So again, this keeps decreasing, 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 decreasing until finally the plates are completely charged with as much charge, and we're in kind of an equilibrium state. Now we know that this never happens until infinity in reality. Why? Because we know what the charging equation is. What's the charging equation? Can we do we know that? That's so the charging equation is V, we'll call it VC, all right, if we call this VC, and let's just call this VI. So VC equals VI times 1 minus e to the minus t over RC. And in this case, we don't really have an R, we just have this voltage. So this would instantaneously charge if things were theoretically perfect, but they're not. There's always going to be some little tiny RC here, so this will take some time to charge up. But the point is, that's the equation there, and no matter what, this term will never, ever, ever, ever go to absolute zero until t is at infinity. So, and anyway, but at 5 RC times, it's charged as far as we're concerned. The point is that we had this current, and over time, the current got smaller and smaller and smaller until the current was zero, right? So we started off with a big current, and then the current dropped down, right? So what if we look at the curve here? So if we look at the curve, and this is time here, time t, all right? And we're looking at, let's say that in this case, we're looking at I, current and amps, all right? And this is for the capacitor circuit, right? So what happens is the second you connect this thing up and you connect it to this VI, you get this, huge rush of current, instantaneous rush of current. It goes, zhoosh, that's that inrush current. Then what happens is as the thing charges, it does this. So the current does this as the voltage does this. And what's the voltage doing? The voltage is doing this. The voltage is doing this, right? So as the voltage goes up, as the charge accumulates, then the current is going down. The inductor does the same kind of thing. So let's look at that. Here, where's the inductor? The inductor is up here. So we've got the inductor. So right now nothing's happening with the inductor. All right. So the moment that we apply a current to the inductor, all right. So the moment that we apply a current to the inductor, what happens? All right. So let's talk about that now. All right. So the second that we apply a current to the inductor, and let's draw it right here. So here's our curve, all right, and here's time, all right. The second that we draw or apply a current to the inductor, that means that the rate of change, this di dt, is absolute maximum, right? So the moment that we try and energize this inductor, right, the moment that there's a voltage, which is going to induce a current, the rate change of di dt is at its absolute maximum, right? So the slope of that di dt is at its absolute maximum. And then times L, that's going to be kind of the magnitude of it. So what's going to happen is at time equals 0, we have no current. And what color do we have here? Let's get a good color. All right. So, and then we're going to put I up top here. And then here's time t. Let's put a better E on there. Put a T on here. Okay. All right. Okay. So at time t equals 0, so down here at time t equals 0, right, we apply a voltage which is going to induce this current. And at this very moment right here, di dt is its absolute maximum. So it pushes back against us. It pushes back against us, right? And so we've got 0 current flowing. And then the current starts rising, 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 rising until it asymptotically hits here. And this asymptotic level, of course, is based on whatever the resistance is in the circuit, and we're going to talk about this when we get there. So I'm just kind of showing you kind of what's happening intuitively, but we're going to go through the charging and discharging. It's very similar to the capacitor. So this is what's going to happen. Then at time when t goes to infinity, the rate change of current is now gone to 0. So there's no more rate change of current, so there's no more back EMF. So then this thing just sits at whatever level it can support based on its internal resistance and all that. And that's what this kind of asymptote here is. This asymptotic level here will be that. All right. Now, the interesting thing is when the second that you turn this on, what we're really doing is we're applying a voltage to it, right? And we apply a voltage to it. And if we draw voltage, like say in blue. So the second that we do this, we're going to get a voltage, and this voltage is going to be at absolute maximum. All right, and the reason it's going to be at maximum because there's this inductor right now. There's no current flowing through it. Right, the current is 0. Because the current's 0. Right, there's like this infinite impedance as far as the voltage is concerned, so the whole voltage would drop over this. So the voltage jumps up immediately to its maximum value, which is just simply whatever the input voltage is, and that'll be like a VI. And then over time, it decays down. And the reason why it decays down is because once there's a bunch of current flowing inside of here, so there's a bunch of current, this thing is like a dead short, right? Now there's no longer a voltage drop, so again, the voltage goes like this. So the interesting thing is so the green one, let's do this. So the green one is current, the purple one is voltage, then over here, the blue one here is voltage, and then this purple one is the current. And then notice they're opposites, right? They're opposites. And again, that shows the analogness of the capacitor and inductor. All right. So anyway, So that was kind of the last thing. So the takeaway of what we're just talking about is the whole concept of inductive reactance and capacitive reactance. And these things, what they do is they impede the current and the voltage. These devices do not want to change, right? So the uh, the capacitor, right? Uh, as you put more charge on it, it doesn't want you to put more charge on it, right? The inductor, as you push current through it, it doesn't want you to push current through it, all right? And so this is where this idea of impedance comes from. Now, one interesting thing is once the capacitor is current's flowing through it and it's come to a steady state, there's this magnetic field around it. Remember, the energy is stored in the magnetic field, and in the capacitor, the energy is stored in the electric field due to the charges on the plates, right? So keep that in mind. Uh, but there's one little detail. On a capacitor, if you remove the power source, the charge stays on the plates. On the inductor, uh, the magnetic field will not. And so one little tidbit here to think about is, and this is kind of interesting. So let's say that we have a circuit, all right, and let's say that there's some resistance here, R, and then let's say there's some power source, plus to minus, right, some V, and this is some R, all right, and I'm just going to connect this up here like this to our little inductor, okay. We're going to turn this on, and this is going to come to a steady state. This is going to energize this. We're going to get our field, right? We're going to get our field, and we're going to get our magnetic field setting up here, right? And so this energy is going to be stored inside of this magnetic field, right? Now, the current I is going to come to a steady state in the circuit. So this current I, which is going to be going around like that, right? That's I. It's going to come to a steady state, and that steady state is going to act as if the inductor is a complete short. So what's I going to equal? I is going to have to equal V over R. In this case, I equals V over R, right? So the inductor becomes a short over time, right? At infinity, it becomes a dead short, and then the final current is just V over R. But with the capacitor, when you undo the two connectors or contacts from it, the charge will stay on the capacitor plates, right? The reason why is because the air itself has so much resistance. There's no path for the charge to go anywhere, right? So typically, unless you have like billions or millions of volts on the capacitor, then it'll find a way. But the charge will stay on the capacitor. But with the inductor, if we remove and cut these lines, right, the inductor can't maintain this magnetic field. There's no current running through it, right? So what happens is, in reality, all right, and this is a little bit tricky, the moment you break one of these lines, whichever one breaks first, right, what's going to happen is you're going to see, and I'll draw it in red, well, not red, let's use yellow. There's going to be an arcing occurring here. And the reason why is because this inductor wants to maintain the current that's flowing in it, right? And because it wants to maintain the current that's flowing in it, right, it's going to induce a huge voltage to maintain that. And that's why, so what'll happen is if you have a bunch of power going through an inductor and you switch it, you try and switch it off, you're going to get this thing called this inductive kick, and you're going to get a huge voltage generated here, and it'll arc, from one point to the other. And then as the field collapses, because that field is going to collapse. And so the moment that you start, if you looked at atomically under an atomic microscope and you started pulling those contacts apart somehow, the moment you did that, the moment there was, the resistance started decreasing, right? Or excuse me, the impedance started increasing as you pulled the conductor away, this thing would start reacting. And it would say, whoa, 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 whoa. Because what's happening is you're changing the amount of resistance in the circuit. The current is changing, right? It's because you're increasing the impedance. You're making less of a path as you're pulling the two wires apart. So what's happening? The current is changing. If the current's changing, d-I-dt, L-d-I-dt, and we're going to get a voltage. And you're doing that so fast and happens so quick, this thing goes shoo, and it goes to hundreds or thousands of volts. Could go to millions of volts. That's where that inductive kick goes. So you got to be careful with inductors, and that's actually the basis of what are called boost converters, or if you want to amplify voltages for power supplies. They use inductors to do that. All right. So anyway, so that's a good place to stop. And then now we're going to go do, in the next lecture, we are going to do the, not the transient response. No, we are going to do the transient response. We're going to do the transient response of the inductor for charging and discharging and work through the math of that. And then after that, then we're going to talk about phasors and complex impedance and all that in the next lecture. And then we're going to talk about filters. And I think that is the order that we need to do this in. I think everybody will be happy. So hopefully you learned a little bit in this lecture, and I will see you in the next one. Bye. All right, well, welcome back, and we are on the next lecture. So we have been talking about inductors, and we are now going to follow up on what we discussed last time, and we're going to do the charging and discharging of the inductor, which is more correctly called energizing and de-energizing, because we're talking about magnetic fields and not charge. However, before we get into that, there's something that I wanted to take a look with you, at with you, and that has to do with the simulation. So I was trying to figure out a place to kind of bring this in so we could talk about it, and I think we have a good place now. So let's take a little sidebar here, and let's talk about this. So what do we know about the charging and discharging stuff? So right now for RC circuits, right? So for RC circuits, we know if we have something like this, we've got plus and a minus, we'll call this Vs. And if we have a resistor right here, and if we have a capacitor right here, okay. And then if we, and then, you know, we talked about this, of course, if we go ahead here and we've got like a little switch here, and let's say, actually, let's kind of do this. Let's kind of make this usable. So we'll put this in here like that. All right, so now imagine if we had, and let's put 3 little points here. Okay, and then let's put our little switch. How about we make our little switch red? All right, okay. So there's our little switch, and then what if we name these? We'll name these little nodes 0, 1, 2, and 3. And then, of course, let's name these components. So this is R, this is C. All right. So the two equations that we know so far are the charging and discharging. So check this out. So when this switch is in position 2 here, nothing happens. It's just floating in the air, and the circuit is completely detached. All right. So it's discharged, detached, nothing's happening. If we move the switch up to position 1, then we go into charging mode. All right, and similarly, if we move it into position 3 down here, we go into discharging mode, right? So we disconnect the battery, and then whatever's in the capacitor will discharge. So this is kind of like a little circuit that you can make, and you can try some of this stuff out yourself. Now, one thing to be aware of is when you have a mechanical switch and you have power, any kind of circuit, the moment that that switch gets closer and closer. So if we look at the switch, and let's kind of abstract the switch to something like they might be 2 spheres, or they could be 2 rectangular mechanical components. And typically, what's going to happen is these 2 things are going to move together, right? And they're going to make contact somehow, or these things are going to move together and make contact somehow. So this distance inside of here, right? This distance inside of here, same thing. As a function of time, that distance keeps getting smaller right at the moment that you're going to close that switch. So this goes from maybe at its steady state, it's 2 to 5 millimeters. 2 to 5 millimeters, 2 millimeters to 5 millimeters might be that distance right there. And then as you close that switch, you flip it with your finger. So whatever the velocity of if you were to compute what the velocity is based on the force of your finger and want to do all that kind of crazy math, you know, at some point, these things are going to get like atomically close to each other, right? So they're just going to get right on top of each other, like we're talking about. And a matter of fact, let's draw that, and we'll draw that in white. So they're going to get atomically close to each other. Oops, where's our white? And until they're just about to touch. And then this distance in between here is next to nothing, right? Okay, so when that actually happens, when these things or these spheres up here representing the contacts are just about to make contact, right? What actually happens is the switch, uh, so charge might jump across the gap depending on the voltage, right, of each side. So you could have some charge jumping across and you could start to get some conductivity. Then when the switch actually makes contact, right, if you were to look at this with high-speed photography and this and that, the switch actually, you know, vibrates. There's friction occurring and all kinds of stuff. So what actually happens is if we were to look, and I'm going to exaggerate this, but this is true. So if we were to look at and say this is time here, time t here, and if we were to say that this vertical axis is resistance, okay, and let's say that this is zero resistance, so they've got perfect contact, and then this is infinite resistance right here when they're completely open. It's actually not infinite, it does have some value, but it's so high because of the air gap, and you could compute what the resistance is of open air at a certain temperature, at a certain pressure, and you know, depending on where you are in the world, you could actually compute that. But let's just call it many, 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 you know, millions, billions of ohms, probably hundreds of millions of ohms. All right, now, so here's time zero right here. So there's time zero. All right, so time zero, let's say that the switch is, let's say that the switch is open. So it's up here, and its resistance as far as the circuit's concerned is near infinite. Now, let's say here at time, say, just to make up a number, we'll say at 1 second. At 1 second, you decide to close this switch. So what happens is, so it's sitting here, it's sitting here, it's sitting here, and then right at this point, this 1 second point, and let's see if we can draw this. It is impressively hard to draw straight lines and everything with these tablets. At least for me it is, because I guess there's not enough room here. All right, so at the moment that we close this switch, what's going to start happening is this resistance is going to immediately kind of go down, right? It's going to jump down. And then it's going to kind of jump up and jump down and jump up and do all this. And then finally it's going to, you know, go like that, and then it's going to settle down to, you know, the 0 ohms or whatever the resistance is of these two conductors, whatever their material are and all that. In any case, all this bumping around, right, is called, you know, it's called bouncing. Bouncing. That's an O. So it's called bouncing. And so what's happening is this is the mechanical contact making contact. It's also potential shorting and unshorting as there's voltage. And because there's voltage, this thing becomes a capacitor, right? There's two metal plates separated by a distance. It becomes a capacitor. It gets closer and closer. All of a sudden, there's an arc. And so all this weirdness goes on for some time. And this time right here typically is in and, you know, I'd have to look this up, and it also depends on a lot of factors and all that. But on average, you're talking about milliseconds to microseconds, right? So we're talking about microseconds to milliseconds. So it could be pretty long, actually. It could be pretty long. You know, milliseconds pretty long. Microseconds is not too long. But anyway, if you make an assumption about what's going on in this little region here, you would be wrong. So this actually happens. So whenever we have a switch, this is what really happens. This is you know, a distortion of reality from our ideal models that we've been using. So keep that in mind so that when we're, you know, doing these kind of experiments, remember we're making these ideal models, but this is what really happens. And so weird things can happen when you close switches because they're bouncing. All right, and then you might hear the word debouncing. Debouncing, the whole idea of that is to get rid of this. So in a debounce, so you have a debounce circuit or switch, what happens is this, you get this kind of thing happening. Boop, like that. You get this nice, clean, this is what happens. So a filter filters this, and it keeps it, and then drops it down. All right, okay, so so let's go back to the circuit here and take a look at what I wanted to talk about. So we've got this circuit here. We've got R, we've got C, and then we know what the charging equations are. All right. So I wonder if I can make that bigger easily without too much work. Let's, you know what? Let's just leave most of this. These paint programs, as we're doing this in real time, this one is quirky. I use, of course, like Photoshop and whatnot for my normal drawing, and this has just got a much smoother tablet interface, so that's why I like it. And you can go kind of full screen with it if you want as well. Anyway, all right, so we've got this situation right here in our circuit. So when we go to position 1, right, then we're getting a charging that's going like this, right? And this is the current I, and it's charging up. And then if we wanted to monitor this voltage, this V sub C, we could monitor it right there, right? And so there would be the charging. And in that case, what do we know? We know that the charging looks like this. Goes, and let's use a different color. So this is time here, time t, and this is voltage up here on this axis here, and it looks something like this. All right. And what does this thing charge up to? It charges up to Vs, right? That's as much as it can charge up to. Charges up to Vs right there, the source voltage, right? And so this is V sub C, right? So this is the capacitor voltage. The most it can charge up to is V sub S. And we know, what's another thing we know? We know that about at 63, and for once I'm going to draw this semi-correct. So we know here at time equals RC, right? And remember, that's the RC time constant, so that's just 1 RC time right there. We know that this point would be 0.63% of V sub S. V sub S. That's what that point is. And then we know over here, right? 1, 2, 3, 4, 5 at 5 RC times up here, we're 99.9999, many nines, percent charged. So for all intent purposes, 5 RC times is the entire thing. All right, so what is the equation for this right here? What's the equation for this? So V sub C equals, what does it equal? It equals the source voltage, the charging voltage, 1 minus E to the minus T over RC. All right, and then the discharging equation. So if we were to flip the switch to position 3, now the charge capacitor, which is all charged, plus, 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 minus, 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 it's going to, this current's going to flip around now. So now instead of the current flowing this way, the current's going to flow this way, and it's going to discharge, right? And what's the discharging equation? We'll just do that one yellow. So this is charge here. We could say this is charge. All right, and then discharging, V sub C again equals, but this time it's simpler. It's a V sub S E to the minus T over RC, where RC is that RC time constant again, and then this is discharge. Okay. All right, so those are our two modeling equations for the RC circuit. All right, so what I wanted to do is I wanted to use a tool to show you how we can model this and actually see it. Now we could do this over on the bench, but you know, setting this up when we're talking about times that are so small, we're talking about milliseconds and microseconds, and then all the other things that are going on with the circuit and all the parasitic things about with inductance and so forth. It's just hard, and then we have to get it on the oscilloscope. We could do it, but it just is not going to be as fun as what we're going to do right now. So what I want to look at right now is I want to take a little quick break here. And what I want you to do is, I want you to, if you've never heard of, I want you to go and download MATLAB. All right, so MATLAB is made by a company called MathWorks. And if you've been to college or you're a professional engineer, if you're a professional engineer, you probably aren't taking this class, well, professional electrical engineer or electrical engineer. But if maybe you did it in physics or something like that, or chemistry, or I don't know, in computer science, if you would ever use math, well, you would use MathWorks, but a lot of times they don't introduce it in computer science courses. They just teach Java and HTML. Anyway, so MATLAB is awesome. MATLAB stands for Matrix Laboratory, and it was designed in the 70s. And I wonder if I have, you can read about it. It's actually an interesting story, MATLAB Wikipedia. And so back a long, long time ago in a galaxy far, far away, uh, and actually it's more than 32 years ago, back in the 70s, and I know the story a little bit if we scroll through here, yeah. So University of New Mexico started developing MATLAB in the 70s. And the whole idea of this is back then, in the 70s, you're kind of programming on mainframes and mini computers, and the language of choice was Fortran, which is a formula translator. And it's very much like BASIC. Actually, I learned to program computers by reading my dad's old Fortran books, and I didn't have a computer, but I would read his Fortran books, and I learned to program by just reading them. And then when I finally got my hands on a TRS-80, I could pick up BASIC very, very quickly. So they used to have to program in Fortran, and they would use these math libraries, right? So he wanted to make something that was easier, and he worked on it for a long time, and you can read about it all here. Anyway, the result is this program called MATLAB, which came out in the 80s, and initial release 1984, 32 years ago. And this program is unbelievable. MATLAB can do just about anything you need to do mathematically, end of story. And so it's a very powerful tool, and everybody uses it. Chemists, physicists, biologists, everybody uses it in a professional sense. Now, a lot of times in school, depending on where you go, you may not use it in your curriculum, which is kind of a bummer because it is really cool. And if you've used it before, you may have forgotten how to use it and all that. I know I do. I play with it, then I forget how to use it because I don't need to do whatever I needed to do with it, and then that's that. But so what it allows you to do is do all kinds of simulations, symbolic mathematics, and do computations that are very complex that you'd have to write programs for. And it allows us to do things like plotting those curves. So MATLAB, if you just go to the website, and I believe and you're going to probably have to do a lot of stuff here, but I've already downloaded. Yeah, so you just give it your email. So if you go to the main website and you look here, trial software, you can click that and type in your email and so on and so forth. So if we say, John Doe at hotmail.com, and all right, so then it's going to ask you to create an account and so on and so forth. At some point, it'll let you download a 30-day trial, and it'll ask you what modules you want. Now, if you're a student, you can get this program for, I think it's like $150 or $200, something ridiculous. But MATLAB normally is thousands of dollars, thousands and thousands of dollars. So if you are a student, so it's even worth it. If you want MATLAB, go take a class for $50 at a junior college, become a student, and then get MATLAB, right? But for us, I want you to download this and get the demo version, the trial version, which is fully functional, because we're going to play with it. So you can pause the video right now if you want, go download it, go install it, or you can just watch this and do it later. We're not going to do a whole lot. I'm not going to teach you MATLAB. That's a whole class in itself, but I'm just going to show you its use, which is cool. All right, so let's close this. Okay, so let's go. I've already launched MATLAB. Now, one thing about this piece of software, it is massive, massive, massive. So launching it actually takes a couple minutes on my computer, and this is a pretty powerful computer. So I'm not sure what it's doing, but it's doing something. It's probably talking to the server a lot. All right, so what do we have here? So MATLAB has got all these, tabs, and it's like a programming IDE for mathematics, and you program it in a C-like language, and this which is this MATLAB language. And then you can see here I've got a script up here that I've written called RC charging 01.m, M for MATLAB script. And you can see it's pretty straightforward here. R equals 10,000, C equals this, VS. So this is kind of the circuit, right? And then down here we have this command window, which is emphasizing this is a trial, right? And you can do things like you can say, A equals 100, and it says fine. B equals 200, it says great. And then I say, hey, what's A times B? And it tells me. So there's immediate mode you can just do mathematics in, and there's a massive library and anything you want to do. All right, so and let's see, home. Oops. Okay, so so now this program right here, this represents our charging model. So let's take a look here. So here's the equation that we want to kind of model. So we want VC, which is the voltage on the capacitor, equals the source voltage, which is the thing that we're charging this with. This could be a function of time, but in this case, we're just going to say it's a static number, like a 9 volt, 5 volt, 12 volt battery. And then the equation is 1 minus e to the minus t over RC, and t is time. So this is going to be our independent variable, and then everything else is going to depend on time. And then R and C are, of course, constants. All right, so we go back to MATLAB. All right, and so I've written this little program right here, and you can see we've got R equals 10,000, we've got C equals 1 microfarad, 1 e to the minus 6 in scientific notation, and then I've got Vs equals 5 volts, then I've got T, okay, and this is a range. So what this does is this is going to create a range that T traverses. I want T to start off at 0. I want it to increment by 0.1 times 10 to the minus 3. So this is a 0.1 millisecond. I want it to go for 100 milliseconds. So that's going to be like an axis. Then V out, which is like VC in our drawing, is the equation. It's Vs times 1 minus x, that's e to something, minus t over RC, all right? Then this kind of defines this function right here, says I want you to create, we're going to do a plot. So this kind of says what the axis, what its dimensions are and what its units are and all that. Then we say, I want you to plot t against v0. So t is this time, v0 is the function. So it's going to basically put t on the bottom axis and then plug the values into t into the function for v0 and plot it. This hold on, this says don't erase anything. And then I tell it, at 1 RC time constant, recompute, reevaluate what V is, and then put a little red marker there of diameter 15. Then I say keep the hold on, and then I say at 5 RC times, take that value and then evaluate it and compute where that is and put a green marker and make it 25 pixels in diameter. So the end result of this is we should see a curve, and the curve should look just like this. And at 1 RC time, right here, we should see a red marker. And then at 5 RC times, which is here, we should see a bigger green marker. All right, that is what we're going for. So let's see what we see. So we run this, we just click run, and like any programming language, you can do all kinds of things. You can debug in single step and all that. So we're going to run it. Here we go. And sure enough, there it is. And so how cool is that? So the bottom is time, and here's the voltage, and you can see that at 1 RC time, the voltage is, it looks like it's about 3.2. And if we were to take the calculator and say 0.63% times 5 volts, that's our total voltage, equals 3.15. Yep, about 3.2. All right. And so anyway, there it is. Now, can we modify this and see what changes here? Sure. So let's go ahead and let's really increase the capacitance. Let's make it 100 microfarads. We'll save that. All right, and then we can just go run it again. All right, and now, so what's happened is the 100 microfarad capacitor is so big, we need a lot more time for it to charge. Okay, so we need a lot more time for it to charge. So let's go up here and we'll make this, say, 10,000. All right, and now we'll run it, and there we go. So again, there we go. And now the scale, this is a time here in seconds. The scale, you can see the scale has changed. All right. So that's it. And these curves are, and because this thing kind of auto normalizes the axes, you kind of always get something. It's smart enough to kind of put it there. So since it does that, it always kind of looks the same. All right. So anyway, this script, of course, is in the resources for this lecture, so you can try it out and play with it. And like I said, if you know any kind of C-based language or even BASIC, you'll be able to pick this up very quickly and kind of get things done and find scripts online that kind of do what you want to do, and you kind of copy and fudge them and get them to do what you want to do without knowing the whole language. But where its real power comes in is with matrix operations. So you can do all kinds of stuff. You can find the inverses of things. You can solve simultaneous equations. You do just anything you want. So it's like a big math engine. Okay. All right. So that's simulation. So this will help you. So if you, after you make a circuit and you kind of want to check it out, you can do it in MATLAB. And so here, all you have to do is change line 5. So if we wanted discharging, we would just get rid of the 1 minus and just it would be Vs x so on and so forth, right? And so you can do charging and discharging. The same thing, once we figure out the inductor, energizing, de-energizing, it's going to be almost identical to this equation, except instead of capacitance, it's inductance, and so on and so forth. So you can change it, and then you can get these things to plot very easily, and then see what your results are. And then you can look up all the graphic stuff and make it prettier and all that, obviously. All right, so I'm going to close this. It's probably using up half the resources of my computer. Okay, so so we're back to this, and so this is good. We're going to keep going. We're just going to keep rolling here, and we're not going to break this up. I want to keep going and finish this off. So first thing is, let's delete all that. All right, so now we're going to do the transient response for the inductor, and we're going to figure out the charging and discharging and kind of go through the math a little bit, just like we did for the RC. And then now, once we have that, then we kind of wrapped up RC and RL, and then we're in a good place to do the next thing we want to do, which is start talking about phasors and impedance and reactance and complex impedance and all that. All right, so let's go ahead and let's get started here. All right, so before we start, let's write everything down, just so that we've we know we've memorized it, and then also just to have these things, which is nice. Okay, so let's do this. So for capacitor, and over here let's do inductor. Okay, and let's just put that in a different color for you, so it's a little easier to see them. Inductor. Okay, so inductor and capacitor. Okay, great. All right, now, so what are the equations that govern these two things? Okay, so let's see here what we want to write down. Okay, let's start off with, we have Q equals CV. So charge equals capacitance times voltage. All right. And then over on the inductor side, we have kind of the analogy here, the analogous thing. We have flux phi equals inductance times current. Okay. All right. Now, we've also learned that if we take the derivative of this side and this side, dq, so if we do this, so if we say dq equals c dv dt, right? Then we have, excuse me, dq dt, right? So if we take the charge per unit time, right, that equals the capacitance times the change in voltage per unit time, right? Well, dq dt, so that's charge per unit time, that's current, right? So we can just put this is equal to current, I. So I equals CdV dt, all right? So that's kind of tells us that all the things we need to know to kind of solve capacitor problems. But again, I like having these next to each other. All right, let's differentiate both sides of this with respect to time. So this is d phi dt. And again, you don't need to know calculus. All you need to know is this just means I want to look at a small change of d phi with respect to time, with a teeny tiny bit of time. All right, so you could actually do this, and you could let me write this first. And so this would be L, and this would be di dt. Okay. You could recast this in this format. You could use this delta notation, and L, and then this would be delta I, delta t. And so what this means is the differentials mean something very specific. They mean this infinitesimal amount, and it's a calculus thing. But we can rewrite it like this, then this becomes an approximation. So let's say that delta t was something very, very small in reference to our circuit operation. Our circuit, let's say, works in the order of microseconds. So if we made delta t nano or picoseconds, and we just did one little delta t, and then computed what delta q, and then we did the same thing with delta I and the same delta t here, then our answer would be almost nearly what this would be, except we're not using calculus anymore. We're just using simple numbers, right? That's it. But then as we make that smaller and smaller and smaller, that is the definition of the derivative, and then you end up with these kind of differential things. But anyway, this is something to remember, this kind of format. And you might see this sometimes, all right? And it's perfectly valid for an approximation. All right, so here's our kind of modeling things. And you know what? And let's not forget, let's throw in our other guy here. Let's throw in Ohm's law, right? And what's that say? That says that V equals I times R, and then of course all the variations of it. And why don't we throw in power equals V times I? So we've got all these things, and then we also know a couple other things. What are the couple other things? We know the KVL, Kirchhoff's voltage law, right? Which I'm not going to state here again in text, but this is just Kirchhoff's voltage law talks about the sum of the voltages around a complete loop equals 0, all right? So that's that one. And then there's also Kirchhoff's current law, which states that the sum of the currents entering a node has to equal 0, all right? So anyway, so those are those two guys right there. And so these are all the things that we've learned, and then we can differentiate, integrate, and do all kinds of stuff to them. All right. Now, so now let's go and let's try and work with our inductor circuit here, and let's see what we can come up with. Okay. So again, we want to do this whole charging, discharging, and we want to compute the solution to it. Again, this is not a math class, and I don't want to do too much math and go through that. I just want to show it to you a little bit and the derivation of it, just a little bit. So let's draw a circuit where we could do charging and discharging. So let's use that little switch idea. So again, let's go over here and let's put a voltage source plus to minus. And I'm going to name this, let's see, what do I like naming this? How about, I'm gonna name this VS, all right? And then this is going to come up here like this, and let's say we've got this little node here, all right? And then let's go all the way over here. Now right here, how about let's go ahead and let's put a, let's see, I want to draw it, let's do this way this time. Let's draw an inductor here, all right? There's an inductor, all right? And then we're going to draw a resistor here. And it doesn't matter where the inductor or where the resistor is. They're both in series, so it just helps making the notation a little bit simpler. All right, and then let's make a switch here. So we're going to make a switch, and it's going to be a kind of a 3-position switch. So it's going to have 3 positions, and then this position will be here, and this will go down to this kind of ground, this common, and if we wanted to, we could put a ground there, right? All right, and then let's draw the switch. We'll draw the switch in orange, and right now it's sitting in this middle node, and then let's label these nodes here. So we'll label this node 0. And these are different than the circuit nodes. These are just the switch positions. They're really positions of the switch, just so we can talk about them. And and so the switch can move up and move down, right? And right now it's starting off in this position too. Okay, so now we have this inductor here, right? We've got this inductor, and let's we'll use this color. All right, so we've got this inductor L, and then we've got this resistor R. All right, and we're going to do charging and discharging in this circuit. So let's start off with doing charging. All right, and right now let's say that nothing is happening, and the circuit was just sitting here in position 2. So the field is collapsed. There's no current. There's no nothing. Now let's move the switch to position 1. All right, so we'll say switch at position 1, all right? And so now we're kind of interested in what's going to go on in this situation here. All right, so switch at position 1. The moment that we close that, right, what's going to happen here? So the moment that we close this switch, we're going to have this voltage immediately is going to be right here, right, at this point, at this node. So we're going to have this voltage right here, and the circuit is going to want to have some current to flow, right? And but what's going to happen is this inductor is going to act like an inductor, and it's going to start doing this thing over here, right? This L di dt thing, all right? And then remember, there's also this minus sign that kind of comes in here, right? And we're going to talk about what's going on there. But right now, so we close this, and then the inductor is going to start having self-inductance. It's going to create a reverse back EMF. It's going to push against the current, trying to get pushed through it in the clockwise fashion here. It's going to lose, and then current's going to start flowing, and then the circuit's going to start working. All right. So let's draw kind of what this current is. So we're going to get this current going through here, like this. All right, and let's go ahead and let's call this, we'll call this I. Let's make a capital I for once. All right, and then we're going to get a couple things are going to happen here. So we're going to get plus to minus, and I'm going to call this VR right here. So right here is VR. All right. And then we're going to get plus to minus, we're going to get a V sub L. We're going to get a voltage drop over the inductor, and it's going to drop like that. So the current right here is going in the same direction as this plus to minus. So now this is where this minus business comes in. So when the current's going in this direction, this is not the current direction that this is talking about. It's talking about the back EMF, which is going to be equal. But the sign is going to be different. So when we're doing the discharging, that's where this minus comes in. So the minus sign is talking when we're pushing in the opposite direction. But when we're charging, we're going to have a positive there. All right. So now let's do Kirchhoff's voltage law. Let's do Kirchhoff's voltage law through this circuit right here. Okay, so we're going up and around, and then that's that. Okay, so what do we have here? So let's just do this. So we start off at Vs, so let's do Vs equals, and then we've got this voltage drop right here. All right, so this is a VL, and then we've got another voltage drop right here, which is VR. Okay, so simple enough. And remember, Vs could be a function of t, right? It could be a function of t, or it could be a constant, right? We're just not going to write it, but let's just assume it is a function of t, so we've generalized this. All right. Now, can we start replacing things here? All right. So, all right, what do we know here? So VR, so that equals, what does that equal? So VR, let's see, that equal, we've got the current, we know what the resistance is, so that would be IR. So there's one thing, so there's one extra piece of information. And then VL, the voltage over the inductor developed over the inductor, can we figure that out someplace here? And that's actually right here, and we forgot to write that down, sorry. So this is d phi dt, and remember d phi dt is V, all right? So that's voltage equals d phi dt, so voltage equals this minus L di dt, but in this case it's going to be a positive, so voltage equals, let's write this down one more time. Voltage equals, and then L di dt, and then with this potential minus sign here, which we have to be careful of, right? And that's that whole idea of Lenz's law, and kind of explains why you're getting that minus. Anyway, all right, so we've got that right there. So we can use both of these things. So let's see what we can write here. So let's keep writing, and let's see here. So we've got Vs equals, and then we've got V sub L, and what's V sub L? Where are we here? That's just L di dt. So that's L d I dt, okay, and then plus VR, but what's VR? That's just I times R, okay. All right, and remember, we want to, in this case, we want to solve for the current, all right, and then we can find what the voltage is also, but let's solve for the current, because we've got a differential equation, and it's in terms of the variable I. See the derivative of I with respect to t and I. So we got to kind of form this in terms of I. So let's move things around a little bit here. What I'm going to do is I am going to move this over to this side. So let's do that first. I'm going to subtract that. So I'm going to get V sub S minus L di dt equals I times R. Okay, and then I'm going to divide everything by R. All right, if that's okay, divide everything by R, and then this will be 1 over R here. All right, and then so these will cancel out. and then I'm going to move I over here. I'm just going to flip it around, right? So I'm going to have I, and then what's the left side? All right, the left side is simply Vs over R, and then this right here, we simply have minus L over R, and then we have di dt. Okay. All right. So, and again, remember this is I as a function of t, right? I is a function of t, and we're just not writing that just so that we don't have to. Okay, so we've got this right here, and we've got another one of these differential equations, but we know that the solution of this is going to be of the form something like this. It's going to be, and we could write it right here. Just write it like this. So the form of this is going to be something like, I is equal to a plus be to the minus t times some kind of little a, or we could, kind of cheat, and we know we could call it tau like that. So based on the initial conditions, so what are the initial conditions? So the initial conditions are at time t equals 0, right? At time t equals 0, there's no current, right? There's no current, but the current is going to rise up. So at t equals 0, there's no current, right? And then the moment we close this switch, right at that moment, that current starts raising up. But at t equals 0, there's no current. And then also at t equals 0, the entire voltage is over the inductor because there's no current, right? So because there's no current, then there can be no voltage drop over the resistor, right? Because if I is 0, then VR, which is I times R, must be 0, so the entire voltage is over the inductor. So remember that. So at t equals 0, all the voltage is over the inductor, and there's no current in the circuit. So those are initial conditions. So once we figure all that out, what we end up with, and we've kind of seen this in the last lecture or so, is because I kind of cheated and showed it to you, is we're going to get I, and again, I'm going to put it as a function of time so we can see this, equals, and so what does I equal here? It equals this V sub s over R, V sub s over R, times 1 minus e to the minus t over tau, all right? And now this tau, right, happens to be this right here. It happens to be L over R equals tau. All right. So that's it. So rewrite this again. I sub t equals V sub s over R, 1 minus e to the minus t, and this is divided by L over R, or we could say, minus R t over L if you like to do that. I don't like to do that. I like to just keep it clean. So I just do this right here, and then I just leave tau as L over R. All right. And that's the worst exponential I've ever made. Let me make that a little bit better. Minus t over L over R. Okay, good enough. Okay, so that's it right there. Now, so that describes the energizing of the inductor. So like the charging in the capacitor, but I like to use the word energizing because nothing is charging. All right, now let's talk about a couple terms here. Let's talk about this term right here. So this is this Vs over R, right? So this Vs over R, what's that? Well, that's just the source voltage over this R here, all right? And so what this is this is kind of the current at infinity. So when this thing has been running for a long time, you're just going to get this. And a lot of times this is just called I naught. So this is the final current in the circuit. So when t is equal to infinity, right? So at t is infinity, what's this term going to go to? It's going to go to 0. And because that goes to 0, we're just going to get Vs over R. In other words, I, the current in the circuit, just equals the voltage over the resistance. And that's what you would expect because the inductor acts like a short at infinity, right? So that's what's happening. The inductor acts like a short. So let's draw that. Let's draw that curve. So let's draw that curve. So let's draw the charging curve here, and I'm just trying to keep enough room so we can keep everything on the screen here. All right, so here's time. time t. Alrighty, and that's going like that. And then now let's pick a couple colors here. Since I already used blue to draw the current, let's just stick with that. But let me use a little brighter one. Okay, so the vertical axis is the current. Okay, so we're going to call this, I in the circuit here. And then of course this down here is 0 in everybody's case. All right, so when we turn this thing on, remember there is no current, right? There is no current because the moment we turn this on, boom, the inductor starts inducting and reacting, and it pushes against everything. And at that infinitesimal little moment, there's no current. And then current starts flowing, right? As the inductor fights back and back and back, and it just loses slowly, all right? So we get this charging curve, right? And so here's what the curve looks like for the current in the circuit. And it goes like this, and it's just an exponential. All right, and this point right here, right, where it's asymptotic, right there. And asymptotic, if you've never heard that word, you've heard me use it a couple times. It's just a math word. It just means it gets infinitesimally close, and at infinity it would make contact, but it never actually reaches it. It's kind of like, you can look up Zeno's paradox a little bit. So if you were like at a wall and say I'm 1 foot away from the wall at this moment in time, and I get a half, I close the distance by a half, now I'm a half foot, close that distance by a half, now I'm a quarter foot, keep doing that, keep doing that, keep doing that, right? No matter what, right, you keep going half as close to the wall, so you would never hit the wall, but in the limit at infinity you would touch the wall. So that's why it's called a paradox. It's kind of confusing. But anyway, all right, so there's the current, I, and then what is this equation? This is this thing right here, right? That's what is drawing this. Now, same thing with the time constant stuff. Same thing with the time constant stuff. So again, I want to start trying to be semi-correct here. I'm always just so off with these things. So if this is 100% right about here, then that's about 60% right there. Okay, so if we go like this and we cut this across, okay, and then as drawn, this is one time constant, right? One time constant. So this is T equals what? L over R, our inductor over our resistance. So at time equals that, whatever that happens to be, we will be at this range right here. And what's this? Well, this is 0.63 times the final current in the circuit. What's the final current in the circuit? It's simply, what is the final current in the circuit? Now I've confused myself. It's the source voltage over R, right? That's, yeah, Vs over R, right? And so we can write it right here. There's just not enough room here, times Vs over R. And then this current right here, this is Vs over R, not 63% of it. And so that's the final value, the asymptotic value. And then here's Vs over R. That's the current when you're at 1 time constant. So this is when time equals LR, which is just 1 tau. And then over here at 5 tau, right? So this would be 1, 2, 3, 4, 5, right? So this is at 5 tau, or 5 times L over R if time equals that. That's when we're at our final value. For all intent purposes, this is 99.9999999 of the final current value. Okay, so cool. Now let's discharge this thing. All right, and let's discharge it. I don't know. Let's use red. So the discharging, and we already know the answer to this, is basically this equation, and we're going to take out this. All right. So first thing, let's write what the charging equation is here. So the charging equation is I sub t equals V sub s over R times 1 minus e to the minus t over L over R. All right, that's charging, so that's CH arging. Okay, that's the charging equation. So the discharging equation is we know we're just going to get rid of this 1 minus part, and the discharging, so say discharging equation, and maybe we can draw that in a brighter yellow. Discharging is I sub t equals V sub s over R, and that's just e to the minus t over L over R, which is that time constant tau. And now we don't really need parentheses there, but I'll just put them there. All right, and that's our discharging. So now remember when it's discharging, so when it charged, looking back up here, the current was flowing clockwise, right, and things are dropping plus to minus, plus to minus. When it's discharging, we go into position 3 here. So now we're in position 3. So now when we do that, here's our red current. So now the voltage is the same on the inductor. It's not going to flip-flop, but the current's going to go in the opposite direction. So now the current's going to go like this, okay? And it's going to discharge. All right, so now we're discharging, and that is the world's horriblest arrow. Okay, all right, so now we're discharging here, and so the discharge curve looks like this, just like that. All right, and it's as you expect, same thing. All right, so this would be like our new time if we kind of reset this at time equals 0 right here. Then when this thing is down 63%, that would be 1 LR time or 1 tau, and then when it's all the way down to 0, that's at about 5 LR times or 5 taus, and then that would be that, and that's the discharge. So again, the discharging is simply I sub t equals V sub s. Now, in this case right here, there's really no more V sub s. So what we have to think about is kind of what that current was, right? And that's why we bring in the concept of, and where is it, where is it, where is it? I wrote it someplace, this I0. So that's at the moment that we switch this thing, there's this current I0, right? And so it's kind of like I0 because this Vs over R, we'd have to bring it from the other side of the event, but we'll just call it I0 here, and that's e to the minus t over L over R, all right? And that defines that, and that's it. Okay, so now, what if we want to know the voltage? So we're running out of room and running out of space, and this is becoming a big mess, hodgepodge. But let's look back at this equation here, back here. All right, so this is Vs over R, right? And then so this is I. Well, I can just turn this into voltage very easily. So if I want to know the voltage, right? If I want to know the voltage, then all I need to do is say this. If I multiply everything by R, right? So if I multiply everything by R, and I multiply both sides by R, these cancel out, and then I just get R times I. Well, what's R times I? That is this voltage VR right here, this voltage V. So that's the voltage V, that's it. So that's the voltage VR. But you got to be careful. That's the voltage over the resistor, right? So that's the voltage over the resistor. And so if you wanted, so this equation is the voltage over the resistor when it's charging. If you wanted a voltage over the inductor, it would just be Vs minus that, right? Okay, and so that would be that. So that's how you can get current, or you can get voltage. You can do whatever you want to do depending on what you want to do. So that is the inductor energizing and de-energizing. We've seen the capacitor charging and discharging. And this is what happens when you're doing these transient pulses. So the reason why this is important is because whenever we have a square wave in a circuit, it's like we're doing this transient stuff. You know, when we do these square waves, it's instantaneously going up, it's instantaneously going down, and of course it's not instantaneously, right? There's some edge here. These are really trapezoids, right? These guys really look like this, right? They look like trapezoids, right? Because nothing happens in 0 time. But for all intent purposes, they happen instantaneously, and because of that, that instantaneous change, we're really kind of doing charging, discharging, charging, discharging. And depending on what the time constant is, we will either the charging will either go very quickly, and then it'll go like this, right? And it'll kind of keep its shape, right? But if it can't keep up, oops, if it can't keep up, let's use red. If it can't keep up, it's going to go like this, and then it's going to go like this, and then it's going to go like this, charging, and then it's going to go like that, discharging, right? Or energizing and de-energizing, right? And so this is what happens, all right? So that's why you don't want inductance and capacitance in your signal lines. You want them to be perfect, which they aren't. So you have this, and so you've got to always be cognizant of this. Now, what else did I want to say? All right, so we're not going to, this is a kind of another discussion, but so okay, we've got capacitors, we got inductors. They both kind of do the same thing, right? So, and they do, right? And you can kind of use one in the case of the other and so forth. But it turns out that capacitors are much easier to make. Well, not easier to make, but capacitors, you can get kind of the frequencies that you want low or high very easily. Whereas with inductors, inductors kind of, because they're coils of wire and wire has like no resistance, you have to make a pretty big inductor if you want to do things at kind of low frequencies. So inductors by definition are very high frequency components. So they're just naturally very high frequency. Now, so when you see, for example, when you look at RF equipment or you look at microwave equipment, if you look at microwave stuff, you like look inside and you'll see nothing but like little pieces of wire and little bars and little, cylinders. And you're like, where is the circuitry? The circuitry are those bars and cylinders and wires, because those are inductors, and they actually at the frequencies that you're dealing with, these things are acting exactly perfectly for the designer's needs of filtering, right? So at very, very, very high frequencies, you're going to see a lot of inductors because those are more applicable to those frequencies. All right, so okay, so that's good. We looked at MATLAB, we looked at these transient responses. I think we're in good shape now. So now, this has been kind of brutal, a lot of math. I know it's not a math class, but I just wanted you to see it, and then we'll just have the equations, we'll use those forever. And then now next, we're gonna have some more math, but it's necessary because we need to understand the concept of frequency response and frequency domain. So this is important. And now what we're going to do is we're going to learn about phasors, and we're going to learn about impedance and complex impedance in the next lecture. And then it's going to start to get fun, because then we're going to be able to directly apply those to things and kind of do computations. And then I'll do a couple circuits, and I'll do something with AC from the wall, so I could potentially start on fire or explode. That'll be fun. And so we'll do that. And then once we're done with that, then we will then go to filters, and then we're going to do a few experiments with filters on the bench. So we're going to get back with our hands dirty pretty good. We'll do the low pass and high pass filters, and I'll show you that. So we're just getting the pieces of information so you guys know this, and it's all really important. And then once we're done with that, then we're on to semiconductors again, and we're going to like get out of the mud and start getting back up into some of the digital domain stuff. All right. So anyway, lots of fun, lots of cool things. It's pretty exciting, and I will see you in the next lecture. Bye. All right, welcome back. We are on the next lecture, and we are making good ground up here. And let's see. So last time, what did we talk about? We talked about inductors, and we went through the transient response of the inductors, so charging and discharging. All right. And now, if you look inside of the notes here, my book chapters, the next section is kind of RLC circuits, and then we've got series RLC and parallel RLC. So we're not actually going to do anything with that. You can read the book if you're interested, or other sources. We've done enough of this so far. But just in brief here, if you take a look, a series RLC is just that. We've got an R, an L, and a C. And so if you combine these three components and you happen to put the capacitor in this position here, you get this kind of thing happening. And then here's a parallel RLC circuit. So you can put these in all kinds of combinations, and I just talk really briefly about this right here. And then we're going to move into a semiconductor concept, some more semiconductor stuff inside of the notes in the book at least. But what I'd like to do is we're going to veer away from the notes here, and we're going to talk about complex numbers. We're going to talk about impedance. We're going to talk about reactance, and we're going to talk about how those things relate to inductors and capacitors and AC circuits. All right. So again, we need all of this material and kind of this math to be able to describe what things do. All right. So let's go to our drawing program here that we like. And so what So what we did in the last lectures was we were looking at the transient response to things. We're looking at the transient response. And so, that has to do with if we have an inductor or we had a capacitor, right? An inductor L, a capacitor C. And if we had one of these devices, and we might also have some resistance in here, right? Resistor, RC circuit, RL circuit. What we were interested in is if we were to graph, and here's say time, and this might be voltage or this might be current. And if we were to excite these circuits with a sine wave or a square wave or something like that, in our examples, we were kind of exciting them with a power source that we just turn on or turn off, which is really the same thing as exciting them with a square wave, right? And then what we started to learn was in the RC circuit or in the LR circuit, right, is that what happens is these components, depending on how they're configured, there's like a charging and then there's like a discharging and a charging and a discharging, or an energizing and de-energizing if you're talking about the inductor. In other words, whenever we apply a current or a voltage, the capacitor or the inductor reacts to this and it opposes either the current or the voltage change, all right? So that's kind of, so this reactance or impedance to it is kind of what we want to talk about now. So now what we're going to do is we're going to generalize this. So now this is a really, really important subtle detail here, and I want to make sure you get this. So when we're talking about the transient response, we're talking about we make a change kind of instantaneously. There's no voltage or no current, and then instantaneously we turn on a voltage or a current, right? And so those are kind of a square wave. So now the next question would be, well, what would happen if instead of just doing that, now based on the transient response, say if we put a sine wave through these components, right? So say if we just put a sine wave, so sine omega t, right? And omega is the angular frequency, so we could also say sine of 2 pi ft, right? Because 2 pi f equals omega. So omega is in radians per second, and then now this would be in hertz, right? When you put the 2 pi there. So either one of these things. And then if we put something in front of here, so if we put an A in front of this, right, that's kind of the amplitude. And that ends up being this right here. This is A, all right? And then this right here, this is the period, right? That's the period. All right, and the period equals 1 over the frequency, right? So, hopefully you're clear with all this. So now the question is, what if we put sine waves through capacitors and inductors? And the reason why we're interested in this, and this is super, super important, is that we can basically take any waveform. So if we have some complicated waveform here and it's all over the place and got all kinds of things, we can deconstruct this into a summation of sine waves or cosine waves. And so that you can look up Fourier if you want to, Fourier transform, and that kind of talks about and describes why that's true, right? So the point is, if we can take any signal and break it into a bunch of sine waves or cosine waves, that means that if we can figure out how to process a pure sine wave of one frequency and amplitude, then the response of a circuit, a linear circuit, to any waveform would just be a sum of all the sine waves that make up that waveform, right? So if we can understand how the response of one waveform works, a pure sine wave, then we could extend that to figure out how it would respond to any waveform, all right? So that's important. So what we really want to do is say, can we figure out how to describe circuits that have inductance and capacitance in a different way, instead of dealing with the time domain that we've been dealing with in the transient response, where we're getting functions v of t and I of t, right? So let's write those down again. So if you remember, we have for the RC circuit, right? Let's write down what we have there, RC circuit, and then we have, we could call it the LR circuit, right? And in one case, let's just redraw what we have here. So we have some voltage source, and then we have a switch here. All right, and then let's draw the switch like this, a little bit easier to draw it like this. And then we have our resistor, and we have our capacitor. Okay, and then down here, we've got a switch that can be in one of three positions. All right, it could either be connected to the voltage source, Vs, and then we have R, and then we have C, or it could be connected here, and then we've got this circuit. So to charge the circuit, we connect the switch here, right, and then we get a current flow like this, right, and then to discharge the circuit, we connect the switch here, and then because the capacitor is charged now with plus on top and minus on bottom, we get a current like this in the opposite direction in that case, right? So that's that case. All right, so there's an RC circuit. And then what were the equations that describe this? So we had for charging, right? So we had for charging, what did we have? We had, so we had V as a function of T, and that's V of C, V sub C. So that would be this right here. Call that V sub C. V sub C equals, and then we had the source voltage, right? And then we had 1 minus e to the minus t over RC. And this RC thing, we call this tau, which is the time constant, RC, all right? And in 1 RC time, the circuit would charge up to 63% of its full charge. In 5 RC times, it would be fully charged, all right? So that was charging. And then what's discharging? Discharging. And, you know, I'm writing these down, but I don't necessarily have these memorized. When I work with them, I memorize them, but after I'm done, I forget them too. And, you know, that's the point of being able to kind of rederive them. You can always look them up, but no one remembers all this. So when people teach things, they teach it 1,000 times. So that, you know, it looks like they know this stuff inside and out, but they've just taught it 1,000 times. They've got it memorized. But, you know, these are not easy things to remember. So discharging V sub C of t, in this case, we're already charged, so we're just going to have this term here. And so it's V sub S e to the t over RC. Now be a little bit careful about V sub S. When we flip it over here, right, V sub S was the original voltage that it was charged up to. When we discharge it, that might be some other voltage, right? We might stop time and move the circuit or whatever, but this is just whatever the charge is on the capacitor. So just be careful. All right, so that's that. And these are transient responses. That's why they're functions of t. So they're in the time domain, it's called. So we're dealing with time. We're not dealing with frequency. Notice there's no F in here at all because there is no frequency. So what's happening is we're assuming that this thing turns on and we're getting this instantaneous, you know, voltage rise. And then we turn it off, right? And then now there's no more voltage, and then the circuit's just doing whatever it's doing. So it's kind of going like this. And you can see that's where we're kind of getting that square wave idea. But what we want to do is instead of having Vs just be a static voltage, we want it to be a sine wave that's a function of time, and then we want to see what the response is, and that's what we're going to talk about and get the language for in this lecture. Okay, again, let's reiterate this real quickly for the LR circuit. So same thing, we've got a power source here, we've got a battery, all right, and we're going to have the same kind of switching mechanism here and here, and we'll go like this and put another little node there, another little node there. And so we want to be able to energize and de-energize the circuit. So put our inductor there and put our resistor here. Okay, like this. Okay, and there's our L, and there's our R, and again, we can call this Vs. And again, when we close this switch to this position, we're going to get a current flow in this direction, right? And that current then, after a long period of time, is going to stabilize. The inductor is going to act like a short, and then the final current will just be Vs over R, getting that kind of thing. But the moment that we turn that on, that inductor fights that, and that's what that whole voltage equals L di dt part is about, right? And so it impedes the flow of this current, so by generating this voltage, okay, or it reacts to it. Same thing with the capacitor. The second we we apply this voltage to the capacitor. The capacitor's initial voltage is 0, and now we're trying to put charge on this capacitor. And as we put charge in this capacitor, charge starts accumulating, and it pushes against that current, right? So the capacitor is pushing against the current, so it's reacting against the current, and the inductor is reacting against the voltage, right? And again, we can write down these equations here. We'll just use a different color here. So charging, and I just made my own mistake. I like calling this energizing because the inductor is being energized. All right, so energizing is, so what is it? And we'll call this I, and let's just call it, we're just going to call this I, and then at when the circuit is all done after a long period of time, I is going to equal what we're going to call I naught, which is going to equal Vs over R. All right. So when we're energizing this I here, we're going to say I of t equals this I naught times 1 minus e to the minus t over tau, which in this case is L over R. So the time constant here is L over R, right? Remember that. And then when we discharge, it's similar, or de-energize, which is the term that we really like because it's more indicative of what's going on. That's I naught, whatever that current is flowing at that time, e to the minus t over L over R. So that's it, and that's the de-energizing. So de-energizing. Okay, so those are those two cases, all right? And so, you know, write those down, try and see if you can work those out and all that. All right, so now what we want to do is, so let's, before we continue, let's look at a couple things with these two circuits here. So, and then we're going to kind of fold this into what we're discussing. All right, so in the RC circuit, so in the RC circuit, what happens is we turn on this this power supply, we turn on this voltage source, right? All right, when we do that, what happens is we start to get some charge flowing here, right? We start to get some charge flowing here. As that charge starts flowing, right, then the capacitor plates start charging and we get a voltage on those plates. All right. So what I want to bring your attention to is that the capacitor circuit, what's happening is the current. So I'm going to write down a little word here, right? So let's put this in a different color, and we're going to use this in a second. So there's the current and then there's the voltage, right? And so current and voltage lead and lag each other in these kinds of circuits, in the capacitive and the inductive circuit. So in the capacitive circuit, we write this down. We write down ICE, okay? And I stands for current, C stands for capacitance, and E also means voltage or electromotive force. Remember, E is like equivalent to V, depending on, if you learned electrical engineering, 20, 30 years ago, we always used E, and now people kind of use V. But anyway, so ICE, and what this means is current leads, and here's the capacitor. So current leads the voltage because it comes before it in the word ICE. So current leads the voltage. Current leads the voltage. So what that means is when we turn this thing on, charge starts accumulating, right? So we start to get a current flow, right? Charge starts accumulating, plus and minus on these plates. As that charge starts accumulating, then a voltage starts developing. So the current leads the voltage, all right? And it actually leads it by 90 degrees exactly. So the current leads the voltage by 90 degrees exactly. So I'm going to draw something here. So I'm going to draw a little graph, all right? Okay, and so this is going to be time t here, all right? And this vertical graph is going to be both voltage and current. So we're going to draw, let's draw voltage in red, all right? So this says that current leads voltage. Current leads voltage. All right, so we're going to do blue for current. So if we were putting sine waves through here, all right, so current leads the voltage, and this is what this would look like. And we're going to get into this a little bit more, a lot more in remainder of the lecture, but I just want to show you this. Okay, so this is current, so this is I, okay, and then voltage we're going to draw here, all right? So current leads voltage by 90 degrees. All right, so here is the voltage. So it's like this. And these are always challenging to draw. Okay, and this one is the voltage. Okay, V, or you could call it E. Okay, and then let's draw this again on top of this so we can see it better. All right, and that's the current, I, the current. All right, so a couple little interesting things to note here. All right, so I is the current, and it's leading by 90 degrees, the voltage, and that's how it always is. Always in a capacitive circuit, the current will always lead the voltage by 90 degrees. But here's an interesting thing. So let's look at what was the modeling equation for the RC circuit for the capacitor? What's the modeling equation? What is it? It's I equals C dV dt. I equals C dV dt, right? And then over here, it's V equals L di dt. So I equals the capacitance times the instantaneous rate change of the voltage with respect to time. Okay, so where's the voltage? So the voltage is right here, it's the red one. Down here at the bottom, if you look at this sine wave, the slope of the sine wave is at its absolute maximum right at 0. So right at time equals 0, the slope of this, and that's what the derivative of voltage with respect to time, the slope of it is at its absolute maximum. Because it's at its absolute maximum at that one point, and you can prove that to yourself. If you just zoom into this, let's take a quick look here. There's a lot of ways to prove this to yourself, mathematically or intuitively, but I like to use intuition as much as I can. So here's what this looks like right here, right? Okay, and then it starts curving away. And remember, this is just a sine curve, right? This is just a sine curve, right? So if you look at this, clearly the slope is decreasing, and then here it would be flat. So here at the very beginning, it's at its absolute maximum. So the derivative, or the slope, of voltage with respect to time is at its maximum. That times C equals I. And look, here is the maximum I. So whenever the voltage crosses the 0 threshold, that's where it's going to have maximum slope, when it crosses the 0 threshold. And every one of those times, you'll notice it's going to, the current is going to be at its maximum, either positive or negative, right? So right there, right, and then look here, right here again, and then right here again, okay, and then right here again. All right, so each time the current will be at its maximum because the derivative of the voltage times C, which is just that, capacitive constant, is at its maximum. All right, now, so we have something very similar, obviously, for the LR circuit. Okay, so over here we've got current leads voltage in the capacitive circuit. Okay, so now let's do something similar over here for the LR circuit. All right, so there's a similar little trick, mnemonic, to remember things with here. And so in this case, it is called Ellie. All right. And I guess if you're a girl, you'd call it Ellie. If you're a boy, you might call it Eli. So I don't know. I've always called it Eli, but I think people mostly call it Ellie. All right. So in this case, again, E just stands for voltage. So voltage leads. And remember, the thing in the middle is just what the circuit component is. It's a capacitor here, and then in this case, it's an inductor, right? It's the order of these things that tell you if it leads or lags. So this right here is just what is it we want to deal with, and this is how you remember it. So voltage comes before, right? Or excuse me, voltage comes before current, and here current comes before voltage, right? Or it leads. So here current leads the voltage, and here voltage leads the current, all right? And the Ellie or Eli. So, and then the component is the L. So if you can just remember ICE and Eli, or Ellie, you'll be okay, all right? Now, let's see kind of why this is. So, okay, the voltage leads the current. The voltage leads the current. All right. So, and we actually have done this, but so I'm going to kind of go through it pretty quickly here. So voltage leads the current. All right, so if you look at this modeling equation right here, this says that voltage equals L di dt. Voltage equals L di dt. Okay, so the moment that we close this circuit, all right, we have this voltage, and the voltage is connected to this inductor and this resistor. All right, the voltage over the inductor, that's what this guy says here, says it's L times di dt. All right, but at this very, very moment, there is no current. We've applied a voltage, but there's no current, right? Or actually, I'm sorry. So so at the very beginning here, we've applied this voltage right here, all right, and the current is zero, right? So the current is zero, but the change of current is at its maximum. So in other words, the moment we close this, we have this circuit with the L and the R. There's no current in the circuit. There's no current in the circuit at this moment, all right? So since there's no current in the circuit, there's no voltage drop over this resistor, and the whole thing drops over the inductor. All right. Now, if we look at this equation right here, it says V equals L di dt. All right. There's no current yet, and remember we're talking about this time equals zero, which is a special little time. There's no current yet, but there's a voltage applied to this inductor, and the current is changing at its maximum, because now what's going to happen is all of a sudden the current is going to want to flow in this circuit. All right, and so it's at its absolute maximum value right now. So we get the absolute maximum voltage right now, all right, at that time. So the voltage leads the current, all right? So at t equals 0, we have all the voltage, the peak voltage is going to appear over the inductor. We have no current, but the current is changing at its maximum, and that's why we're getting the maximum voltage. And I know it sounds kind of circular, but if you think about it, that's what's going on. Okay, so let's draw again. Let's draw what's going on here. All right, and this hopefully will help a little bit. That's probably, let me back this up a little bit here. Okay, back it up just a little bit. Okay. All righty, and we have time t down here at the bottom. All right, and up top here, we're gonna have voltage and current. All right, so this time we're saying that the voltage leads the current. So we use voltage red here, all right? So the voltage leads current. So here's voltage I'm going to draw here, and we're using sine waves. So we're just going to continue with that very cleanly, attempt to draw a sine wave. All right, so this is a voltage. All right, and then the current, all right, so voltage leads the current. So the current is lagging by 90 degrees. So now we're just going to draw a sine wave right here, carefully. Okay. And okay, good enough. All right, and then this is the current here. All right. Now some things to look at. So all right, when we're at 0 here, okay. So the current, all right, when we start this circuit off, the current is 0. All right, there's no current in the circuit. We apply a voltage, no current has flowed yet, but the rate change of current with respect to time is at its maximum. So right now you turn this thing on, and this circuit wants to go. So the instantaneous change of current with respect to time or its derivative is at its maximum. Because it's at its maximum, L times that is going to give us the maximum voltage, and that is this right here. All right, so we're going to get this voltage right here. This voltage that we'll end up getting is going to be equal to Vs over R. Okay, and that's what that I naught is. There it is right there, that Vs over R. That's that maximum. All right, and so now every time the voltage goes through its maximum slope, which will happen every time the current goes through its maximum slope, that's going to happen every time it goes through a zero crossing on the axis here. So every time that happens, you're going to get a maximum voltage. So here's one here, and sure enough, there's one of your maximum voltages. Here's one here, and if you want to bend the line a little bit, you get another one there. All right, so the voltage leads the current by 90 degrees. All right, so and then here current leads voltage by 90 degrees. that's something that you need to remember. And if you want, you can kind of go through these kind of analyses to kind of remember why that happens. But this is important because what we're going to do is we're going to stop here and pick up in the next lecture. But we're going to take this, we're going to make an assumption of this fact now that we've kind of figured this out. All right. So again, current leads voltage in a capacitor by 90 degrees, always, and it's always by 90 degrees. And voltage leads current in an inductor by 90 degrees as well. All right, and then here's all the modeling equations for everything, all the modeling equations, the charging, discharging, energizing, de-energizing, and so that's all we need to know. Now we're going to go into the AC domain, and I'm not so much interested in AC like coming from a wall AC. I'm not interested in that. And again, it's a really bad word, not a bad word. It's an unfortunate phrase, alternating current, because whenever we're talking about signals, right, we're going to be talking about technically AC, right? The signal is alternating, but it could be alternating about a DC offset. So typically when people say AC, they mean wall outlet power, right? And so that's true, that's AC. And what we're going to be doing is talking about AC, but we're not necessarily talking about power coming from the wall. We're just talking about sinusoidal signals that alternate in time, and that's it. And we're ultimately we want to talk about a sum of them to make up any complex signal, not just one single sine wave at a single frequency and amplitude, but a number of them that compose like the audio that you're hearing right now or the video signal or anything. All right. So anyway, all right. So let's finish up here. This is a good spot just to stop, and then I'll meet you in the next lecture, and then we're going to talk about phasors. We're going to talk about reactance, impedance, and a whole nother way to do circuit computations with reactance and impedance. And it's pretty cool, and it's a lot of fun. And then after we get done with all that, then we can finally talk about filters, because we'll finally have the language that we need to describe those very easily, and you will understand what they're doing. All right. So finish up, and I'll see you in the next lecture. Bye. So the capacitive reactance, right, is always going to be 90 degrees. The voltage is 90 degrees lagging, so it goes right here. So it goes right here. There we go. And so this is x of c. And guess what? We know how to compute it now, right there. That's the formula. It's just 1 over 2 pi fc. So we know actually how to compute it. And now here is the inductive reactance, x sub L. And we know how to compute that. It's just right there, right? So now for a given frequency, we know how to compute these things, and we can draw this little phasor diagram of x sub L, x sub C, and R, all right? And once we can do that, now what we can do is we can add R's and C's and R's and L's together in single circuits, right? And we can do things with them, okay? So I think, so why don't we do this? Let's just keep breaking this lecture up, because we're kind of segueing into different elements here. So let's just break this up into another part, and then we'll continue. So let's stop now, and we're going to pick up. And then when we pick up, we're going to talk about RC, RL circuits. We're going to talk about the reactance, all right? And do some calculations and run through some examples, which will be fun. Then after that, then we're going to generalize this into what's called impedance, and then we're going to, and impedance are based on complex numbers. We're going to generalize it a bit into impedance, and then that's going to help us finally with filters. But anyway, so take that in, and I'll meet you in the next lecture, and we're just going to kind of continue with this, but we're going to do some examples. But this is a good place to stop for now, and then we'll pick it up in the next part of this lecture. Okay? All right. See you then. Bye. All right, welcome back, and we are on the next part of this lecture. So we're just continuing on here and talking about, if you take a look at the screen, this is what we were talking about last time. We had the capacitor, we had the inductor, and we were showing the reactance on the phasor diagram here. And we had x of L, going upward in the vertical direction and X sub C going down, and then we had the resistance to the right here. And so let's keep talking about this. And now what we're going to do is we're going to kind of generalize this a little bit. We're going to add some more math, but it's really easy math. And I know I keep saying this isn't a math class, but believe me, this is not a math class. This is most of this is just, it's mostly arithmetic, right? And maybe some algebra here and there, but mostly just arithmetic. But again, it's needed to understand what's going on. And then once we understand everything, then we can kind of forget about it. But we need a little bit more math to help us describe things, and I'm going to show you why. All right, so what I'm going to do now is first, let's make sure here that we remember a couple things. So remember X sub C, which is the capacitive reactance, is 1 over 2 pi fc, or 1 over omega c, where omega is the angular velocity, which is equal to 2 pi f, right? And the inductive reactance is 2 pi FL, or just omega FL, right? And then when we draw it on this phasor diagram, which is just a representation to show the relationship between resistance, inductance, and capacitance, we draw it like this, where the resistance is on the 0 axis here. And the reason why is because the current and the voltage in the resistor are always in phase. Then what happens is in the inductor, for example, and if you remember, let's put our little thing here. So for the inductor, we have LE, right? And then for the capacitor, we have ICE. So for the inductor, voltage leads the current. Voltage leads the current. So that's why we have X sub L up here. So this voltage right here is leading the current, which is at the 0 degrees, because in the resistor we know that the voltage and current are in phase, and we're going to just call that 0 degrees. So the inductive voltage here, if we were to draw V sub L, it's 90 degrees ahead or leading. Then on the capacitor we have current. Current leads voltage, or we could say voltage lags current, and there's our voltage for our capacitor, and it's down here, and that's at minus 90 degrees, right? And that would be V sub C, the voltage over the capacitor. All right, so the information that we have now, we can actually solve a lot of problems, but we're missing a little bit of math that'll make things a little bit clearer as we go. And so we're gonna kind of go through a couple problems, and we're going to look at how we might need something else, and then we're going to learn what that thing is. Now, before I erase this, I want to talk about one thing, and that is we've been using the word resistance for this resistance, and then we've been using the word reactance for the capacitive reactance, which is the resistance to AC, and we've been using inductive reactance for the resistance to AC in the inductor. In general, this whole concept of resistance falls under what's called impedance. Impedance, okay? And the word impedance means to resist current flow, for a component to resist a current flow, which has both a resistive and a reactive component. So it includes both a resistive and reactive component. So in the resistor, it's purely resistive. In the inductor and capacitor, it's purely reactive. Both of those are impedances. They just so happen to be 100% reactive in one case and 100% resistive in this case, right? But the word impedance, typically we use the word impedance when we're describing AC circuits or circuits that are not working at DC. However, so if DC is here, and this is 0 hertz, and over here is infinity hertz, right? Somewhere in between here is kind of where all the signals exist. So if we talk about pure resistance, we're always talking about DC. But if we're talking about impedance, impedance includes DC, right? That's just a signal with 0 hertz. So a lot of times you'll find electrical engineers talk about just the word impedance in general, even when they're talking about DC. So I myself, I'll just always say, impedance, because then I know I'm safe. I know that if there's a resistive component and a reactive component to the overall resistance, I'll be safe if it's at DC or if there's a signal going through it. But if I just say the word resistance and there's a signal, an AC signal, that is incorrect. But if I say impedance, I'm always correct. All right. So impedance, and come over here. So impedance, we use the letter Z. All right, we use the letter Z to represent it, and we're going to learn this in a little while, but right now, impedance is composed of two different components, right? And it's composed of a real part plus an imaginary part, which we're just going to call this X for now, times the imaginary number J, or this is I. If you're a mathematician, it's a J if you're an electrical engineer. So, so this is what EEs call it. And this is what math people call it. They call it I. Either way, this is an imaginary number. So what we're going to learn is, and we're going to just hold off on this just a little bit because I want you to see why we need it. So if you look at this phasor diagram right here, we have this resistance here, and it's on this axis here. This you could call this the x-axis for a second at 0 degrees. Then we have this inductive reactance. Then we have this capacitive reactance here, and they're always 90 degrees away, rotated. So if we were to label these two axes, right, we could label this X and we could label this Y. We could think of X sub L and X sub C and R as a vector with two components, an X component and a Y component, right? So you could do that. But in electronics, what we think of this as the real axis with that funny R, right? And we think of this as the imaginary axis. So we have to do all this with complex numbers. So we have to first understand imaginary numbers, and then we use imaginary numbers and real numbers to form complex numbers. So we're going to get to that in a minute. If you did imaginary numbers, everyone learns imaginary numbers, I think now in junior high school. High school definitely, if you take a trig class, I would imagine. But if you go through college, there's no way to avoid imaginary and complex numbers in at least one class. You may have forgot them or may not understand them, but I'll show it to you. And I don't even really want to get into it right now, but it's not that hard. And it's just the mathematical notation and a tool to be able to separate the real part, the resistive part, and the reactive part so that we can keep them separate and not mix them up in our calculations, all right? And then we're going to get a more advanced way of representing these polar values, these phasors, and so forth. But just right now, just kind of hold that idea. So impedance is the generalization of resistance and reactance together. So something can have both resistance and reactance. We call that impedance. It goes from DC to infinity. The symbol for impedance, we use Z's, and then it's the combination of the real part or the resistive part plus the imaginary part, which is the reactive part. And remember, reactive or reactance in general, you're never going to dissipate power. You're either charging a capacitor or energizing a magnetic field, but what goes in comes right back out in a perfect capacitor, perfect inductor. Okay, so just hold on to that for a second. Now, with what we know, can we solve some circuits and have some fun? Let's find out. I don't know. Okay. So, all right, so let's go ahead and let's do an RC circuit. So let's do some kind of RC circuit with AC, and let's see what we can figure out in this thing. All right, so let's have some fun here. So, so let's go and let's draw an AC source, and let's say that this is 10 volts. And remember, when we're saying the 10 volts, we're either meaning it's root mean square or it's the peak. So let's just call it 10 volts RMS for now. All right, just use that. We'll use that kind of convention. It's usually RMS unless we'll state otherwise. So we've got 10 volts, and let's say what its frequency is. Let's for fun here, let's say it's kind of an audio frequency, and let's call it, say, 1,000 hertz. Okay. Most of the time when people do these experiments, everything is always AC voltages and frequencies. So let's change it up a little bit. So 1,000 hertz is a pretty high tone. It would hurt your ears. All right. And then let's put it through a resistor. And let's put it through a capacitor. Okay. And all right. So we're going to get a current flowing here. Right, we're going to get a current flowing here, and the current's going to flow this direction, and then it's going to flip back, and then it's going to flow this direction, right? Okay, so we know that. So I'm just going to generalize it now and just talk about one cycle, and the current is flowing that way, and we can just call that current I. All right, and we've got this 10 volts over here, and let's just call that, we're going to call this V source. All right, it's 10 volts at 1000 hertz. All right. Now we've got this resistor R, we've got this capacitor C. Again, let's just come up with some values here that aren't too bad. So 10 volts, so why don't we set R equal to, say, 100 ohms, and we'll set the capacitance equal to something reasonable, but not too easy, so we get some numbers that aren't all multiples of 10. How about 2.2 microfarad? All right. Now, let's do one little thing here. So if I tell you that we've got the voltage source is 10 volts at 1000 hertz, right? So this is a frequency, right? F equals 1000 hertz. How would we write that, right? And I want to make sure we know how to do this. So V of S sub t, right, equals, this 10 volts is the root mean square value, right? So it was something times 0.707 equals that. So 10 volts times the invert of 0.707, which is 1.414, times 10 volts would actually be the root mean square. So if we wanted to write this, we should write this like this. So we'll write 10 volts times 1 over the square root of 2, which is, I'll tell you, is 1.414. That'll give us the right number and sign, and then it's just 2 pi, what's our F? 1000 hertz, right? And then right now we're not going to worry about this phase angle business, so we're just going to say it's 0 for now, all right? And so this is what, if you wanted to write down the mathematical formula for what this this generator, this voltage generator, would look something like this. Okay, so here we go. All right, so let's figure some stuff out. So the first thing we know is we have reactance and we have resistance in the circuit. All right, so let's go ahead and let's draw our phasor diagram. Why don't we draw it right here? So we're going to draw this like this. Okay, and these are, and remember this is a kind of a circular axis where we've got an angle and a magnitude. All right, so the first thing we're going to do is we're going to draw the resistance, and we'll draw the resistance here. Why don't we draw, let's draw the resistance, and sure, we'll draw it in, let's draw it in, we had it in green last time, huh? So I kind of like that. So let's make this yellow. You know what, let's just erase that, and we'll make that, you know what, let's make it this color. Sorry, all these color decisions make life difficult. Okay, so, all right, so we're going to draw the resistance. So this is the magnitude of the resistance right here. So this is R, right? And that's drawn in green. All right, and then on the vertical axis, we're going to draw our impedance or our capacitance. And which way does this go? So remember, the capacitance goes down, so it's 90 degrees down. All right, and this is our X sub C right here. And we have no inductance inside of this. All right, so and the reason why we draw it down is because we know that in the capacitor, if we write our little formula down here, so what is it? It's ICE. And that says that current leads the voltage, or voltage lags the current. So voltage lags the current, and so in the resistor, we know that the current and voltage are in phase at 0 degrees phase angle. So the capacitance, the reactance, we draw it down here, and that would also give us a voltage phasor that would go down, and then the voltage phasor for the resistor would go to the right here. Okay, so now we have this phasor diagram. So, you know, what do we do with this? All right, so first let's do some math up here and just get some answers. So let's compute the capacitive reactance, right? So that's 1 over 2 pi FC. All right, so everybody get out your calculator and let's do this. All right, so 2 times pi times the frequency, 1000, times our capacitor, which is 2.2 to the minus 6th. Take the invert of that, and we get 72.34 ohms. All right, 72.34. Now, when you're doing these calculations, you can either round things off or, you know, or not. So we'll keep things at 2 decimal places just to do it. But in reality, You don't really need to do this for these simple calculations. The tolerances of these components would be 5 or 10%, and so I would personally just round these things up or down. So in this case, I would just call it 72 ohms and be done with it. But we'll just keep the decimal places for now. All right, so that's 72 ohms. Remember, that's reactance, right? But it is still measured in ohms, and we know the resistor is 100 ohms. Okay, so now let's go down here and let's write what these values are. So the capacitive reactance is 72.34 ohms, and the resistor is 100 ohms. Okay, now what we're going to do is we need to find the total impedance in the circuit, and the impedance is both the resistive component here, right, and the reactive component here. Now, we don't know how to use complex numbers now, but I'm going to show you how we can find the magnitude of the impedance, just the magnitude. If we can find just the magnitude of the impedance, we can actually get some work done. So let's just figure out what the magnitude of the impedance is. So let me show you this. So we've got a triangle here, right? And if we wanted to compute what the hypotenuse of the triangle is, in other words, if we're going to add these two vectors together, right? What you would do is you would take this, this guy right here, and you would move it over here, right? Remember that? And so we would just kind of put it right here, make a copy of it, and then we would go ahead and we would draw like this. And so, so this is x of c here as well, right? And so what we want to find is this hypotenuse, which we're going to call z, and this is the total impedance. But this is just the magnitude of it, right? Notice we're not figuring out this angle yet. All right, so how do we figure this out? Well, it's just the Pythagorean theorem, and that means that z squared equals r squared, right? R squared plus x of c squared. In other words, z, or we could write that z equals the square root of r squared plus x of c squared. All right, so let's plug these values in here. So where is r? R is 100 ohms. All right, so that's 100 squared. And what's x of c? 72.34. 72.34 squared. Again, let's get our calculator. And depending on your calculator, be careful you don't do things in the incorrect order of operations. So what I'm going to do here is I'm going to say 100 squared plus 72.34 squared. I'm going to find the answer. Then I'm going to find the square root, and 123.42. So 123.42. And again, this is measured in ohms, and this is Z. So this is what the impedance of the circuit is. This is the total impedance. However, notice there's no phase angle in here. There's nothing like that. This is only the magnitude of the impedance. And this kind of analysis gives you magnitudes. It doesn't so much give you angles between things. And we know there are phase angles going on here, but this is still good work, and this can help you figure things out. All right. So we know that Z is 123.42, and we can just put that 123.42 ohms. All right, so we have all the different sides of this, and so now let's go back and let's look at Ohm's law. All right, so Ohm's law, let's just put it up here, and that says that V equals I times R. All right, so now I'm going to also tell you that V also equals I times Z. Okay, so we can generalize this and say V equals I times Z. All right, so we know what Z is. That's that 123.42. We know what V is. V is just the magnitude. It's just 10 volts, right? And we want to compute I. So let's go ahead and let's figure out I. So let's go back down here and let's figure out I. So I equals V over Z, right? V over Z, which, what's our V? It's just 10 volts. What's our Z? Where did Z go? 123.42. 123.42 ohms equals, and let's figure this out, 10 divided by 123.42 equals 0.081, so 0.08, let's just call it that, amps, or actually we could put this in milliamps, and we could say it's 81.0 milliamps, whichever one you like. All right. So that is the current. Now, what kind of current is that? That's an RMS current because we've got an RMS voltage. So that's the current in the circuit. Now, what do we always know? We always know that no matter what, the current and the voltage are always in phase in the resistor, and they're always out of phase in the capacitor by 90 degrees, right? But the total, so the source now, the source, it's going to have a current and a voltage, right? It's going to have a current and a voltage, and we can compute what its phase is, all right? So now we can do that by going back to this phasor diagram here, all right? And so what we want is we have this Z here, which is this hypotenuse, and we want this angle in here. This is actually this phase angle, and this phase angle here tells us about the angle between the impedance here, the Z, and X sub C and R. So we can figure out a number of different things here, right? So now the first thing is what we can do is we can either do it from this diagram here, or we can make another diagram, all right? And we can do kind of the voltage diagram to do this computation. Either one will work, all right? So let's actually draw another one, all right? And because we're not talking about impedances right now, we're talking about voltages and currents, all right? So, okay, all right. So now, now what we want to do is we know what the current is here, right? We know what the current is. We know what the impedance is of the circuit, of the total impedance of the circuit is, all right? And so what we want to do now is, and there's lots of ways we can do this, so what we want to do is let's figure out what the voltage, the magnitude of the voltage over the resistor and the magnitude of the voltage over the capacitor is, all right? So let's figure out those. So I want to figure out, let's call it V sub R, all right? And V sub R, it's just going to be the current times the resistance, right? So I, which is 81 milliamps, so let's just put it as 0.081 amps, and then times our resistance, which is 100 ohms, times our 100 ohms. All right, so let's do that. So we get 0.081 times 100. Just going to move the decimal place a couple times. So we get 8.1 volts. All right, now let's figure out V sub C. Again, that's going to be the exact same thing. It's going to be the current, which is 0.081 amps, times the capacitive reactance, which is 72.34, right, which is 72.34 ohms, all right. Again, 0.081 times 72.34 equals 5.85, all right. 5.85 volts. Okay, first thing I want you to look at here is 8.1 and 5.85 definitely do not equal 10. So the two voltages do not add up to 10, right? Why? Well, because these voltages are out of phase with each other, right? And because they're out of phase, they don't add up. Just by magnitude. The phase is important, and we're not writing down the phases of everything yet. So that's why they don't add up. So you got to be very careful. All right. But we can go over here and we can draw what's going on. So first, let's draw the voltage of the resistor. All right, so I'm going to put the voltage of the resistor here, and I'm going to put that in red here. So this is VR right here. All right, voltage of the resistor. And the reason why I'm putting it there is because we know that the voltage in the resistor and the current in the resistor are in phase, and we're going to call that 0 degrees. We're just going to call that 0 degrees, all right? And that's kind of our reference. All right, now what we're going to do is we're going to put the voltage of the capacitor. That's 5.8, all right? And again, we know that the capacitor is going to, the current in the capacitor is, and the voltage in the capacitor is going to lag the current by 90 degrees. So it has to be right here. All right, it has to be right here. Okay. All right, so this is the voltage in the capacitor. Okay, so now what are these values? So voltage in the resistor is 8.1 volts. Voltage in the capacitor is 5.85 volts, 5.85 volts. And now notice these two diagrams are equivalent because they're only scaled by the resistance, right? That's really what's going on here, but this is kind of more what we're trying to figure out, so we're just going to kind of go with that. Now, I think you can see that if I just do this kind of construction and I draw this, right? I can do this. Now I can figure out what this, here are these two voltages. I can figure out what this VS here is, right? I can figure out what this VS is if I want to. So VS, let's figure that out. So VS would equal the square root of both of these things, right? Which would be 8.1 squared plus 5.85, 5.85 squared. So let's do that. So 8.1 squared plus 5.85 squared. Remember, we're going to start losing a little bit of accuracy because we're rounding things a little bit. And if you do this, you get 9.99999. So, but we're going to call it 10 volts. And lo and behold, it is the 10 volts. So this is correct. So we're doing everything right. But what do we really want? We want this interior angle here. We want to know what is the angle between this this vector right here, which is the source voltage, and this vector right here, which is the resistive voltage. And we know that the current in the resistor is in phase with this. So this can tell us what the phase angle between the current and the voltage is, okay? There are a lot of ways to figure this out, right? So we have everything here. We can use sine, cosine, and all that. So one thing we can do is we can use the tangent function. So we can say that phi equals the inverse tangent of what? So tangent is opposite over adjacent. So the opposite would be v sub c and adjacent would be 8.1. So we could do that. So it would be the tangent of what? V sub c over v sub r. That would tell us what phi is, right? Okay, another thing that we could figure it out is we know what this z is now, right? This hypotenuse, right? So if we look at some sine and cosine, let's look at cosine, for example. Cosine is kind of my favorite trig function. The cosine of theta, so cosine of theta is adjacent over hypotenuse, right? Adjacent over hypotenuse. So that would be VR over VS. That would be VR over VS. So therefore, phi would be the inverse cosine of VR over VS, right? And then sine of phi is going to equal opposite over hypotenuse. That's V sub c. V sub c over V sub s. So that phi would equal the inverse sine of V sub c over Vs. So whichever one of these you like, most people will use this right here, the tangent function. Okay, so V sub c, what is it? It is, let's first get tangent here going. All right, and then we want 5.85 divided by 8.1, 8.1. All right, and my result is 35.8 degrees and some change. So phi equals 35.8 degrees and some change. So that's the phase angle phi. Now, let's be careful and make sure we understand what this means. So phi is this phase right here. All right, and so this is telling us that between the source voltage, right, between the source voltage and the current, right, there is a 35.8 degree lag here, because we know that the current is here at 0. So we can say a couple of different things. So that we can say one thing. So if we look at the source voltage, right, and we want to talk about that relative to the current. So if we call the current phase angle 0 in the circuit, then the source voltage is lagging by 35.8 degrees, right? Because it's falling back here, because this is a capacitive circuit. So in capacitive circuits, you're going to get a lag of voltage, right? You're going to get a lag of voltage, right? Now, and it's always going to be between 0 and 90, right? Okay, but if we want to talk about the voltage as the reference, and a lot of times that's what people will do, they'll say that this is the reference, 10 volts is the reference. So if we want this to be the reference, then the current would be leading by 35.8 degrees, right? So however you want to do that. So again, it depends on what you want to pick for a reference. If you want current as your reference, you want to set that at 0 degrees, right? Then we have the voltage, which is lagging because it's down here, right? It's reactive capacitive. But if we want to just say we like our source to be the reference, that's what we're going to reference everything to, and we're going to say that we're 10 volts, 1000 hertz, and this is actually, we want this to be 0 degrees, that means that if we want to talk about the current, we're going to change the phi in the current, and we're going to say that the current is leading by 35.8 degrees. Okay, so we figured out everything here. So we figured out what the voltage is in the capacitor, the RMS voltage. We figured out what the voltage in the resistor, 8.1. We figured out what the current is in the circuit someplace here. Yeah, 0.0, where is it? Right here, 81 milliamps, right? And again, that's RMS current. We figured out what the phase angle between the voltage and the current relative to the source is, right? And now we have to be careful. The source, this is talking about the source angle, okay? But the current, and this is super important, the current and the voltage in the resistor is always in phase, 0 degrees angle. The current and the voltage in the capacitor is always out of phase by 90 degrees. Always, always, always. The overall circuit now, the overall circuit, the current and the voltage are out of phase by 35.8 degrees relative to the source. But if we compute the phase angle in the capacitor or in the resistor, they will actually be 0 degrees here and 90 degrees here. The problem is this math doesn't give us enough latitude to do that exactly. We need another tool, and we need to kind of formalize the idea of phasors with angles and a complex impedance so that we can write these things down and keep these numbers. See, we've been working all in magnitudes here, right? And what we want to do is we want to keep the real part, the resistive part, and the reactive part separate. And to do that, we're going to write impedances Z as a function of R, the resistive part, plus X, the reactive part, and then times the imaginary number J. All right, so this is what we're going to do. So anyway, so this is kind of showing this example with the capacitor, and we could do the exact same thing with the inductor. It would be the exact same. The only thing that would change is instead of capacitive reactance, we would do inductive reactance, and all this math would be exactly the same. What would change, though, is down here, instead of V sub C and X sub C pointing down, we would have, what would we have? We would have the V sub L pointing up, and then we would have, let's use a different color, we would have the X sub L pointing up, right? And then now what would happen is this phase angle would flip, it would become negative, right? So now it would flip, and then we would have the voltage leading the current in the circuit, right? And that's about it. So again, capacitors and inductors are just analogs, and they just kind of do the opposite things, you know, very, very, very cool little devices. All right, so let's take another pause here. This is another big chunk. We're doing this as a multi-parter because there's just a lot of stuff, and I kind of want to keep breaking it up into pieces. So now let's take a pause here. We're going to come back, and now we're going to move into phasors that have complex. We're going to deal with imaginary and complex numbers and complex phasors and complex impedance, and kind of formalize what we're missing here so that we can do this stuff a little bit differently and generalize it. All right. So meet me in the next part of this lecture, and we'll talk about that. All right. Bye. All right, welcome back, and we just took another pause. We're kind of breaking this big lecture up into parts here so that we can make them semi-bite-sized. So looking at the screen, that's where we left off, all right? And so what we kind of came to the conclusion of was that we can do these computations. We can figure out what the total impedance Z is, right? And then we can figure out the currents and the voltages and all that. But what we're kind of missing is we are computing magnitudes with all these values. We're computing magnitudes. And because we're doing that, we're kind of throwing away the angles. And what we want to do is we want to maintain that information or be able to do that if we'd like to. And so what we're going to learn about are, we're going to learn about phasors with both polar and rectangular representations, and then how to manipulate them, and then how to add them into these circuits and represent the components and the voltages and the currents in one uniform mathematical notation. That'll make everything nice and easy to compute. And we can always go back to that if we want, or just go back to the simpler format. But we need to kind of take a look at this because it's going to help us with something else. All right, so first let's just get rid of this. All right. Okay, so let's go ahead and let's talk about a couple things here. So first, let's talk about imaginary numbers really quick, right? So imaginary numbers, all right? And again, I don't want to make this a math class, so we don't need to go into the theory behind the math. We just want to kind of know the math enough so we can manipulate it and then use it. So imaginary numbers, if you recall this, so if you have the square root of -1, this is called I, the imaginary number I, all right? And then electrical engineers will call this J. J is the square root of -1. It's just a notational thing. And the reason why that we like to call it J is because I is for current, and so it gets kind of confusing, so we'll typically use J. So if you see that notation, it just means the same thing. All right, so I equals the square root of -1, and then that's that. So it's not imaginary. It's it's an object, and you can manipulate the object, and there are lots of rules to the object. So for example, if we have I squared, that equals -1, all right? And so you can start manipulating i's based on the square root of -1, but you have to be careful of the radical sign, and some things will not come out to the way that you would imagine they would. So you have to be careful of that. So what's best to do, if you want to know all the different rules, we can, you can go to any math book, but if you go into Wikipedia here and look under imaginary numbers or imaginary unit, and we can kind of see some of the stuff here. So like I said, I squared equals -1, and then you can see, you can start playing around with multiplying them and whatnot. And then over here, here's kind of these powers of I. So anything to the 0 is 1, I to the 0 is 1, I to the 1 is I squared is -1, then I cubed is -I, and then these repeat over and over and over. All right, so you can see I to the 4th is back to 1, and so on. So the couple interesting things to pay attention to, I to the -1 equals -I. This is kind of useful right here, right? I to the -1 equals -I. So the other one that we like here is I to the -1 equals -I. So what this means is if you have 1 over I, you can recast that as that. All right. So that's basically it. And so that's what I is. So now why this is important is because we want to represent our impedance, and our impedance looks like this. It looks like Z equals a real part, right? And for now, we can call the real part R, not for real part, but for resistance. So the resistance is kind of the real part. And then we have a reactance, which we're going to call X. And then we put a times J here. So what this means is because we're multiplying the reactance times J here, that puts it into a different axis, or if we were to represent this as a two-dimensional plane. So if we were to come here and do something like this, all right, and we could make this the real axis. Okay, so in this case it is the real axis, and this is the imaginary axis. And again, we would also call that J. All right, so this is plus R, this is plus I, this is minus I, and this is a coordinate system just like anything else. All right, and then this is minus the real part here. So whenever we have a number, whenever we have a number or a complex impedance like this, so it has both the resistance part and then the reactance part, or we just want to represent what are called complex numbers, they have two parts. They've got the real part and the imaginary part. So if we're just representing complex numbers, they don't necessarily have to be impedances. They could just be anything. So if we come over here and we say something like, say we've got a complex number, and a lot of times we'll use A star to represent a complex number, and this could be A plus B times, and we can use J here, or we can use I, but we'll just use J. And we might say that B star equals, and let's do this actually, we'll say that, how about, I want to keep the notation the same. So let's say that A star equals, let's go ahead and do that. We'll say it equals A plus B times J, and then we'll say that B star equals C plus D times J. So these are two complex numbers, and the reason why they're complex numbers is because they have both a real part and an imaginary part. And the imaginary part is the B and the D, and the real part is the A and the C. So we can think of these as existing in this two-dimensional complex plane where the x-axis is the real axis and the vertical axis is the imaginary axis. So again, there's nothing imaginary about it, and there's nothing complex about it. It's just they're called complex numbers. That's all, no big deal. So we can plot points on here exactly the same way we would if it was an XY coordinate system. So really, complex numbers, you can map them vectorially to the X and Y plane just as easy. But because when we're doing electrical engineering, they actually represent real and imaginary components, it's better just to use the real and imaginary axis and call them complex numbers and not call them vectors in X and Y. All right, so anyway, so then the question is, so we've got a number, a complex number, and how do we add these things, right? Well, if you want to add these are pretty easy to add. So A star plus B star equals A plus C. You add the real parts plus B plus D, and then times J. So you just add them just as you would imagine. Now, multiplying them is much more complicated, right? But you can just use their definition. So A star times B star equals A plus BJ times C plus DJ. So we've got to multiply these step by step here, right? Just like you would. So we have to distribute the A over this term and then distribute the B over this term, right? So it's simply like this, right? Just like we learned in elementary school. Same thing. So the product is, so we have A times C. So we have A times C. And then we've got A times DJ. So we've got plus A dJ. So that's an imaginary component. Now we have BJ times C. So we'll say plus BCJ. We'll kind of collect the terms in order. And then we've got BJ times DJ. So plus BDJ squared. All right. So now let's write this out. So we have AC plus ADJ plus BCJ. So can we just add those together? So let's just say that's AD plus BC times J plus this term right here, wait a minute, this J squared, it's the same as I squared, right? J and I are the same. It equals -1. So this really means -1 times BD, which equals, so this is a real part here, so this really equals AC minus BD, that's the real part, plus AD, this part here, plus BC times J. If I didn't make a mistake, if I did, sorry, but you get the point. You just distribute it over there and that's it. So this is kind of laborious, where addition is very quick and easy. This is laborious to do this. Now, that said, there's another representation that we can represent these numbers in. So this is in rectangular form. So we have this A star is A plus BJ. So what does that mean over here? If we were to draw this, we would say this. We would come out over here, and let's say that this is A on the real axis, right? And then we would come up here, and then this is B on the imaginary axis, right, which is the I or J axis. And then our final vector here, our final complex number, right, is this right here, is this A star. Then same thing here, if we have this B star, and if we were to draw another vector representing that, maybe we can draw it in purple. And I'm not doing this to scale or anything, so I don't know what it'll end up looking like. But this is C for the real part, so right here would be the real part, right? And then really there's projections down here, right, like that, and then projections over here like that. And then The imaginary part is D, so we kind of come up here and there would be our D, right? Then if you wanted to add these two things together, right? So the sum of these two things is just this result right here, right? Right. Let's do a different color. The result of these two things, if we add these two things together, what we need to do is we need to put them head to tail, right? So if we put them head to tail, so we're going to take this vector right here, and we're going to try and put it like that, right? And then the resultant vector would be this one right here. All right, so that would be the same as the sum right there. All right, so the rectangular version of it is very useful because we can clearly see what the real part is and the imaginary part. In this case, if it was an impedance, we can see what the resistance is and what the reactance is, and that's kind of what we want to use this tool for. But it's a little bit hard. There's another format, called the polar format. All right, and so let's kind of do that right here. So this is rectangular format complex numbers. So now let's take a look here again. So here is our coordinate system again. All right, and again, this is going to be the real axis here. Let's draw that a little bit better. All right, so this is the real axis here, plus and minus real axis, and then here's the imaginary plus I up here and minus I down here, or J, whichever way you want to represent it. All right, so now let's go ahead and let's draw a vector here. We'll draw it in, how about red? All right, so now say that we have a complex number, all right, and we've got A, we've got B, so we'll just call this, C star right now. And let's see, A, B, C, D, and let's just say for fun it's E plus F. In this case, since we're using I's here, we'll say I, right? All right, so the real part is E, the imaginary part is F. All right, so if we drop this down here, on the real axis, this must be E, and then on the imaginary axis, this must be F. Okay? So given that right there, we can talk about a couple things. The first is the length of this, right? So now we can see where that length comes in, or the magnitude. When we were computing the impedance in the last lecture, we computed the total Z, we computed its length, but we kind of threw away the angle. We could recompute it, but we didn't keep it. We just kept the magnitude. So the magnitude, or the length here, of C here, so if we come over here and we want the magnitude, so if we said, what's the magnitude of C, and these two bars mean the magnitude of it, right? It's just the Pythagorean theorem, right? So it's going to equal the square root of the square of the sides. So that's just E squared plus F squared. So that's the length of this right here, right? So that's the length of it. So we could come back here and we could say, C star, and we could put length here if we want, right? And put the bars around it. That's its length. All right. Then if we want this angle phi here, right? So the angle, there's a lot of different ways to figure this out. So we know that the tangent of phi equals the opposite over the adjacent. Well, here's the opposite side here. That's just F, okay? And the adjacent is just E. Therefore, phi is the inverse tangent of F over E. All right, so that's it. So now that we have these two pieces of information, we have the length and we have the angle, what we can do is we can write these complex numbers in this polar or phasor format, right? They're the exact same thing, but they're just in the other format, all right? So let's go ahead and let's erase all this, all right? And so now we have something like this. So we have in rectangular format, so let's go here and let's say that we have our A, and I'm going to get rid of these stars if it's okay. We know what we're talking about here. So I'm going to say the complex number A is composed of A plus B times J, and it could be I also. So there's one complex number. And then we've got this other one, big B equals C plus D times J. So both of these are in rectangular format. And then if we come over here, right, so this is the plus J, this is the minus j or I, right? And then this is the real axis here. And I've never really figured out a good way to draw this real symbol. There we go, that's not bad. All right, and then so go like that and go like that, minus, and then we can plot these things here again real quick. So we got a plus v, so if we wanted to plot a, here would be a here, and then b would be right about there, and then we would say that here, right, this would be a, so this is the complex number a. All right, now, and there would be phi. All right, so we can't really tell what this angle is from this rectangular format, but if we do the math, we can, and we know that phi, we just on the other page said that it's the inverse tangent or the arctangent of the opposite side, that would be b over a. So it's as simple as that. All right, so given that format, we can write that in a compact form. So we can say that the polar form or the phasor form, all right, is this length here. So the length of A, right? So I'm going to put the length of A, and then we put this little angle symbol, and then we put phi. So that's the polar phasor form. And then remember that the length of A is just the length of it's the hypotenuse, right? So the length of A is simply the square root of little a squared plus b squared. Okay, given we have this format right here, all right, and so I'm going to put a little phi1 there. All right, and so if we were to figure out what the phasor or the polar format of this one would be, it would just be this. We just call it B, and let's call that phi2. All right, so what that would look like is, if we were to draw, let's draw something here so we can kind of see it. If we draw another vector here, all right, and then C and D, so here would be C, and then here would be D, and then we would have this angle here, and then that would be our phi2, and then here's our phi1, is this one. So we've got two vectors or two phasors. Each has an angle with the real axis, which we're always kind of calling that 0 degrees. Each has an angle with the real axis. Each has a length. We can compute the length by taking the square of the components, the rectangular components, and then finding the square root just by using the Pythagorean theorem. And then we end up with these two formats right here. Now you might think that's a lot of work, but a lot of times things will start off in this format where we'll know the magnitude of something, and then we'll know the phase angle, so it'll already be in this format. All right, so once we have this format, now watch what interesting happens here. So if you want to multiply two phasors together, if you want to multiply two phasors, so again, so let's say that, again, we can say that this is A and we can say that this is B, right, but in polar format. If we want A times B, we want to multiply those. Maybe we have like V equals I times R, right? And so maybe we want to compute R, and that would be V over I, and maybe V and I are both in phasor format, right? If they're in phasor format, then multiplication and division is what we want to do. So check this out. So this is kind of cool. So A times B equals this phasor or this polar version of the complex number times this one. And how you compute it is simply like this. It's simply A times B. So you just multiply those like you would. And then here is the fun part. It's just phi1 plus phi2. So in the polar coordinate system, or in the polar domain, when you multiply phasors, you simply multiply their magnitude and add their angles. All right. When you divide them, so A divided by B equals the magnitude of A over the magnitude of B. And now the final angle is phi1, the top, the numerator, minus phi2. Again, really, really easy. So you remember the multiplication was really complicated when you have rectangular coordinates like this. Division is way worse, right? But here it's super easy. It's just you multiply or you divide and then you add or you subtract. So a lot of times what we'll do is we'll go from one format to the other so that we can do the computation easier. So the conversion is rather easy, and then it makes the computation easy, and then we can just go back to whichever format that we want. All right. So there's uh, rectangular format, and then polar or phasor format. And the whole point of this is just so that we can represent complex impedances. All right, and then now that we have this mathematical tool, what we can do now is we can talk about everything as a complex number. All right, so it can either be a voltage, a current, or it can be an impedance. And all of those can be in this one mathematical notation. And what's nice about it is that when we have things in this format, so again, we have this A equals little a plus B times J, it keeps them separate. So no matter what, we have this complex number here. We know that this is always the real part. We know that this is always the imaginary part. When we multiply, divide, subtract, add, always the result, this will always be the real part, this will always be the imaginary part, and they never get mixed up. And the reason why they never get mixed up is because on this coordinate system, these axes are perpendicular. All right, and so because the axes are perpendicular, the coordinates will never, commingle. They'll always stay completely separate. All right. So, and of course, this works in higher dimensions, 2 dimensions, 3 dimensions, n dimensions, or whatever, and that's why you can have unique coordinates in 2D and 3D and ND spaces, because you can keep them separate. But instead of calling it an x and a y, we call it a real axis and an imaginary axis. And because we're talking about complex numbers that are representing complex impedances or voltages or currents. Okay, and we want to keep the math consistent so we don't have to kind of fudge it like we did in the last section where we're kind of computing magnitudes only and we're throwing away these angles. All right, so let's do a couple examples. All right, let's just do a couple examples here, and just do some concrete stuff here so that we can see what's going on. All right, so why don't let's do one, let's see, just A equals 3 plus 2J, and let's have D equals minus 5 plus 10J. All right, so let's do a couple things here. So first, let's add these up. So I want to know what is A plus B. All right, I want to know what the length of A is. I want to know what the length of B is. I want to know what the angle is for A and B. So let's go and we can call this phi A. I want to know that. I want to know phi B. All right, and then I want these to be both put into polar format or phasor format. So I want, the phasor format for A and for B. All right, and then I want to multiply AB in phasor format. Okay, in phasor format or polar format, same kind of thing. Okay, so let's go to this. So first thing is, why don't we let's kind of draw these here. So let's draw this stuff over here a little bit, and all right. And again, we're just kind of making this up, so things are usually going to not be to scale. So let's do A first. We'll do A red. All right, so this is the real axis here. So there's real, here's minus real axis. Up here is the plus J imaginary axis, and here is the minus J. All right. All right, so it's 3 plus 2J. So we'll go out here, 1, 2, 3. And so that's the real part, and then 2J, so up 2, like that. All right, and so here would be our final result. Just kind of go like that, kind of go like that, and there we go. That's all there is to it. That's A. All right, and then now B is minus 5 plus 10J. Okay, so it's minus 5. So, 1, 2, 3, 4, 5. All right, so that's minus 5. We can put the 3 here if we want. We can put the minus 5 here if we want. And then it's 10 in the positive J-axis, in the imaginary axis. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so it's up there pretty good. So we can go ahead and we can extend this a little bit. Okay. All right, and let's go ahead and let's draw that one. We'll draw that one green for B. All right, so it was 5, and here was our 10 right here. All right, so here we go, and we'll put that like that. All right, so kind of put this here, like that. All right, and we're going to try and draw a straight line. There we go. All right, and so that is B right there. So we've got B and we've got A. Now, we've got these angles that we're concerned about, phi A. So over here, this interior angle right there, that would be phi A. And then now let's be careful. The angle for phi B, it's not this angle. It's not this one. It is this this angle here. It's this larger angle here, right? Phi B. Okay, so we want to compute these things. All right, so the first thing is let's go and find the length of each. All right, so that's easy enough, right? So we're going to find the length of A here. So the length of A, and that just means the length of this hypotenuse right here. Well, that's just the square root of 3 squared plus 2 squared, right? 3 squared plus 2 squared, all right, equals, and so that's 9, the square root of 9 plus 4. So we've got 9 plus 4 and 13, take a square root of that, and it's roughly 3.6. And again, most of the time we're going to be representing impedances and voltages and currents, so we don't have to be super accurate, but 3.6, that's length of A, all right? So that would go up there. And then now we've got our length of B, same thing. What are B? Minus 5 plus 10, so again it's minus 5 squared plus 10 squared, square root, all right? So what does that equal? So that we've got 5 squared, all right, plus minus 5 squared, right? And it'll always be positive, obviously, plus 10 squared, all right, and take a square root. And, you know, and again, obviously we can square 5, that's 25, and 10 squared is 100, but, you know, just do the calculator at the same time you're doing it in your head, and that way you've got two different things figuring out the answer. And between the two, you won't make a mistake, hopefully. All right, so we've got that, and that seems about right. So this length right here is roughly 3.6, and this length is 11. This length right here is 11.18, right? Okay, now let's figure out what these two angles are. Okay, so phi A, all right, so that's this angle right here, and so it's the opposite over the adjacent. So in this case, the opposite, right? What's the opposite in this case? That is the height here, which is 2, and then the adjacent is 3. All right, so we want to figure out phi A, and it's going to equal the inverse tangent of 2 over 3. Okay, 2 over 3. All right, so let's go ahead and do that. Get our calculator out, press inverse tangent, and 2 divided by 3. 2 divided by 3 is 33.69. 33.69 degrees. And that, you know, even with this horrible drawing, 33.69 degrees, that looks about right. And let's go and figure out the other one. So phi B, that's going to equal, again, the tangent, inverse tangent of what? So here it is here, it's the opposite. So the opposite side of this angle is a large angle, and we got to be careful of something. So watch out. So there's the opposite, there's the adjacent, so it's 10 over negative 5. 10 over negative 5 equals, so we'll do tangent, inverse tangent of 10 divided by negative 5. All right, and then we get minus 63 degrees. All right, so now we have to be careful right here. So we have minus 63.4 degrees. Now, in this case right here, what this is telling us is that we're over here, and the angle up here is minus 63.4 degrees. All right, so this angle right here is minus 63.4 degrees. So what we want is we want this entire angle right here. So this, we know that this whole thing is, so when you're doing tangent, remember tangent has, you know, signs in each one of these quadrants, so you got to be careful of it. So in this case, we just have to, you know, watch what we're doing and make sure we're using the right angle here. So so we have minus 63.4 degrees, but in reality, it's this angle right here. So we're going to take that and we're going to add 180 degrees to it, and we're going to have 116 degrees. So what we really want, this phi b, right, is really 116.56 degrees. All right. So so in that case, that's what all there is to it. So we've got our rectangular. We found their lengths. We found these angles. All right, and now we want to put these into our phasor formats. So again, we want to have the magnitude and the angle, right? The magnitude and the angle. So we can just read these off now. So for A, if we want this in the phasor format, right, it's just the magnitude. What was the magnitude? 3.6. All right, and the angle now is, where the angle goes, 33.69. All right, and now B, we have its length, which is 11.18, and now we want its angle, right? And again, because we want to reference this as our 0, we got to be careful. So now this angle is 116.56. All right. So now, if we want to multiply these two things, we just simply multiply and add. So now if we want to figure out A times B, that is simply going to be 3.6 times 11.18. And then over here, it's just going to be 33.69 plus 116.56. And when we get done and do all that, we get 3.6 times 11.18, and that gives us 40.2. And then now we just need to add these up, 33.69 plus 116.56, and that's 150.25. All right, so those are the two different formats, and that's kind of an example of working through and solving these things. So let's see here. I think that's all we really need. So okay, so now the point is that when we have a complex impedance Z, we're going to have this real part, which is going to be the resistance, and then we're going to have the reactance, which is X, and then we're going to have this times J. So we're going to put everything in this format right here, and then we can maintain this as we do calculations. We'll do everything in complex format, and then we can see that from that we'll have more than enough information to figure everything out. We're going to have to do more calculations, but we'll always have all the information. We won't lose anything. Okay, so let's go ahead. Let's stop this. Let's stop this part right here, and then we'll come back and we'll finish by doing some examples now using complex impedances to go back to our RC example and maybe an RL example. All right, so let's stop here, and I'll meet you in the next lecture. Bye. All right, welcome back. We are on the next lecture, which is actually a continuation. We're doing kind of a multi-part thing here. And so what we've been talking about is complex impedance. So we've been talking about capacitive reactance, and we've been talking about inductive reactance, and then resistance, and then putting it all together and having this thing that we're calling impedance. And so let's just jump right back into where we were. So what we want to do now is we are going to do an RC circuit. We're going to do an RL circuit. And the plan is, and we'll see how this goes time-wise, but what I want to do is I want to do an RC circuit, do a analysis, and then simulate it maybe, and then build it on the bench, and then do the same thing for an RL. So we've got both examples, and then we're done with this kind of this lecture right here. So, all right, so let's go back and let's talk about what we've been doing here. All right, so let's write some things down. So the first thing is, and so I'm going to go a little bit quick here, as if I don't always go quick, but so let's start off and let's write a couple things. So if we have a capacitor, all right, and a circuit C. And if we have an inductor L, we learn that the capacitive reactance, which we call X sub C, equals 1 over 2 pi Fc, which is equivalent to 1 over omega C, where omega is the angular frequency. But we also learned that in reality, if we want to generalize this to impedance, then there's a imaginary term here that goes along with this. So if we want to write this in terms of impedance, then we would say Z sub C equals 0 plus, and then here was the tricky part, it's 1 over 2 pi Fc, and then there's a J down here in the denominator. But remember, we learned that J, and here's some of the imaginary number stuff, remember, imaginary numbers. And so electrical engineers, so EEs, call it J, and mathematicians call it I. All right, either way, it's the same thing. So I squared equals -1, and of course I equals the square root of -1. We also learned that 1 over I is equivalent to minus I. All right, and then J and I, of course, we can just replace. So we're gonna, sometimes I will accidentally do both, but J is kind of what we want to use. So this right here, we can rewrite this as Z sub C equals 0, minus J over 2 pi Fc. Or we can leave it in terms of X sub C, and we can say this, we can say Z sub C equals 0 minus J times X sub C. All right, so that is the capacitive, this is the impedance, and then here's the capacitive reactance. So this is the total impedance. Notice it has 0 for the real part, and then it has X sub C for the reactive part, all right, which is what we expect. Now, over here on the inductor, we've got X sub L equals 2 pi FL, all right. So the inductive reactance is 2 pi FL, but in reality, and of course that's also, we can say that's omega L, right? If we want omega, which is just 2 pi F, and that's in radians per second, that's the angular frequency. And again, if we want to generalize this to impedance, right, we say Z sub L equals 0, because there's no real part, it's completely reactive. And there's a J up here, so this is plus J 2 pi FL, which is also equivalent to, we could also just say 0 plus, we could say J omega L, and then we could also just put it back in terms of X sub L, and we could say X sub L, and then put a positive J out in front of it. All right, so once again, let's write this. Z sub L equals 0 plus Jx sub L, and then Z sub C equals 0 minus Jx sub C. All right, so those are the impedances. And then if we have a resistor, what's that? What's its impedance? ZR equals simply R plus 0J. It has no imaginary part. So those are all the impedances. And remember, impedance is the AC resistance. You could think of it's the resistance in AC. And to keep track of the phase angle, we use this notational trick where we use imaginary numbers because they represent two axes, an x and a y-axis, and the x-axis is real and the y-axis is imaginary. All right, so we remember all that, hopefully. So let's just erase that. All right, so we are going to jump right in, and let's do a RC circuit, and let's analyze it using impedance, complex impedance, and we're going to keep track of all the phasors either in rectangular or polar form, whatever's convenient for us. Okay, so let's do this. All right, so let's make a circuit here, and we're going to have an AC source. And so we're going to try and simulate this. So we want stuff that we can kind of simulate. So we want to be careful what value excuse me, we're going to simulate it. That's easy, but we're going to build it also. So we want to use values that we can actually build and nothing's going to explode or blow up. So just for now, we'll say that this is a 10 volt source, a 10 volt AC source. And for now, we'll say, let's just say it's at 50 Hertz. That's easy enough to change because we're going to use a signal generator. All right, and then remember this 10 volts, when we're talking about the 10 volts, we're talking about sine waves, always about sine waves, we need to say, is this the peak value or the RMS value? All right, so either way will work. So for fun, we've always been saying this is RMS, so why don't we just say it's the peak value right now? And all that means is everything will be in peak values, all right? Okay, so now let's put a resistor, okay, and let's put a capacitor, all right, and that's it. All right, and then so we've got our R, we've got our C, and let's set some values here. So for a resistor, let's see here, what do I want to use? Why don't we use 100 ohms? All right, and for the capacitor, let's use 10 microfarads. All right. And again, I like to do things in real time. I don't like to fake it, so I don't do these problems beforehand. You're doing it with me for the first time, so that way I keep it honest, and I'm not making things look easy that aren't easy. So if we get stuck and the numbers don't work out, they just, they're not working out good because we picked bad values. In a math class or in an EE class, values will be picked to make the problems work out easy, and I don't really like that because then it doesn't kind of show what happens. Now, even though 100 ohms and 10 microfarads are kind of easy numbers, we could pick, definitely worse resistors and capacitors, but still, because we've got pi's in there and twos in there and different things in all these formulas, things get kind of ugly, but that's good. All right, so we know that we're going to get a current in here, right? And the current's going to go this way, and then it's going to flip back and go that way, right? So we're going to call that current, let's call that current I, all right? And let's go ahead and just to make this easy, let's call this, actually, yeah, we'll call that I and we'll call that V, V for the source there. Okay, so let's start writing stuff down here. So here we go. All right, so X of C, all right, the capacitive reactance equals what? It equals 1 over 2 pi Fc, which equals 1 over 2 pi, frequency is 50 hertz, and C is 10 microfarads. Okay, so that's that right there. We'll figure what the actual value is in a second. All right, let's do X sub L. All right, what does that equal? That equals, oh, excuse me, we don't need an X sub L here. All right, in this case, we just have an R here. All right, so now let's go ahead and let's start writing down some impedances. So if we want to write down Z sub C, it has no real part, so that's 0. And then we got to be careful, it's capacitive, so it's minus J times whatever this X of C is, right? Minus J times X of C, so that's 0, and then J times, and let's figure out what X of C is. Get your calculators out. Again, I want you to be just super comfortable using a calculator and getting these values, and not just thinking you're doing it. So we put all that in, and then we get a value. So 318. And what I'm going to do is I'm just going to go to, frankly, to make this simple, I am going to round all values to a whole number. So this is 318.3. I'm just going to round it to 318. All right. So this is going to be 318. This is going to give us a little bit loss of precision, but it'll give us less gray hair. All right, so that's that answer right there. And then you might see this as simply as minus, J 318, right? That's exactly the same. We don't have to write the 0 here, but it helps us as a placekeeper. Okay, now let's do our resistor. All right, so we want to figure out what ZR is. Okay, so that was the whole calculation of X of C. And then if we want ZR, go ahead and we can put this in a different color. So ZR, all right, equals, it only has a real part, which is 100. So this is 100, and then it has no imaginary part, so we could say plus J0, all right, or 0J. All right, so that's it. So now we've got our two uh, impedances, our two complex impedances, ZC and ZR. All right, and so now if we want here, we can go and let's go draw these. All right, real quick. So let's go on our phasor diagram here, and we could draw these. All right, and so we know, and we're gonna overlay. What we're doing here is we're overlaying the imaginary and real axis here. So there's the plus real axis and the minus real axis would be in that direction. And then up here would be the plus J axis, and here would be the minus J imaginary axis, all right? Okay, so let's go ahead and we'll draw the resistance. We'll draw its impedance in green here. So its impedance is just 100, and it's on the real axis, so ZR. So if we come out here, and again, these are not to scale, unfortunately. So that's ZR right there, and it's completely real. That's why it's on the real axis there. It has no imaginary component. And then in red, actually in blue, let's draw the capacitive, let's draw the impedance due to the capacitor. All right, so the impedance ZC due to the capacitor, now remember, it's always pointing down because it's minus 90 or it's minus J. That's that minus J right there. See that? That's that minus J. So it's pointing down and it's 318. So it's actually much longer. So just, you know what, just for fun, let's kind of make this a little bit to scale. Let's erase that. And let's lengthen this up a little bit. There we go. Okay. All right, so this is now going to be 3 times as big, right? So there's 1, there's 2, there's 3-ish. All right, so there we go. And let's make this horrible little triangle there. Okay, arrow. Okay, and so this is our Z sub C, all right? And so there are our two impedances drawn on this phasor diagram. All right, so those are correct. Now we could go and we could find the hypotenuse and all that. We can do it that way. But let's keep working with the complex impedances in the format that they are. All right, so the first thing is we've got this is a rectangular form. So we've got ZC in rectangular form, and it's ZC equals 0 minus J318. And then we've got ZR is 100 plus J0. So we've got rectangular form of both of these, right? Now, can we get the polar form of both of these as well? So let's see. So in this case right here, we've got this ZR, and so if we want the polar form of this, right, that's fairly easy. ZR equals, and what's the length of this? Well, if you want to convert from rectangular to polar, we need to take the square root of the square of the real part and the imaginary part. 100 squared, square root is 100. So when there's only one component, the magnitude is just that one component, right? So we've got 100, all right, and what's the phase angle? Well, here's 0 degrees right here. The phase angle is clearly 0, and we can see that from here. There's no imaginary component. If there was an imaginary component, right, that's where that phase angle would come from, but we don't have any. So the phase angle is 0 degrees. All right, so there's ZR in that format. Okay, and then ZC. Okay, let's do that. So ZC again, what's its magnitude? And be careful here, what's its magnitude? It's 318. Its magnitude is 318. And again, how do we find that? We square that, and we square that, and then we take the square root of the sum. And since this is 0, minus 318 squared is, and then we get rid of the sign when we do that, right? And then take the square root of that is just back to 318. So it's 318, all right? And also remember, these things are all in ohms, right? So these are in ohms, right? Ohms. Everything is ohms. All right. So and technically, we can put the ohms symbol right there. We could put it after. So you know, ohms are there. Ohms are there. All right. And what's the angle here? So this one is tricky. So this is minus J. So if there was no angle, if it was 0, it would just be 0 degrees. Minus J is over here, right? And so minus J is what? It's minus 90 degrees. relative to this x, and then plus j, right? Plus j is plus 90 degrees, right? So it's minus 90 degrees. And then also, for those of you that don't think in radians as much, right? So remember there are 2 pi radians in a circle, and that's 360 degrees. Or there's pi radians in 180 degrees. Let's keep dividing. Pi on 2, 2 in 90 degrees. Okay, so if you can just remember these 2 pi, 360, pi is 180, and then pi on 2 is 90. So this is pi on 2. 90 degrees equals pi on 2, and then minus 90 equals minus pi on 2. Okay, all right. So now we've got these values here. All right, so we've got our complex impedances both in rectangular and polar form. All right, and so now let's go ahead and let's write down our rule here, and for Ohm's law, and our rule for Ohm's law is V equals I times R. But when we're talking about impedances, now we've generalized this, right? So now it's not R anymore, it's Z. Okay, so this works all the time, no matter what. So no matter what, if you have an impedance, complex impedance, this will work. And if you just have an R, then there's no complex part of the number, but it surely doesn't hurt to do all the math. So this formula right here is, Ohm's law for Z. Same thing. Okay, so V equals I times R. All right, so let's go ahead and let's figure some things out here. All right, so the first thing is, why don't we figure out what the total impedance is? So the total impedance, okay, so let's figure that out. So if we were to add these two things together, we would call that Z sub T, total impedance. And just like two resistors, you just add the resistance together, but they're not resistors, they're impedances, they're complex impedances, and we have to add them together using their complex representations. What are their complex representations? Well, they're right here. Here's Z sub C, and here's Z sub R. All right, so when we add these two together, so we're going to say Z sub T equals Z sub C plus Z sub R. All right, and when we do that, we look at this. So Z sub C is 0 minus 318. So we can do it like this. We can say 0 minus J 318 plus Z sub R. What's Z sub R? Where did it go? 100 plus J0. 100 plus J0. And then clearly, when you start doing this a little while, you realize all you have to do is just kind of overlay the real part here and the imaginary part here, because each one is missing the other side. So this only has an imaginary part, this only has a real part. So when you add these two things together, it's just 100 minus J318. And there you go. It's 100 minus J318. There it is. Very simple. So it's 100 minus J318. Okay? All right, so that is our total impedance right there. Okay, so now we have our total impedance. So let's go back over here and and so what we want to find out is, how about we want to figure out I, and that's going to be V over Z, and Z meaning our total impedance. All right, so first, what is V? Okay, so this is what's V? Here's V right here. V is 10 volts, okay? And but we need to put this into complex form, right? Into complex rectangular or polar form. So let's so first, right now, this is the magnitude, or it's the peak, or RMS, and we said it's the peak, so keep that in mind. And what we want to do is we want to use the voltage source as the reference for the whole circuit, for all the phasors, for the current and voltage phasors. So what we're going to do is we're going to arbitrarily say that the voltage source has a phase angle of 0, and then we'll find everything else relative to that, because everything is relative to everything, so we can make one the reference, all right? So typically you make the voltage source the reference, or you could make the current source the reference also if you had a current source. We're going to make this the reference. So V equals 10, right? And it's 10 volts. And what's its phase angle? 0 degrees. It's as simple as that. So that's it. And then if we wanted to put this into rectangular form, we could do that very easily, right? So if we want to do that in rectangular form, what's that? We could also say V equals, the real part is 10 plus 0j. So very easy. So 10 and 0. So now, here we go. So this is 10 volts and 0 degrees, right, over what's our Z total, and we want Z total in, we need it in a polar format, right? We need it in a polar phasor format. So we need to work on this right here. So let's do this. So if we want the length, so here we go. So if we want the magnitude of ZT, that's going to equal the square root of 100 squared, right, plus negative 318 squared equals, let's get our calculators out and do that. So we've got 100 squared plus 318 squared, and notice I don't need to put the negative sign in there, obviously it's going to square out, and then we'll take the square root, and 333 ohms, okay, 333 ohms. 333 ohms. All right, so that's the length. Okay, so that's good. Now what we're looking for is we need the angle. So remember, the angle is the imaginary part over the real part. All right, so the angle phi is the inverse tangent of the imaginary part, which is this minus 318, over the real part, which is 100. All right, so let's go ahead and do that. Tangent inverse of minus 318 divided by 100. We have that right? Okay, and that's minus 72 degrees. All right, so minus 72, and it's 72.5. So on these values, like I said, we're just kind of rounding a little bit. But on 72.5, since that's right in the middle there, I think I'm just gonna, now, you know what? Yeah, let's just leave that as 72 minus 72.5, because the angle will kind of have a larger effect on things. All right, so minus 72.5. Now, is that correct? Is that correct? Let's think about that for a second. So this is a capacitive circuit, right? A capacitive circuit. And if we were to add these two reactances or these two complex impedances here together, right? What would we do? We'd kind of put this down like this, and we'd go over like that, and then we'd put the hypotenuse here, right? And that length, what's that? Where is that? That's our 333. That's our 333 ohms. That's our length. And then this angle here would be the angle right here. That is that minus 72.5, right? That minus 72.5 degrees. That looks about right, even drawn with this horribly incorrect, not to scale figure. So things are doing what they should do. And remember, capacitive circuits will have the reactances down on the negative imaginary axis, the minus j axis. So that's why you're getting this negative number here. Inductive circuits will have the reactance and their complex impedance up on the positive j axis, so then you're going to have a positive, all right? And so now we're computing current here, so let's compute current, all right? So now we're done here. We've got this answer down here. So we want now the phasor here for Z sub t. So what I'm going to do is, can I scooch this in here? Yeah, so I'm just going to put this in here. So I'm going to say Z sub t also equals 333, and again, we can put ohms here because that's what it is. And what's our angle? Minus 72.5. All right, so just don't lose that right there. It's kind of scooched in there. And okay, so now we've got everything that we need here. So now we can put this down here in this denominator. So we've got 333 ohms, and we've got minus 72.5. All right, so now let's do this math. So remember, when you multiply and divide phasors, right, that are in polar format, all we do is just multiply and divide the magnitudes, and then we add and subtract the angles, all right? When you multiply, you add the angles. When you divide, you subtract. So be careful of that. So first, let's figure out the magnitude. So that's just 10 divided by 333, all right? And so we get 0.03. So why don't we, so we get 30 milliamps right there. So this is 30 milliamps, we'll call it. 30 milliamps. And what's its phase angle? Its phase angle, now we got to be careful, is 0 minus a minus 72. So it's 72.5 degrees. All right. Okay. So it's 72.5 degrees. Now, that's what I is equal to. All right. So now we have I. We've got X sub C, we've got Z sub C, we've got Z sub R. We literally have everything in the circuit we could possibly want to know. So now let's figure out something else. What do we want to figure out? So let's figure out, for example, if we want to figure out what the voltage across the capacitor is. So if we want to figure out V sub C, let's use a different color for that. So if we want to figure out V sub C, so V sub C equals, and if we look at Ohm's law here, so voltage equals current times the impedance, all right? So where and in what format do we want to use? Probably the polar format because we're doing a multiply here, all right? So let's get the current here, which is 30 milliamps, all right? So 30 milliamps with an angle of 72.5 degrees, okay? And now we need to multiply that times the impedance of the capacitor, the complex impedance, which is this right here, all right? And so that is 318, and hopefully I haven't made any mistakes here, all right? And that had a angle of minus 90, all right? So now let's go ahead and do this, all right? So 30 milli times 318 equals 9.54. So 9.54, and of course that's volts. And an angle, what's the angle? We just add the two angles together. So that's easy enough to do. So that's 90, excuse me. So that's 72.5 minus 90, and that's minus 17.5. Minus 17.5 degrees. So that's V sub C, all right? So now we'll get to the significance of that in a second here. All right, okay, so let's see here. Now, how about let's do the same thing. Let's get a little space here, trying to keep us all on one page. So now let's do the same thing for, what are we doing? For the resistor. All right, so let's compute V sub R. V sub R, so is simply the current times the impedance. All right, so again, what's the current? The current is still that 30 milliamps. Very important, the current in the circuit is the current in the circuit, always, right? So keep that in mind. The angle is 72.5, 72.5. All right, and notice I'm putting parentheses here, just trying to keep everything straight. It's really easy to make a mistake with all this, and I probably made one, but hopefully if I did, we catch it later. But just try and keep things as clean as possible. All right, so we got 30 milliamperes as our current at 72.5 degrees, and now we need our complex impedance for the resistance, right? And that's right here, right? And it's 100 ohms at 0 degrees, okay? So that's 100 ohms at 0 degrees, all right? We like zeros. All right, so now we multiply this together. So 30 milliamperes times 100. That'll bring us up a little bit. So we got 3 volts. And we've got our angles. So we multiply, we simply add. Okay, so there is VR. So there's VR, and here is VC, V sub C. All right. Okay, so now let's look at this for a second. Let's take a pause here. We've done a lot of math, and hopefully some of it is correct. So let's take a pause and let's think about what's going on here. All right, rule number 1. In the capacitor, the voltage and the current are always out of phase, right? Remember this? And what is it? It's ice, right? So the current leads the voltage, or the voltage lags the current in a capacitor by 90 degrees. Always. So this has to be true. That's number 1. So let's keep that in mind. Let's see if that's correct. On the resistor, the current and voltage are completely in phase, and the phase angle is 0, right? Okay, so let's see first if the voltage and current in the resistor, if the voltage and current in the resistor are in phase, all right? So what is the voltage of the system? The voltage of the resistor, here we go. The voltage of the resistor is at 72.5 degrees. It's 3 volts at 72.5 degrees. Okay, what is the current in the system? It's 30 milliamperes and 72.5 degrees. Okay, so that checks. So the voltage and the current are in phase in the resistor. That's good, okay? And just as a side note, it's actually dissipating real power, right? And the power that it's dissipating is simply 30 times 30 milliamperes times 3 volts. So it's actually dissipating power. That's good. Now, on the capacitor, what is the current and voltage going through it? Let's look around. So here somewhere. So here's the current. It's still the 30 milliamperes at 72.5 degrees. What's the voltage on the capacitor? It's over here. So it's 9.54 volts with a minus 17.5 degrees here. So wait a minute here. So minus 17.5 and we got 72.5. So let's look at the phasor here. And I'm just going to draw this on top of this diagram right here. So bear with me. So I'm going to use blue. And blue is going to be this current phasor, okay? And I'm not going to draw it to scale. I'm just going to draw it like this. Okay, so here is our I. And, well, at least I could do for you is I can make this angle more realistic. All right, so here is this I, and it says that it's 72.5 degrees. So this angle right here, all right, we'll call that like phi1 is 72.5 degrees, 72.5 degrees. Okay, now where is our voltage over our capacitor? It's here, and it has a lagging or negative angle of minus 17.5, okay? So let's go ahead and just draw this in this pink purpley color, minus 17.5. And again, I'm not doing these things to scale here. And if I did, this would be huge because I drew this so big and it's only 30 milliamperes. But I'm going to draw this kind of small here, okay? And this is V sub C here, all right? It's phasor and its angle. And what's its angle? Minus 17.5. So I'm in the negative direction here. So this is minus 17.5. So if you take 72.5 and 17.5, right, and you add up the entire thing, well, look at this. Look right here. This is 90 degrees, which it should be, right? So if we say 72.5 plus 17.5, and the universe is okay, it's 90 degrees. So this is interesting. So in the circuit, the rules of the capacitor and the resistor are maintained, but everything's been shifted around, right? But they're still correct. And the reason why everything is shifted around because we've mixed these two components together. So if this is a purely capacitive circuit, then these angles would be rotated back to zero. They'd still be 90 degrees, but they'd be rotated back to zero. The second we add that resistor, we start rotating this phasor relationship. But for each component individually, the relationship must be maintained, right? And it is. Okay, so that's it. So we figured out the current, we figured out the voltages, we figured out all the phase angles, and that's it. So we figured out everything, all right? And so we know everything about this circuit, and we can compute what the power is, right? So the real power here, the only power that's dissipated is in the resistor, and it's just 30 milliamperes times 3 volts, right? So if we wanted to know that, what is that? 30 exp3, 30 exp3 times 3 is 90 milliwatts, right? So this guy is dissipating 90 milliwatts, all right? And again, we got to be careful with this because this is the peak, not the RMS, all right? So this is not exactly true because we're not using the RMS values here, and this is going to be RMS. So this is kind of the peak power being dissipated. And then on the capacitor, is there any power being dissipated? Well, no, because the current and the voltage are 90 degrees out of phase. And because they're 90 degrees out of phase, no power can be dissipated. It's impossible. They're never overlapping in time, right? So, so anyway, keep that in mind. Remember, capacitors, inductors are reactive. They never dissipate power. Real ones do because they're not perfect. Remember, we looked at the models. They really have resistors in there and other capacitors, and they're not ideal. Okay, so that's it. And so what I want to do right now is let's keep going here, and we're going to take this circuit and we're going to put it into a simulator. All right, so let's put this into a simulator. So let's get that set up right now. Oh, and before we do that, before we put that into a simulator, on Wikipedia, this is a nice, if you look up phasor, and I wanted you just to take a look at this, just kind of peruse through this Wikipedia phasor, like phasor in Star Trek, sort of, with an O. It's got some nice, figures here and some nice animated figures which kind of show you this, and then it goes through all this math that we've been kind of doing, all right, but in a little bit simpler way. This makes it look really, really bad. But this is a nice figure right here showing relationships and so on. So anyway, take a look at phasor on Wikipedia, okay? All right. Okay, so what we're going to do here is we're going to use Proteus to do the simulation. And again, because Circuit Maker does not have simulation, and that's kind of the program that we're going to be using later when we're laying out circuits. But for now, we're going to use Proteus, which you can download a free copy if you go to the website, which we looked up. All right, so here I've kind of put together a small circuit to kind of mimic what we're doing, and we kind of use this for some of these experiments that we're doing. So if we look at our circuit, let's go ahead, and we've got 100 ohms here for this R1, so let's just go ahead and change that to 100 ohms. All right, and then for our capacitor, we've got, what do we got? A 10 microfarad instead. We've got 10 microfarad. Okay. And then for our AC source, we've got AC source, and we're doing a peak value here. And the peak value we said was 10 volts, right? And the frequency, what did we say, is 50 hertz. Okay. And all right, so when I run this simulation now, a couple things here. I've got AC volts here, so this is, and again, this is why this is a great program. Even if you don't buy it, because it's fairly expensive. You get a student edition, it's a lot cheaper. But even if you don't buy it and you just use the evaluation version, the simulator is worth that alone, because you can just drag parts in here and simulate, and it works very, very well, and it does very complex chip level simulation. So this is great. So Proteus, download it, and then you can follow along. And then all I really did here was I went and found these components in the parts libraries, and then you simply drag them down into the design, and then connect up the wires, and then these AC voltage, AC milliamperes, AC voltage, these are just come down, and I believe they're right here, these kind of instrumentations, this little instrumentation icon, and then you can grab different components here, AC voltmeter, AC ammeter, watt meter, and so forth, and kind of put this together. All right. And then this is an oscilloscope, which on channel A and channel B, I'm watching what the AC source is, and then watching what the voltage over the capacitor is, just for fun. Now let's go set everything here. And I've done this a couple times, so some of these values will still be here. All right, so we have the frequency at 50 hertz. And now on this particular simulator, peak means peak to peak. So I had to remember this actually, and so that kind of messed things up. So what I'd like to do is this. So in our circuit, we were calling the 10 volts the peak value. The problem is with that, if we do that and run the simulation, all of these sensors, these instruments to measure currents and voltages work in RMS. So it's best that we just pretend that everything was RMS, all right? So we'll just say that instead of peak, when we did all the calculations, it was the RMS value. Wouldn't change anything, it's just a convention. So we're gonna say it's RMS 10 volts, all right? And we've got 50 hertz. All right, so we've got 100 ohms, 10 microfarads. Let's go ahead and run the simulation. All right, we've got our oscilloscope here. All right, and so we've got all these values, and sure enough, they do match. So we've got 30 milliamps, 3 volts over the resistor, and 9.5 volts over the capacitor. Let's take a look, and let's see if that is accurate. So we have 30 milliamps, there's our 30 milliamps. We have 3 volts over the resistor, and we have 9.5 volts over the capacitor. So amazingly, that is completely correct. So that's good. All right, now So here's the thing. We have validated the circuit, and so the math matches the simulation, and that's usually going to be the case. The math and the simulation will actually be very accurate to each other. And now, of course, in the simulation, if you have a capacitor that's got a non-ideal model where it has actually some resistance in there, and then some inductance as well, that's going to be even a closer model. But the difference between your math and the ideal model simulated, or even the correct model that's non-ideal, will be very close no matter what. Where you're going to find a huge disparity many times is when you do the actual build of the circuit. And this is why there is no, there's nothing like building the circuit. You have to build the circuit to see how it actually performs. And the reason why is because the capacitors are not ideal, the inductors are not ideal. There's all kinds of things going on, parasitic effects that are going on in a circuit. And of course, when you build something on a PCB, it's going to be much better than if you're building it in solderless breadboard and so forth. But you still want to build it to get an idea of what's going on. But before we do that, let's take a quick look. So here's the oscilloscope here. And the oscilloscope, of course, is, it's kind of wonky. I mean, it's a virtual oscilloscope of a virtual circuit being simulated, so we can't expect too much out of it, but it does work. And so I don't use this that much, but anyway, what we're going to do is we're going to turn the gain up here a little bit so we can see things. And that's the blue, and that's the blue and yellow. Okay, and if we look here and follow these leads, the blue signal is the capacitor, and the yellow signal is the source voltage, and the blue is the capacitor voltage. Okay, we see that there is a phase difference between the source voltage and the capacitor voltage. So the question is, what is it? Now, I'm sure there's a way to measure it on this tool here somehow, or we could eyeball it. What we could do is we could get one wave lined up, and then we could change the horizontal sweep rate, the virtual sweep rate here. Okay, God help us. So let's turn this down, all right, and all right, so that's not bad. And then we can slide the position over, all right, so that's kind of cool. So we can see where the traces, where the traces cross zero, right? We could see where the traces cross zero. And then the yellow is the source voltage. All right, so there's the yellow, it's a source voltage. So let's do it a little bit more so that we can kind of see. All right, so there we know is 180 degrees, or pi radians. We know there's a half cycle. And there, the yellow trace is the source voltage, and then the blue trace is the capacitor voltage, all right? So what do we know? Let's go back and let's look here. So we see there's a lagging. So we see that the blue trace, which is the capacitor voltage, is actually lagging the yellow trace, which is the source, all right? So it's lagging it. So is that correct? So let's go take a look here. So if we look up here, it's ICE, so current leads voltage, all right? So that's not helping us too much right there. But if we go look at the phasor diagram, the voltage phasor is at 0 degrees, right? The voltage phasor is at 0 degrees. And then if we go look at the capacitor phasor, for voltage, look at that, it's minus 17.5 degrees. So there it is right there. It's this pinkish one, V sub C. So it's lagging 17.5 from the source voltage, 17.5 degrees. So that looks pretty accurate. And so 17.5 degrees right there, and that looks like to me that's exactly what it is. So anyway, so the simulation is correct, and that's really cool. Now, what we would like to do is then go take this simulated circuit and build it and see if the built circuit matches the simulation. All right, but we're going to have a problem. And so what I just realized is, well, I didn't just realize it, but I didn't think about it too hard, and I was kind of hoping it would work out. But the problem is that when we run the simulation, we want to use these RMS instruments here. And to do that, we have to come in here, and we can set what this RMS value is, this peak value, this amplitude value, and all that. The problem is our signal generator cannot do an RMS of 10 volts. And the reason why is, remember, and actually let's bring this up here so we can look at this, make sure we remember this math. So if we recall, let me get a good color here. So if we recall, if we want to compute voltage RMS, it equals voltage peak times 0.707. All right, let me do that, times 707, right? So the problem is, if based on this right here, if we have a VRMS of say 10 volts equals V peak times 0.707, right? Or V peak equals 10 volts divided by 7.7, 0.707, or multiplied times 1.414. Let's do that math. What do we get? We get 10 divided by 0.707, and that equals 14.14, right? So V peak equals 14.14 volts. The signal generator that I have only goes up to a peak of 10 volts. So we basically can synthesize a sine wave that looks like this, that has a plus 10 and a minus 10. So we got to kind of work backwards if we want to simulate, build a circuit and simulate it. So if we had a peak of 10 volts, what would the RMS be? So RMS is 10 volts times 0.707, so clearly that's 7.07 volts. So this RMS would be 7.07 volts. So we'd have a plus and a minus 7.07 volts. So if we go back to our simulation and set our simulation for 7.07 volts, and then we run our signal generator at a peak to peak of 10, plus 10 and minus 10, then we should get a matching simulation. All right, so let's do that. So let's move this back off here. And so what we're going to do is we're going to say that we have a RMS of 7.07, all right? And now also we can put that there, or we can put it in the amplitude, and it should end up being 10, and it is. See, it's 9.99, right? And this is, I don't like this, but if you say peak, it really means peak to peak, and look at it, doubles it. So it's doing the peak to peak. So that can be a point of confusion. I haven't used this in a while, and so that kind of confused me for a second. But anyway, let's go back to RMS. We'll leave it as 7.07, which means we're going to put in an amplitude or a peak voltage of 10 for the positive and a minus 10 for the negative on the signal generator. Then the simulation will match what we get. So now we know that our math matched the simulation, so the simulation is correct. Therefore, whatever we build should match the simulation for a lower voltage, right? Okay. So we've got this, and let's go ahead and let's run the simulation. All right, and everything is working. And we've got this 2 volts and the 6 volts here, and the oscilloscope showing the phase lag and all that. And then go back here. All right, and so we've got our amplitude of 9.99 or 10. All right, so now what we want to do is let's go to the bench and let's build this circuit. All right, and then let's run it and see if we get to these same results. So we're going to go, and we would just want a 100 in series with a 10, and we want to put instrumentation in here. So kind of keep a picture of that in your mind, and let's go over to the bench and let's build this, okay? All right, so we've got our board here, and let's just put this thing together. So we need a 100 ohm resistor. So I've got all my parts here. You can't see them, and my wires and everything laid out, so it's easy. So here's my 100 ohms. So that's brown, black, brown, right? Brown, black, brown. Let's take a quick look at it on the zoom camera. There it is, brown, black, brown. Okay. All right, so first thing is we're going to use, here will be where the signal generator is hooked up. So here's the signal generator input. So we're going to kind of make the circuit exactly how it looks on the screen there. So let's go ahead and, so the signal coming from the signal generator will come from this top rail. And there it is right there. Give ourselves some room here if we want to do anything. Okay. And then we're going to have, let's just add a little piece of wire here to put some space between things. It never hurts to have a little extra space. All right, and then we are going to put our capacitor. So we need a 10 microfarad capacitor. So here's one right here, 10 microfarad, and this is 63 volts. So 10 microfarad and 63 volts, and of course this is electrolytic, so it's polarized. all right? And this means it could withstand a maximum of 63 volts. So when we do that simulation, we want to make sure that we are never exceeding that 63 volts. And personally, don't exceed it by 50%. You can probably go 70%. You can probably go to the whole value, but I would advise against it. Okay. All right. So we're going to put that in there. All right. And why don't we zoom in a little bit more so you can kind of see a little bit better. All right. Okay, so we got those two circuit elements, all right, and now we're going to put this one to ground. This one has to go to ground. Okay, so the capacitor is going to go to ground. All right, and so now if we turn the signal generator on, this circuit will energize and it'll do what it's supposed to do. And the couple things that we want to be careful of is the amount of current that we're putting through different components of the circuit, like the resistor. We already computed it's like 90 milliwatts, and this is a quarter-watt resistor, so that's okay. So, do sanity checks as you're building things so nothing blows up or explodes or whatever. Again, I'm wearing protection glasses. Even though we're not going to put a lot of power through here, you got capacitors, you never know, something might pop, so it never hurts to wear protection glasses. All right, and so now let's add some instrumentation. So we want to measure the voltage across the resistor, the current in the circuit, and the voltage across the capacitor. So we're going to add a lot of instrumentation. We don't want to put too much load on the circuit. So for now, why don't we just, let's measure just the two voltages, and we can measure the current maybe after. All right, so we need to put a voltmeter across the resistor, across it, not from here to ground, not from here to ground, but across it, and then across the capacitor. So what we're going to do is we're going to get a couple wires, and we're going to go across the resistor differentially, and then we're going to plug in one of these little guys that I made out of these power supply connectors, these PC power supply connectors. These are really, 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 really useful. All right, and the probes will go in there. All right, so there's that one voltage. Now let's get the capacitor to ground is the next voltage that we want to monitor. So let's get another wire here, and we want to put it at the top. And why don't we put it right here? Don't want to get too messy. And then maybe we can do do we have a shorter one? Not really. All right, so then, and I know that the connections are three holes apart, or 0.3 inches. This is 0.1 inch spacing. All right, so I just put those three apart, and then I'll put this in here. And again, orientation doesn't matter because we're measuring AC, right? We're going to measure AC signals. Now, the meters, here's another potential problem. The meters are going to measure, what are the meters going to measure? The meters are going to measure RMS values if they are an RMS meter. And you want what's called a true RMS meter. And what that means is it doesn't assume the signal is sinusoidal and just look for peaks and then synthesize a sine mathematically and then do the math. It actually digitizes the signal. So it actually is measuring the signal. So if it's a deformed sine, it'll be correct. So anyway, that's important if you want to do very accurate voltage, current, and power calculations with your meters. You want true RMS meters, all right? Okay, so what we're going to do is we're going to hook these two meters up, and then I'm going to try and get everything on the screen here. So I'm going to hook the meters up. So let's see here. So the voltage over the capacitor, how about this? The voltage over the resistor will be the big green meter. So we're going to do that, big green meter. Okay, and that'll get on screen in just a second. And it's always fun trying to get everything to fit here. So I'm going to zoom out a little bit here. All right. Okay. So there is our big green meter. All right. And I'm going to zoom out some more. Okay. Don't worry about the camera shake. I'll stop it. All right. And then we've got this black meter here. All right. And so first, let's get both of these things to turn on. And we'll turn this one on. All right. Make sure it's in AC mode. All right. And the range is correct. Okay. So the black meter is going to be the capacitor voltage. All right. Now we're going to see. Now again, I like to do these demos, on the fly. So we're going to kind of find things out as we go. And then the reason why is you know, we're never going to be surprised, and we're not going to have to figure out any problems. All right, so I try to just do this as we go, so we can kind of, you know, see things go wrong. Otherwise, we're never going to learn anything. All right, so okay, so I think we're ready. And all right, so now what we're going to do is we're going to go on to the signal generator, and we're going to set the signal generator so it's plus and minus 7 volts, 7.07 volts. All right, so again, I'll put a camera on that for you. Okay, so you can see the view of the signal generator, and so now I've got the frequency at 50 hertz, and I could change it there if I wanted, so it's at 50 hertz. And then we've got the amplitude here. We've got 7 volts for the high, and we've got -7 for the low. And then you can see the synthesized signal. It kind of shows you the signal, which is nice. And we've got a sine wave, right? We could, you know, there's a square wave, but we want a sine wave because we're doing sinusoids. And then if we press this button again on this particular signal generator, it'll show you that the peak-to-peak value is 14 volts. Okay, so the peak-to-peak value is 14 volts here. And so what we want here is we want to make this 10 volts, right? So that we get a 7.07 RMS value, right? So what we need to do is we're going to drive this thing all the way up to the 20 volts, all right? So we're going to drive this up to, and sometimes it's just easier to enter it in. Okay, so now I've got 20 volts peak to peak. So we've got plus 10 and minus 10. But the RMS value of 10 would be 7.07 and minus 7.07, right? So back in our simulation, that's what we have. So now when we run the circuit, we should get something similar to what the simulation says. All right, so now I'm going to go ahead and I'm going to turn this on. All right, so we go ahead and turn on the signal generator, and let's take a look and see what we have here. So we have 5.98 volts across the capacitor, and we've got about 1.6 volts across the resistor. And that's what this is showing. And again, these are RMS values. All right, so we've got about 6 volts and about 1.6. Now, if we go back and look at the simulation, the simulation here says that we should have about 6.76 volts and about 2.14 volts, all right, and about 20 milliamps of current. All right, so we're in the ballpark. So we've got 6 and 1.6 instead of 6.7-ish and 2.1. All right, so what is wrong? So what's wrong? Well, the problem is this capacitor. This capacitor is electrolytic, and it says 10 microfarads on it. But it's got a tolerance of like 20%. So it could be 8 to 12 microfarads, right? So that capacitor is not very accurate. All right, so we could grab another capacitor, and again, many types of capacitors, if you want them accurate, the cost goes up dramatically. The only reason you'd want a very accurate capacitor is because it's in a filtering circuit and you are doing very, very specific filtering. Otherwise, typically, it's in a circuit as a bypass capacitor or a charge storage capacitor, and an extra 20% either way doesn't matter because you're gonna design it so that it's big enough, no matter what, to do what you need it to do. But let's go ahead and let's try a different type of capacitor. So let me show you this in front of the zoom camera. All right, so this, and it may not be able to focus on it. Oh, it can't because of the object in the back. But anyway, this is a ceramic capacitor. All right, and this is 10 microfarads. So what we're going to do is we're going to replace the electrolytic. So let's go ahead and turn off the signal generator. And I'm just going to replace the electrolytic capacitor with the monolithic ceramic capacitor, meaning it's non-polarized. Okay, I've replaced it. Now let's turn the signal generator back on. All right, and now we've got 6.09 volts and 2.1. Going back to the simulation, we've got 2.1 and 6.7, all right? So a little bit closer, but we're still off. So in reality, these capacitors are just not accurate enough to make what we build close to the simulation. the question is, could we figure out what this capacitance is, at least how it's acting in this circuit? Sure. We can go back to the simulation, and what we can do is we can adjust the simulation. We're looking for 6.1 and 2.1, 6.1 and 2.1. We know to start at 10, so let's adjust what the capacitor is in the simulation to meet what we're finding in reality here. So 6.1 and 2.1. All right, so we're back here in the simulation, and so what we're going to do is we're going to stop the simulation, and this is great. This is you know, when you learn is when you see how you have to kind of go to the bench, you check things out, you kind of come back. So let's adjust this, and let's just make it 9 microfarads. All right, so let's make the circuit less capacitive, and let's run the simulation. All right, and what are we getting? We're getting 6.8 and 1.94, so that looks like we're probably going in the wrong direction. Let's see, let's go 8, and let's rerun the simulation. All right, and 1.7 and 6.8. So we're going in the wrong direction, all right, for that capacitor. So apparently we need to go larger. So let's try 12 microfarads, all right, and run the simulation. Okay, so now we've got 6.6 and 2.5, all right, 6.6 and 2.5, all right, and so let's go to 11, all right, and run the simulation. All right, and now we've got 2.3 and 6.6. So you can see we're kind of homing in on the capacitor. But remember, there's other parasitic effects here, and we have this thing built on a solderless breadboard, and that's why we're not seeing the system work the way that we think it would. Now, let's try this. Let's go ahead and let's increase the frequency. All right, we'll increase the frequency, and let's increase the frequency to say 1,000 hertz. And let's put our capacitor, we'll leave our capacitor at 11 because that probably is a little bit more accurate to what we are. All right, let's run the simulation, move the oscilloscope. So now we've got 7 and 1 volts. So notice the voltage has changed and kind of switched around, right? And the reason why is because the capacitor's reactance now, right? The capacitor's reactance to this high frequency, right? And if we remember the capacitive reactance, X of C is 1 over 2 pi FC, and now F just went up, so the capacitive reactance just went down, all right? So now we have 7 and 1 volts, which is kind of lucky. And so now let's go look to the simulation. Let's run it at 1,000 hertz, and let's see what we get. All right, so we're back over here at the simulation, and we're thinking that this capacitor is probably more like 11 microfarads, right? Somewhere around there. So now we're going to go to the frequency adjustment here, and we'll put this to 100, and then we'll move the control to the left here. Okay, 200, 300, 400, 500, 600, 700, 800, and 1,000, or 1 kilohertz. Okay, we just changed the frequency to 1 kilohertz. And I've switched meters here, and the reason why is the other meter, the leads seem to be getting loose inside of the sockets. All right, so anyway, now looking at these two meters, we see 0.75 volts and 4.5 volts. Now, back in the simulation, we've got 1 volt over the capacitor and 7 volts over the resistor. So let's make sure here what we've got going where here, right? So the green meter is over the capacitor. The green meter is over the capacitor, and that's 0.75. And the lime green or bright green is over the resistor, and that's showing 4.5 or 4.6. So we're getting 0.75 and 4.6, whereas in the simulation we're getting 7 volts and 1 volt. So this should be 1 volt, and this should be about 7 volts, right? Again, what's wrong? Again, what's wrong is that the capacitor is not acting exactly as it should. So it's frequency dependent as well. So again, you know, we come to the conclusion that not only do all these wires affect things when you're talking about analog signals, right? The components are not ideal, and things get affected. So that's why the way that you build things is very, very, very important, and how you build them is very important, and that you model things correctly and that you test things. All right. So we see that as we increase the frequency, this circuit becomes even more and more non-ideal. All right, because other things start to come into play. What comes into play? Inductance starts coming into play. High frequencies, inductors don't like high frequencies, and so that starts affecting the circuit, and we start getting impedances. These wires and all this, you know, affect things. And another thing that affects things is actually having the meters themselves in the circuit these are impedances, right? They're not for free. We don't just connect them to something that have infinite input impedance. They actually have impedance. So when you connect these to a circuit like this, it actually affects the circuit as well. So there's that. So just measuring it affects the circuit. So that's why you want to have really expensive meters and really good probes. And here's a crazy fact. Really good probes, these probes, really good probes can cost up to $10,000 or $20,000 each, if you can believe that. That is crazy. You can go on DigiKey and Amazon and you can find $10,000, $20,000 probes. So anyway, so we did the math, we did the simulation, we built the circuit, we adjusted the circuit because our signal generator couldn't go high enough. Then we've kind of played around with frequency a little bit, and we see that, yes, indeed, the capacitor acts as a frequency dependent resistor, right? An inverse, all right? And then just let's watch these two values right here as I change the frequency again. So I'm going to go over here and I'll turn it to, so right now we've got 0.75 and 4.5, and I'll turn it to 2 kilohertz. And you can see it changing, 4 kilohertz, 5 kilohertz. All right, so we're at the 5 kilohertz, and we see that this value right here is the voltage drop over the capacitor, and this is the voltage drop over the resistor. And we see that the voltage drop over the capacitor, right, the RMS value of that, is very, very low as we increase the frequency. Let's increase it some more. Let's take it up to 10 kilohertz. Now it's at 10 kilohertz. Now it's almost nothing. So why is that? Well, the reason, remember, the capacitive reactance goes up as the inverse of the frequency. So the capacitive reactance is nearly zero. Let's figure out what it is, right? It's 1 over 2 pi fc, okay? So 2 times pi times the frequency, 10 kilohertz, times the capacitance, 10x minus 6, equals, take the inverse of that, 1.6 ohms. So this is 1.6 ohms right now because the frequency. So again, the higher the frequency, it acts as a frequency dependent resistor, an inverse resistor, 1 over R, or 1 over F. So the higher the frequency, the lower the resistance. That's useful. Same as the inductor, except the inductor is directly proportional. The higher the frequency, the higher the resistance. And now let's lower the frequency back down. 9, 8, 7, 6, 5, and notice the voltage is going up, 1 kilohertz. Now 900, 800, 700, 600, 500, 400, 300, 200, 100. There's 100. Now look, we're at 4.77 and the 3.2 volts on the resistor. All right, and then we can go even lower. We can go down to like 10 hertz. All right, and at 10 hertz, now we have the opposite. We have everything dropping over the capacitor, 6.97, and very little dropping over the resistor. All right, so that's about it. So that was good. So let's stop here, and then we'll do another part, and we're going to do an analysis of an LR circuit. Same kind of thing. We're going to do an analysis, simulate it, and then we're going to build it. So go ahead and stop here, and I'll meet you there. Welcome back, and we are continuing our discussion. We've been talking about the AC response of an RC circuit, and we've been talking about complex impedance, and now we're going to do the same analysis with a LR or RL, an inductor and a resistor. And again, we're going to use what we've learned about rectangular coordinates and polar coordinates and phasors to kind of do the analysis. So let's just jump right in and start working on it, all right? So let's get our drawing program up here. All right, so what I'd like to do is let's try doing something where we kind of simultaneously do a couple things at once. This will be fun. All right, so let's first put up the circuit that we want to kind of analyze using our techniques for phasors, all right, in complex impedance. So let's go ahead and we're going to put an AC source, and let's put a resistor, and we'll put an inductor. All right, we'll close that off and complete the circuit. So we've got this R and we've got this L. And now since we've got a signal generator, we can kind of change whatever this value is. But since we're going to do one computation here, we are going to say, let's see here, how about we do, let's say that we've got an RMS value of the voltage, an RMS value of, so let's do voltage equals 7.07. And so we'll say V equals 7.07, and that's RMS. And again, the frequency can be anything we want, but we'll say, just starting off, we'll just say it's 100 hertz for calculations. Now, the reason I say 7.07 is because the particular signal generator that we're going to do the develop the circuit on that we want to play with, it has a maximum peak voltage value of 10 volts. So that means the RMS would be 7.07, or excuse me, 0.707 times 10, which would be 7.07 volts. So that's why we're just setting that value there, just so that we can kind of mimic what we do here in the circuit on the bench there. All right, so here's one circuit. Now, what I also want to do is draw another circuit, which is similar, but we're just going to change a couple things here. So we're going to put the same generator. We're going to have the same values, so we're not going to copy them here. And then this time, we are going to put the inductor here, and then we're going to put the resistor here. All right, and so there's our resistor, there's our inductor, and in both cases, we're going to look at a couple voltages here. We're going to look here, right? Say this node here, and this would be, in this case, it would be the voltage over the resistor. In this case, it would be the voltage over the inductor. All right, and then we're also going to look differentially. So let's draw these as just dots, a little easier. All right, draw those as dots. And so we're going to look at the voltages across the resistor and the inductor in both cases. Now, one thing I want to bring your attention to is right off the bat, you can see that these are both like voltage dividers. So there's like a voltage divider kind of action going on here, right? And in both cases, if we think of these values, the R and the L, in terms of impedances, right? So we've got, ZR here, we've got ZL here, and then over here, we've got ZL here and ZR here, all right? And so now this is just the voltage divider, right? So the voltage over, say, the inductor would be ZL, right? So if we just wanted to know the voltage over the inductor here, right, that would simply be ZL over ZR plus ZL times whatever the input is. And as a matter of fact, we'll just leave that as V instead of a V, and we'll just call it V, all right? And so that would just be times V. And that's what would be the voltage over the inductor. And the reason why we can write that is because we're doing this all in complex impedance terms of Z. So these are voltage dividers. Both are just voltage dividers, all right? So let's start writing down what we know here, all right? So let's write down what the inductive reactance is, all right? So let's write down what the inductive reactance is, and let's set some values here. So I'm going to say that R equals 200 ohms in both cases, and L is going to be 2.2 millihenries, all right? And again, the values are both the same in both circuits. I'll just copy them over here. 2.2 millihenries, not micromilli, and then this is going to be 200 ohms. All right, so one interesting thing is when you start working with inductors, the thing that you figure out real quick is inductors, the values that you're going to get commonly are going to be in microhenries or maybe millihenries, and it's really hard to make circuits that do anything at low frequencies. So in other words, you're going to have to get into real high frequencies when you start playing with inductors. So in this case, the resistor that I'm picking, 200 ohms, I'm picking that on purpose, and I'm selecting that value for a couple of reasons. Once we compute the inductive reactance here, you're going to see that the inductive reactance is pretty low until we get the frequency up pretty high. This 100 hertz has to get pretty high. And so we want to be able to affect this 200 ohms in a voltage divider like action. So we want to go from 0 to say 1,000 ohms of inductive reactance over some frequency range that's reasonable so that we don't have to go up into megahertz, right? And so to do that, we're going to get inductive reactance at some frequency, and it's going to have some value. The lower I make the resistance, the larger that inductive reactance will seem to that resistance as we make the resistance low, because we're trying to create a voltage divider action out of this circuit so we can see it. So if we pick a very large resistor value like 20K or 100K, we're never going to get 100K ohms until we get up into mega or gigahertz of frequency. So I picked a fairly large, fairly small resistor in this case. Now the other thing that's important is when we put this on the signal generator, if we pick too small of a resistor, the signal generator won't be able to drive the circuit and too much current will flow. So we've got to kind of balance things. So again, you got to balance things if you want to get things to work on the bench and to be able to experiment with them. In simulation, we can do whatever we want, but on the bench, we can only do certain things with certain equipment. All right, that said, let's just get in here and let's start doing this. All right, so let's go ahead and let's calculate what x sub c is, and it's the same in both circuits. So x sub x sub l, what's the equation for that? 2 pi fl, all right? And since I just mentioned x sub c, what's the equation for that? It's 1 over 2 pi fc, right? But we don't have that, so we're not going to use it. We don't have any capacitors. All right, so it's 2 pi fl, and our frequency is 100 hertz here. All right, so x sub l equals 2 times pi times 100 times our inductance, which is 2.2 millihenries. All right, and let's go ahead and let's everyone get their calculator out. Let's do it. 2 times pi times 100 times 2.2 millihenries is 1.38 ohms. All right, 1.38 ohms. 1.38 ohms. All right, and let me do that again just to make sure, and you check it again. 2 times pi times 100 times 2.2 milli. All right, 1.38 ohms. All right, and so that's at 100 hertz. Okay, at 100 hertz. Now, because the equation here is completely linear, if I double the frequency, right, then this would be like 200 hertz, right, 200 hertz, then this resistance would double. Seem reasonable? So it's linear. So at 100 hertz, it's this, all right? So at, we'll say equals, at 1,000 hertz, it would be 10 times this, right? So it would be 13.8 ohms at 1 kilohertz. Right? And then it would be, again, times 10, so it would be 138 ohms at 10 kilohertz. All right? So hopefully that's reasonable. So you can see at 10 kilohertz, we've got roughly what our resistance is here, right? Obviously a little bit less, right? And then we could say, we could go to 100 kilohertz, but that's going to be problematic with the equipment. So why don't we just now double that to 20 kilohertz, all right? So at 20 kilohertz, it'll be 2 times that. So again, let the calculator do arithmetic. 276. So equals 276 ohms at 20 kilohertz, okay? So here are different ranges that we could set the frequency at and get different values at. Now, what we're going to do is we're just going to do all these calculations right now for this one value right here, right? But we know we could do them for all of these, and this is how things would go. All right, so first thing, let's talk about what the complex impedances are of each thing. All right, so again, both circuits are the same. We're going to do the left one, and then I just want to talk about the one on the right. All right, so over here, if we want to write Z sub R, right, the real part is 200 ohms, so it's 200 ohms plus 0J, right? okay? And the complex impedance for the inductor is what? It's simply 0 plus x sub L times J. All right, and we know what x sub L is here at this particular frequency of 100, right? It's 1.38, so we're going to put it in there. So this equals 0 plus 1.38 J. Now let's be careful here for a moment. In the capacitor example with the reactance of the capacitor, remember the capacitor had a minus J, and the reason why is because it's x sub c equals 1 over 2 pi fc, and there was a minus J. And then if we go and we look at the phasor diagram real briefly here, if we can draw a straight line, if we look at the phasor diagram of the impedances, we would get, so let's say that the resistor, right, we'll make that one yellow. Hopefully you can see that. All right, so here's the resistor, here's its impedance, right? It's right on the real axis, right? And remember, this is the real axis right here, and then this is the plus J, and then this is the minus J. So the inductor, right, those always have a positive J, right? They're going up this way. And the capacitor has a negative J, all right? So this is x sub c goes this way, and x sub L goes this way, all right? So when you have the phasor diagram, you can kind of remember that. So we've got a plus J here and a minus J there if it's a capacitor, and a plus J if it's an inductor. So that's where that's coming from right there again. All right, and so now the impedance for the inductor is 0 plus XL sub J, and for the resistor is 200 plus 0J. All right, and these impedances are measured in ohms no matter what. All right, so now we have those things, and so now let's talk about the voltage here. So remember, we can write this in both polar and rectangular form. So the magnitude of it, in this case, it's an RMS value, but we're going to first write it as a phasor. So we're going to say that V equals, and its magnitude in this case, and we're not talking using the word magnitude to represent if it's a peak value or an RMS value or this or that. We're just talking about in phasor nomenclature, notation, the first number is the magnitude of the signal. In this case, it's an RMS signal, so we know that, but when we use the word magnitude, we don't mean we're talking about the sine wave magnitude, we're just talking about the magnitude of the phasor. All right, so in this case, it's 7.07, all right, and we can put V for volts there if we want, but it gets a little confusing because we're calling this V, all right, and so we'll put the little V there, and then we're going to put our angle here. And now remember, we get to pick something as a reference. So we're going to pick the voltage as a reference. So we're going to put 0 degrees. If we wanted to put this in rectangular form, right, it would be simply this. It would be 7.07, right, and plus, and then there's no imaginary component, so it would just be 0J, right? And this, again, this whole thing is volts, right? So you can put the V right there. All right, so 7.07 plus 0J. So we've got both formats there. Now, same thing here with the ZR, right? The ZR, again, is in rectangular coordinates right now. If we wanted to put it into the polar coordinates, the magnitude of it, it's 200 plus 0, so the magnitude is just the 200. There's no component in the other axis. So that would be 200, and we can put ohm here. And the angle, right, is just 0 degrees. This is right on the real axis, right? It's only got a real part, so that's what it would seem. And then now the impedance for the inductor, it has no real part. It's purely imaginary, and it's in the positive J. Okay, so let's be careful here. So first, what's its magnitude? Its magnitude is just this 1.38. 1.38, and again, this is in ohms. All right, and it's pointing in the plus J. So what is that? That's 90 degrees, right? That would be the angle. And then this, if it was down here, it would be minus 90. So this is plus 90 degrees. Okay, so that's it. We know everything there is to know about this circuit, about the components at least. So now let's start doing some calculations. All right, let's put some of our famous pieces of information up here. So what do we know? Let's put Ohm's law, and V equals I times R, but we're doing the new Ohm's law, which is, or the modified one for complex impedances or just for impedance in general. And remember, impedance is it's the opposition to change in current, change in voltage, and remember it's complex and it's for AC. So when you're talking about impedance, you're talking about AC circuits. An AC circuit can have a frequency of 0 though, so you can always use the word impedance if you like, but typically impedance is for AC circuits and it's a complex number which has a real part and imaginary part. So this is the equation right here. We're using V equals I times Z. And now we can figure out whatever we want to figure out. So why don't we first figure out the I in the circuit, so the general current in the circuit. And remember, the current's going to flip back and forth. One time it's going to, at one phase, it's going to go this direction, and then it's going to flip back and go that direction, all right? Doesn't matter. All right, so let's figure this out. So based on our formula up here, we have I equals, all right? And so I would equal V over Z. All right, so what do we need? We need the Z here, so we need the Z total. So we can compute what the Z total is very easily. So we want V over Z total. So to do this, we have V, that's right there, right? But we need Z total. So to do that, we simply need to add up our two complex impedances for the resistor and for the inductor. Okay, so that's easy to do. So Z total equals, what does it equal? It equals ZR plus ZL, all right, which, let's do it right here. So ZR is 200 plus 0J. And since we're doing addition, we're going to use the rectangular format. If we're multiplying, we would use the polar format, but the rectangular is better for addition. So what do we have? 200 plus 0J, 200 plus 0J, all right. And then I'm just going to put a plus here, if that's okay with you, ZL, which is 0 plus 1.38J. And just so I can put them under each other in column form. 0 plus 1.38J.